Okay, just letting you know that we are live and we have opened the doors. So I know we're still getting set up. We're going to give you guys 10 minutes or so. I mean, of course, take as long as you need to get us all perfectly or as best as we can connected. And we'll let everyone come in and join us so you can watch the setup here initially. And then I'll welcome and say hello to everyone in about 10 minutes. Good morning, Henrik. I'm just going to check in with you. We do have pretty good number of participants joining us, and we already have a lot of chat going on YouTube. How are things? Are you who's connected to Hawaii this morning?
I am right now. We're setting up the instrument, talking to the telescope operator. There are some clouds out in Hawaii, so we'll see what we can do, but we're just getting set up.
Okay, I'm going to stop sharing so people will be able to see your videos and hear you for a little bit. And again, I will do an announcement in a few minutes. Ah, I see. I have left the chat on in Zoom. So we have lots of people saying hello, hello, everybody. Lots of. Oh, good. North from Cumbria. Maryland has joined us this morning. India is here as well. Just want to give a shout out to India this morning because I got an email from someone in India this morning and said, "Oh, Miss, can you please send out the link?" And I realized I hadn't sent out the link to everybody on Eventbrite. So thank you for that. Scottish Highlands and Thailand. Guys, we're getting people from all over the place. It's very exciting. I don't know if you're talking with us, Henrik. I can't hear you. Or if you're speaking to the telescope people.
All right, I believe Henrik's talking with Tio at the moment. We'll be just setting up the first sky and star lines and sorting out comments. Just fairly use probably for myself than anything, that I know kind of what's going on at the moment, because we end up with a lot of observations that you get very mixed up between what happened on what day, when, and why. So we often have to leave comments for ourselves. I will apologize at the moment. I am also very distracted. I am trying as best as I can to also get in on the conversation. So I could probably reiterate, at the moment I'm not in that conversation. But Henrik's been a long time observer, so they're pretty, I think they're probably more happy to see that he's about. Oh goodness, yeah, sorry. As I said, I will very much apologize to everyone on the stream.
Not at all.
Thank you very much for joining, everyone. Do appreciate we have everyone around the world, and that's very exciting. A little bit nerve-wracking, I'm not gonna lie. But we'll do our best today. I'm gonna see if, should I pin my second screen for that to be the main focus?
You give it a go. Let's see what it looks like on YouTube, and then I guess I could just, if I
So right now we're focusing the telescope to make sure we get sharp images.
Okay.
So that's just a faint star we're focusing on.
Okay. Is that the one that I put in, or is it a different one? Sorry, I was going to ask, is that the leading star that I put in the notes, or is that a different star that we're just checking?
You do have a 3-button mouse, right, Henrik?
I do, yeah.
Yay, me too.
You found one.
You're in ahead.
A good chat going on in the Zoom with all our attendees. We had nearly 500 people register by today. So and registration for this event, this 3-day live stream, is still open. So if you have any friends who want to join us directly on Zoom, then just send them to the Eventbrite link. And otherwise, you can watch us live stream directly from YouTube. But of course, it's more fun to be here with the astronomers.
That's the TO. Can recognize the voice.
How's the primary mirror this time, Henrik? Last time, was that all good last time when we were observing Jupiter? That was kind of interesting and fun to see what that was like.
I don't know if Henrik can take questions. Sorry, can you repeat the primary?
The primary mirror last time when we were observing Jupiter had been changed, and I think needed to be calibrated or something. And hopefully there's no issues that time, or there's no maintenance going on today. I don't know.
I had maintenance 2 days ago, I believe. So we should hopefully not have any issues on that side. In the past, we've had a slight technical issue with a macro. Basically, it's a lot of code saying, could the telescope specifically do these set of maneuvers? And yeah, in the past, it's been tricky. One of the macros we had set up, which basically asked if we could keep moving the slit further and further and further down Jupiter, or further and further up Jupiter, to basically just take a scan, as we'd call it, would just break the telescope and it would stop working, and would have to completely basically turn everything off and turn everything back on again to restart it, which just kept happening. So we had to keep, well, I think we eventually had to unfortunately call up the main person in charge of the telescope, well, not telescope, wow. the instrument itself, which obviously in Hawaii is about 3 in the morning. So they were very groggy, very tired, and were asking us several questions which we didn't quite know how to answer.
And that's just pretty amazing to know that there's always someone there 24/7.
Yeah, I mean, almost 24/7. So they will have a group specifically, well, to my knowledge, there may be a different spin on, but to my knowledge, there's a group who'll be doing engineering, and they'll be there usually during the day because most people don't want to do daytime observing.
Right.
I know there are instances, obviously, if you do want to look at the sun or around the sun, then obviously that's going to be very useful. But typically you'll have the TOs, that's the telescope operators short for, and they'll be on site pretty much from the start of the night till the beginning of the morning. So
Wow.
they do the night shift essentially.
Yep. So that's another perk of being an astronomer is sleeping during the day.
Exactly. Except we also need to do the work in the day as well.
And Henrik, I don't know if you know you are muted, so I don't know if you want to speak with us. We can't hear you.
Oh.
Is he still there, Henrik?
Maybe.
Yes, I am.
Okay.
I got the instruments on the same screen as the Zoom, so we're focused up. Fairly decent skies right now, so we're going to go to star first.
Okay, shall I do an intro now and then sort of just say hello and welcome everybody at this point?
Yeah, sure. Yeah.
Okay, great. I just wanted to make sure we sort of do a proper hello to everyone. So I'm just going to spotlight my video here, make sure that all changes. And let's see here. Probably, am I still sharing? No, I'm not. Okay, well, I just want to say hello and welcome everyone. I see a lot of people in the chat from all over the world, actually, to the 3-day live stream of the weird and wonderful world of Uranus. Hi, my name is Lucinda Offer, and I am the Education Outreach and Events Officer for the Royal Astronomical Society. Have you ever wondered what a professional astronomer does? Well, today you're going to find out. If you haven't already been observing since we started, lots of setup technical issues and lots of problems to solve as we go. We will be remotely observing Uranus from NASA's Infrared Telescope Facility, the IRTF atop Mauna Kea, Hawaii, to watch astronomer Emma Thomas, who is here with us, and also Dr. Herschel Museum, part of the H3+ astronomy team at work from the University of Leicester, although some of them are around the world as well, who will join us later as we go through our 3-day live streaming event. We're going to see what discoveries might be made. We're going to get updates from the astronomers as we observe, and throughout the day of observing, we'll hear from our RAS librarian, Dr. Sean Prosser, who will be sharing about the history of the search for Uranus and its connection to William Herschel, who was our first RAS president at the Royal Astronomical Society. Charles Draper from the Herschel Museum in Bath, he will be joining us today, where William Herschel himself first discovered the planet with his own homemade telescope 240 years ago in 1781. And he'll be giving us a tour of that and some really great information, and he'll join us live today. We'll also have special guest appearances by scientists who will join us throughout the live stream over the next 3 days. They're going to share insights about the weird and wonderful world of Uranus and other things. We're going to hear about brown dwarfs. We're going to talk about exoplanets. So we're going to be looking at all kinds of areas around planetary science and also doing our best to connect it all the way back to Uranus. But a lot of really interesting and current new, all these scientists who are doing research now. So this is what's so great and exciting about this is this is their current area of research, and we're going to be hearing from the experts. So let me just introduce who we have with us today. Emma Thomas is a third-year PhD student at the University of Leicester, whose research is to investigate and document the infrared aurorae at Uranus so that we can understand how space weather impacts with Uranus's magnetic field and atmosphere. And Dr. Herschel Museum is a planetary scientist at the University of Leicester, who is the world expert in measuring the Uranus ionosphere with infrared measurements and has recently presented about this at the Royal Society. He has also published several papers detailing how the upper atmosphere of Uranus is cooling and continues to cool in ways we don't fully understand. So that's going to be part of some of the observations that we're going to be making today. Is that correct, Henrik? We're going to be looking at temperature. And of course, Emma, we're going to be looking at aurora, which is really exciting, hopefully. Fingers crossed.
That's right.
Fingers crossed,
Yeah.
I will say for just the general public today, fingers crossed we're going to be seeing some interesting bits and bobs on kind of the imager, as well as mainly the spectra. We're going to be more excited on the spectra because the imager itself is not in the exact wavelength we're looking for, but it just makes it easier to see Uranus itself. But the exciting part, we're hopefully seeing areas of the spectra light up. It's probably something we're going to go into more discussion about anyway in the next 10-20 minutes or so, but the interesting part should be if we start seeing areas light up as trying to actually observe the Uranus aurorae are very, very tricky, and again we'll get into more discussion as to why that is in a bit. I will also apologize. You're going to see me flicking my well, where I'm focusing on a lot. I currently have about 3 devices going on in the background here. One of them is, well, you'll see an Emma 2. That's my second screen. That will basically be the output of whatever I'm looking at. I am currently just trying to refine a output screen. That's what it is. So that everyone can see what's kind of going on our end. Once I have that ready and done, I will have that up. So bear with me. We'll have about 2-3 minutes and we'll get this sorted. Oh, thank you very much. She is, this little kitty here is my number 2 in helping me out, especially when I'm working from home. She will be complaining quite a lot through this because I'm not doing my usual. So apologies if you hear her yelling in the background. Please don't think that I'm being mean or abusive in any kind of way. She is very, well, she's deaf, so she screams really loudly so that we can hear her and so that she can hear herself.
It's always nice to have a cat around and our pets. But I realized that I didn't share the program with everyone, and I have a question in the QA about that. So if that's okay, I'm going to go ahead and do that really quickly and just show everyone what we are expecting to see and do today. So thank you so much for Katrina Jackman for asking me that. So we're on day 1 today. Is Friday, October 8th. We are observing from Mauna Kea, and this is the IRTF here. And I should say we are doing this in collaboration, of course, with the RAS, the University of Leicester School of Physics and Astronomy, and the Herschel Museum of Astronomy, as well as the Bath Preservation Trust. And hopefully I haven't, and the Bath astronomers are going to be with us as well this week. So very exciting. Today's program, so we're just getting set up pretty much shortly. If there's been much, we are going to have Emma and Henrik discussing the science, and then hopefully by 10 a.m. We got an update of the telescope view of what we're observing. We're going to have a classroom from London, I believe the Garris Primary School, if I'm pronouncing that correctly, at 10:30 a.m. We're going to continue to do updates throughout the day of what the astronomers are observing. 11:30 a.m. we're going to have Dr. Jean Prosser visit us and give us an update, I believe, from the RAS library directly. I believe she will be there. And then Charles Draper will be joining us from the Herschel Society. We'll have a Q&A with the H3 Plus team. And I don't know if we're going to have more of the team members join us by 12:45, but I think as we go on through the day, we'll have at least a couple more members join us. Dr. Lee Fletcher from the University of Leicester will be speaking with us at 1 p.m. Again, another update and another possibility to ask your questions to the H3 Plus team. Dr. Will Dunn's going to talk to us later about his research with X-rays. He's also going to talk about Uranus's magnetosphere, aurora and magnetosphere. And another update. And we're going to finish with the Westminster School visit, GCSE astronomy class there in the UK here in London, and have a Q&A session with that. And I'm sure before we leave, we'll have a final update. We got some raised hands, lots of things happening, a lot more interaction than we did last time. And I think the one last thing I do want to say is thank you so much. If you have any questions, definitely put them in the QA boxes on Zoom and YouTube. I don't know for how long I'm going to keep our chat open, so on Zoom, because it can be a bit distracting. But if you want to, you can tell us your name and where you're from. And thank you. People have been doing that in the chat, and I'll continue to talk about where we got people from. And or you're welcome to always remain anonymous. So thank you so much for being here. And I'm going to get back to Emma and Henrik.
Well, hello everyone again. I'm still working on getting the output. I'm so sorry about this. I have recently changed laptops as well as changing a desktop format now. So I am trying my best to get a good output. It may not be as shiny as I was hoping it to be, but you know, it's what happens live on the day. So that's first. I'm just getting the second up, and then hopefully we may have something nice and shiny to show everyone. I do thank everyone for your patience with this. It's a slight handful because as today I am the lead observer, or PI, as we often get called. That's the primary investigator for the observations that we're doing today. So today's observations run from 10 o'clock in the evening in Hawaii. So that's 9 o'clock here in the UK, which is plus 1 hour of UTC, which is universal time. But it just gives us a heads up of kind of what's going on. In terms of how long we're expecting to be observing. Hopefully we have 7 hours and 55 seconds, or essentially 8 hours of observations today at Uranus, which sounds like a lot of time, but because Uranus is so far away, it's very difficult to build up a very good signal, unlike that of Jupiter, where you could probably look at Jupiter for about 10-20 minutes and get a suitable signal to noise ratio to do any of your data. At Uranus at the moment, we're finding we need about an hour and a half as kind of like the comparison here. So having about 8 hours gives us enough for us, you know, a reasonable amount. I can pin myself if people want to see me.
So we're taking observations of a star right now, a calibration star. We've got 5 minutes left on that, and then, well, we'll see how it looks first, but then we can head out to Uranus.
Lovely.
It's exciting, isn't it?
Yeah, so remind me again, the star that we're looking at today is A0?
A0, yeah, that's the spectral type. Right.
Okay. Sorry, I'm juggling. I was going to comment on that because we typically use an A0 star to help us with working out, I think Henrik said, about calibrations. Calibrations are incredibly important when it comes to doing spectral work. The reason for this is that well, essentially the numbers that we get given from observations are basically what photons will be counted. And they get basically converted into CCD counts. CCD counts are great and everything, but that doesn't give us an actual idea of the amount of the light that's coming into. But say the light, I'm meaning more in the sense of the flux, so the rate of light that's kind of coming in. Well, rate, volume, all the fun bits and bobs in between. So because of that, we have to take a standard, or in this sort an A0 star, where we know what the flux is or the intensity of that star is, so that we have a comparison with what our values are to that star, so we can actually get some of the science out, rather than just being like, oh, it's about 4 photons or 4 CCD counts, which isn't too helpful to the science.
Yeah, it's a way of quantifying in energy what we're seeing, right?
Exactly.
Okay.
Okay. I am nearly done. Thank you everyone for bearing with us. I feel so terribly sorry because I will be nice and ready for tomorrow. So everyone's going tomorrow will be poised. I'm sorry, Henrik, did I cut you off?
Oh yeah, no, nothing. I weren't seeing data coming in, but I was looking in the wrong box. Okay. So that's one AB pair. What's the, yeah, sorry, right.
There we go.
So it's important that this calibration star has a good, strong signal. So the stronger the signal on the star, the lower the sort of errors of the uncertainty we're going to get on our Uranus values, ultimately our Uranus temperatures. So how hot is the very top layer of the atmosphere of Uranus? And the better the signal on the star, the lower the uncertainty on those temperatures. So like Emma said, this is a super important step in getting things absolutely right. It's obviously not the most exciting step. That's just something we have to do.
I'm just getting up so I can hopefully put this up. Oh, yep. And then there we go. Very unhelpful place for that. Okay, there we go. Hopefully everyone can see that. Apart from I'm sharing the screen with myself. So let me unpin myself and then that should help. There we go.
Hello.
Oh, hey, Riyang. So yeah, okay, that's all good for schedule. Yeah, so at the moment, this is kind of the layout that we've got to give an idea of what's going on the screen here. So at the left-hand side, we have the Uranus cam, which technically isn't Uranus cam at the moment. It is the star. So that's the very bright thing you can see in the green box. That's the star, calibration star that we were mentioning that we're looking at. On the right of that, that's the spectrocam. That is essentially the orders of spectra. What I mean by that is basically as you go from left to right is, I believe we're increasing in wavelength. And basically any emission lines that we get from stars or we get from specifically for Uranus will be seen in this spectrocam. At the moment, we're building up the star spectra, so you should expect to see basically very long streaks of lines. Long streaks of lines on the spectra, basically one black line and one white line. And the reason for black line and white line is because we do what are known as AB pairs. AB pairs are, in essence, we take the star at one position and that's known as position A. And then we will move the star along the slit to position B. And if you do an A minus B, your B is going to become a negative and your A is going to become a positive. So you'll end up with basically two long streaks along where you would expect. Two long streaks from the star. So sorry, I have two bits of chatter in my ear at the moment. So I'm just keeping an eye on both. It's not coming through the right bit. Excellent. All right. Sorry, lots of technical issues at the moment. So otherwise, yeah, the other two things that we have going on here. So yes, I have a schedule at the bottom. I may have to get rid of that just because I'm having to do it by myself. And I am, unfortunately, I put myself in charge of a lot of things I didn't realize I was going to do until it dawned on me today.
That's quite okay, Emma, and I think that's a great idea.
I said I'll try and do what I can on the scheduling, because I do want to let people know kind of what we expect is going to come up next. And then, yeah, finally, we have 2 movies going on. I may change these as we go, because at the moment, this isn't, as you can see about how sped up things are. These aren't the actual Sky Above IRTF and Inside IRTF. These are movies from the previous night, so that was last night. Of just kind of the observations that were going on. So you can see inside IRTF, there's a lot of static, and then suddenly come on and then turns back off again. And that's kind of giving you an insight into how the TOs will basically come in, will turn the lights on, and very quickly will then turn them off to then start the observing run, but you still kind of see things being lit up as, the telescope is in operation. Outside, so that's just kind of like for the couple of hours. I think you normally have about 8-9 hours GIFs, and you can find these online if you look for IRTF cameras. We normally do that ourselves just to see kind of how the conditions are. It's great, obviously, being communicated that it is, it's cloudy or it's snowy on the top, but it's a great way, especially if you're doing remote observing like we are for, been doing for the last year or two. It's great to kind of actually be able to see it in person of kind of what's going on. And then, yeah, finally we have the Sky Above IRTF, and that's essentially just a camera that is pointed straight up. This is technically above the Gemini telescope rather than IRTF telescope, but Gemini and IRTF work pretty much in the same area, so the sky view won't really change dramatically more than what you're seeing on the right hand side. So yeah, that's kind of the layout that's here. I hope that it is sorry, I've got a question from Christopher saying, cannot see what Emma is talking about. Is the output? I can see it on my other screen.
I can see it on YouTube. So what I could do is I could spotlight the big screen for everyone. So, and then that might help them see it larger, and then going over it. I think it'd be good to go over these cameras again and again anyway throughout the day. And as you said, you might change them?
Yeah, so I have stills instead. So instead of it kind of constantly on a loop from the previous night.
Okay. They're saying on Zoom, they can only see one screen. How's that, James? I see one screen, but YouTube sees 3. So, okay. Well, I don't want people to go to YouTube, but you can watch both simultaneously. What is it like now on Zoom for our Zoom attendees? Hopefully you guys...
Are we there? Are we there? Oh, that's me, yeah. We just arrived at Uranus, so we'll get our first views, hopefully right now.
So let's see here.
Ooh, not guiding.
How about now? Okay, on screen still the 5-panel one. So it looks like they can now see the one screen with I think this is the panel. I'm just highlighting the panel now. I guess we're going to call it the panel. I don't know what else to call it.
Okay,
nice.
so they can see 5 panels in one screen. So I'm guessing they can see everyone's videos and the one that I'm showing, but it's not been like the main focus.
So I think I'm just showing that panel. And then, yeah, YouTube had the gallery, but for whatever reason, it wasn't being shown in Zoom for the gallery. So,
I'll see you chaps later. It's good to see you again.
Put you on gallery. Let's see. Hopefully, let's take off the spotlight.
Can you see Uranus on the Zoom? Did it come up?
I can see it currently. I believe that's up. It looks bigger than the star, wherever I'm looking at. So.
Yeah, it is. Right, that's.
I may just have to have my speakers up, so apologies to everyone on stream. I just can't hear anything coming from the No, that's not going to be a good idea. All right, I'm just going to have to be mute for in the Zoom call. The other
And
one.
now I'm going to give you an
minutes.
update on Zoom, a Zoom update here. So Zoom does all these actually software upgrades and updates. It allows me now to change attendee view, which I didn't realize before. So now I can switch for attendees to see the whole gallery now. So thanks for highlighting that. And you guys should all see Henrik, Emma, and the panel of the 5 paneled screen. Thank you.
Thank you for your patience. I'm happy to reiterate what I was going through. So yeah, sorry for everyone that was on YouTube. You're probably going to be bored by this, but just a reiteration. So on the left-hand side here in our view, we have the Uranus cam that at the moment should have Uranus. You can just see that's basically, well, I believe, frustratingly, I haven't got myself connected into the Zoom call with the TO, so I can't get an exact idea of what's going on.
Well, yeah, that is Uranus.
Yeah, okay. It is Uranus, and we've got one of the moons at the bottom.
Yep. We'll find out which one. Oh, 3 moons.
Oh, 3.
Whoa.
Awesome.
Excellent.
So yeah, we'll probably have a quick checkup on the orientation of Uranus to just confirm exactly which of the 3 moons that we are looking at. But the very faint glows that you're seeing on the bottom right of Uranus are the moons. We will basically be using that to kind of get an idea of, where the slit is on the planet, as well as the angle of the slit on the planet itself. We then have to the right of it, if possible. Yes, it is possible. I will get to a screen where we can look specifically at that. I just would like to go through just kind of everything, because you'll be seeing a lot of these. Seeing a lot of these images, because some of these will be relevant to some of the discussions we'll be having.
Let me just check. Sorry, Emma.
No, it's fine.
I'm in the wrong Zoom room. Sorry.
So secondly, we then have the spectrocam. That is the idea of basically the data that we're getting from Uranus. Sorry, there's a question: is this being observed from a satellite or from the ground? Okay, yes. So, Krishna, thank you for the question. I should point out this is being observed from on the ground, but this is being observed in Hawaii, over in America. So, though it is daytime in the UK, it's currently 10 o'clock in the evening for Hawaii. So we're now in the middle of the night. I say the middle, a couple of hours into nighttime at the moment. Hopefully I will be able to pick up a picture shortly to be able to kind of show what's happening at IRTF. Again, thank you for your patience with sorting out the technical side of things. It's only been really today that I've been able to grab everything that I needed. So again, feel free to ask these questions. Some of it may just be that I am just sorting out the technical side of things. And then, yes, lastly, before I will see if we can flick to a more zoomed in version of the Uranus cam, is we have the inside of IRTF and the sky above IRTF. Inside IRTF is at the bottom and sky above IRTF is to the right. Inside IRTF is basically a loop of about 8 hours showing you kind of the inside of the telescope of IRTF. Occasionally you might be able to see an observer or a TO, as we know them, which is basically the technical operator on the telescope, and you'll be able to kind of see how it moves and interacts. Whilst the sky above IRTF is essentially a camera that is pointed directly above the telescope. Technically, this is at Gemini rather than the IRTF telescope. However, Gemini and IRTF are basically on the same area, both on Mauna Kea in Hawaii, so the sky should be relatively the same, and gives quite very pretty pictures. So thank you for bearing with me there. I will quickly need to first off take the camera down and then change over and then put the camera back up again. So bear with me on this because I need to, I can't see past this main one, so you're gonna have to see me down here. Apologies. There we go. If we take ourselves this way. Nope, that's not the right one. Yeah, sorry about this. I only have 2 screens and then my 2 devices and everything else. So you may occasionally see stuff come up. So I will do my best to mitigate that as best as possible. So stuff in the camera. Okay, there we go. So I can now change over to the cameras that I need. Again, thank you for bearing with us in this. Oh, goodness, sorry. There's a couple of fiddly work going on in the background as well with the Uranus slot. So some of this is going to be a bit funky. So that's going to go there. Again, apologies. Some of this is going to be very, very boring as I am trying to set things up.
Not at all, not at all. And I thought if we just, setup is, I think what I like about this is that, technical difficulties and setting up and having problems is part of showing what astronomers deal with when they're trying to observe what they want to observe. And so I think that's quite okay. And I thought, I know we're due to have some updates and things, but I think it's okay if we wait until 10:30 when the class gets here, if you're okay with that.
Yeah.
To do that then. So if you need more time to set up, not a problem. I think it's all still very exciting to see. Look at. You're doing a great job, Emma.
Yeah.
Trying what we can here. As I said, you're getting a very fun view of me actually just doing it in person at the moment. This is what I'm doing in the background. Because unfortunately I'm still very new to OBS. I've only really been using it for like the last, I say year, but that's only when we're doing live streams. So it's only a couple of times a year I get a chance to use it. I don't
I'm
live
really
stream
impressed.
Myself.
Very impressed by it.
Haven't got the guts to live stream by myself. And if it would be, then it would probably be video gaming. I'm better at doing video gaming.
I noticed you have really cool what are they called? Can't even think of the word, but you have a gaming chair. I see you have a gaming chair behind you.
Yes, well, this is my other half.
And headphones. Headphones, that's what the word I was trying to, really cool headphones that light up.
Thank you. Yeah, I tend to go kind of for the expensive stuff and gaming stuff. It's usually not worth it, but sometimes, the shiny parts are quite pretty.
I'm going to look for those headphones or put on my Christmas list.
So yes, I've gone for a zoomed in version. Again, apologies, I think, with the output, as well as the fact that this is the screen that you're actually seeing. This is actually much larger than the over here than what I have. Hopefully you can see that that's the size of my mouse. So the screen that we've got zoomed in, blown up on Zoom rather than zoomed in on Zoom, because that ends up with too many zooms. It's quite a small window. So unfortunately it may look quite grainy, but perhaps that shows very well why we do have troubles of our own when it comes to looking at very small planets, such as Uranus. Looking at Jupiter and Saturn, they would essentially dominate most of this field of view that we're seeing.
Yeah.
So I think it kind of gives a good idea as to why we struggle a lot with the ice giants when it comes to observing.
So Emma, I'm also learning Zoom right now because it's so different to me. I took a nice break over the summer from Zoom and I see all these updates. So what I'm going to do for you when you need it, I can highlight or spotlight, the big 5 panel, or the panel is what I'm going to continue to call it. So if you want that big on the screen to all the Zoom attendees, let me know and I will make sure that is what's nice and big on the panel for them to observe while you're talking about it.
Cool, that would be appreciated. I'll give you a heads up when I'm remembering again. Apologies to everybody. I will be doing my best to remember what's going on. Today is very much going to be a touch and go instance. And so yeah, this is a slightly different setup than we had when we did this last year. I don't know if everyone came along to that, or we had a couple of people in the audience who also came along last year.
Is that when we were observing Jupiter?
Yeah, when we were chasing shadows at Jupiter.
That was so awesome.
That was fun, yeah. So we got a couple of dots just below Uranus, which is obviously a big bright blob. Closest to Uranus, right below it, is Ariel, its moon Ariel. And then straight down below Uranus is Umbriel, another moon. So that's pretty awesome. We should be able to see the rings of Uranus as well, but it might take some processing of this data. But it's all in there, which is pretty amazing, really. So the green box, I don't know if you mentioned this, Emma, but the green box is how we sort of steer the telescope. This is an imager, basically a reflection of a metal plate, and there's a hole in the metal plate, which is that straight line in the middle, and that light going through that hole goes into another instrument, which is the spectrograph. It sort of separates the light into separate components, and which is what you see on the left, the spectrocam there. So we can steer the telescope by holding Uranus within that green box. So we do small correction to the telescopes, adjusting it as Uranus sort of passes over us in the sky in Hawaii. So yeah, it's a nice way of holding the telescope steady while we get our data. So we're actually taking scientific data right now.
Okay, I was going to say, I'm just looking. So I see that we're doing, yes, sorry, I'm reminding myself of how everything's going. So we're going to be doing this next set of data for 200 cycles, so that's going to be about 1 minute, 30 times 200, that's a lot of maths to try and sort out.
It's 1,000 minutes, but we're not going to go for that long.
True.
You have a question that came in from Kevin asking can you say more about the moons of Uranus?
Well, I think Tom, who's going to join us later, might know more about the moons than I do. But
excellent.
Yeah.
That's okay. So I'll put that to the side for then. And Kevin's gonna. I'm sorry, not Kevin. Tom. I think around 1 o'clock or so is when he will be joining us. Thank you.
It's moments like this that I wish I could just call up some of the PhD students, because there's Oliver King in our department who does a lot of work with the moons in the outer planets. I'd probably be able to give him a call and have a much better idea.
Moons of Jupiter,
Yeah.
So on the right, if I can highlight it, maybe.
I don't know if you'll be able to highlight on my screen, but I can bring up.
I can do that.
Oh, yeah. No, you can do that. Yeah.
Yeah. So that is just on the edge of the field of view of this camera is a moon called Titania. It's very, very just on the edge. It might rotate into view. Oh, it's going to rotate out of view, maybe. We'll see. So these moons will rotate around Uranus as we observe the planet. And in the end, we should be able to stitch all these images together. Hang on, Tio's calling.
Nice. Yeah, so what Henrik's saying here is basically when we are doing our observations, we'll take a lot of pictures or we'll save the images from the viewer as well as the spectra that we're seeing, so the two images that we have up here. And as Uranus will rotate over the next kind of 7 to 8 hours that we're going to be observing Uranus, we can get a good idea, or we can actually be able to start seeing the moons rotate around the planet itself. So we may get to, as we kind of continue with our observations, begin to see Titania move into view, and hopefully in the coming well, tonight I'll probably be making a movie and be able to show for tomorrow the observations that we took from today. So I'll be able to kind of make a very short little clip of how that rotation looked, and maybe we'll be able to see Titania. We'll find out later.
Actually, I think there's a fourth moon there as well. This one here, you can see it. It's very faint.
Very faint, yeah.
Let me see if I can fix it here. Yes.
Yeah.
You see it?
Just about, I think.
That's Miranda.
Yeah, I was going to say there's always I think Miranda comes up quite a lot when it comes to her because it's so close.
Yeah, yeah. So all the moons of Uranus are named after Shakespeare characters, I think.
I believe so. So I'm not that up to date with the naming conventions of planets. I think we had a question from Arwin on YouTube asking about what the two blobs on the bottom right are. I believe that's the mention of the moons, but that may be me misinterpreting. That these are, I'm going to remind myself, this is Ariel to the bottom right of Uranus, but at the exact bottom or right down to the bottom.
Yeah,
is
this
Umbra.
is this is Ariel. And does that come up the box?
Yep,
yeah.
That's come up.
And this is Umbriel.
I've got another one from Rosie Johnson, asking, will we be able to see the moon Rosalind over the observations? Just asking because that's my name, although I'm not sure I'm named after the moon.
Oh, nice. Yeah. I don't know, Rosie. We're going to have to wait and see, aren't we?
Yeah.
That'd be cool, though.
It's certainly a good treat if we do get to see it.
Yeah.
How do we know which are moons and which are stars in the image we have from Simon Waters?
So there's some great tools on the internet which NASA provides. You can plot sort of the view of Uranus from the Earth at any time. It's called, quite simply, Uranus Viewer. And so if you type Uranus Viewer in Google, you can do this set the field of view and the time, and it'll calculate what the system looks like. And you can add all kinds of moons. I mean, I think Uranus has 79 moons in total or something like that. Obviously, most of them are like tiny, so you're not going to see any of them, but it's sort of the classical sort of 4 or 5 that we can see from the Earth are going to be in there as well. So yeah, we basically get a star map, but it's just the Uranus system. I think you can add stars to it as well. But yeah, it's kind of neat. And you can do that for any planet, Jupiter, Saturn, Uranus, and Neptune. Any giant planet, that is. So NASA's been very helpful.
Yeah, definitely. So it's the go-to when trying to work out from your imager what's going on.
Yeah.
I should
Emma,
briefly come back to it. Yes, sorry.
The view in spectrocam, that's the A frame, I think.
Okay. Okay, I'm going to.
I don't know how I mean, you're the wizard on the OBS.
No, it's okay. I need to fiddle then, so we need to take the view down for a second.
Oh, okay.
It's all right, but bear with me, everyone. Sorry about this. It's going to be a lot of working and toing and throwing and all lots of fun.
She says, sighing. Yeah.
It's okay. As I said, it's me juggling 2 jobs. I did see in the YouTube message I should pay someone to do it. I wish I had the money to do it, but I only get paid peanuts to do this kind of work, unfortunately. I could ask my other half, but I would feel a bit mean on a day off to ask to do this. So I'm just juggling this myself.
I think you're doing a great job.
Thank you.
You're doing something no one else has the skill to do, so I think that's great.
I'm just trying to stop the video. There we go. Sorry, we've got a lot of lag on my other computer because it is chugging away trying to juggle everything. Okay. Gonna see how this goes. Ooh, all right, this is gonna get very fun indeed later on. I say, sorry, what I mean by that is I am juggling with these 2 screens, and I will also later on be basically taking over for Henrik, hopefully, just so that I can kind of get my own experience, because I'm still, I would say, very new to observing. I know that I've got over 100 hours. I've done a lot of observing runs. I've looked at Jupiter, I've looked at Saturn, I've looked at Uranus. I don't think I've looked at Neptune just yet, but I'm sure we could sort that out in the future. But the big thing at the moment is just trying to juggle it all. And yes, I have at the moment trying to sort that out so that I can hopefully do the observations myself and do a lot of the technical side of things, hopefully while still talking to people, but we'll see how I manage. But because of that, I need to have a display where I can fidget, and I don't want to fidget with the display that I'm currently giving to you as the audience. Hi, Sissy. Sorry, that's the cat going to say hi. She may hear us very shortly because she'll probably start complaining that I'm not paying attention to her. Oh goodness, yes. So, oh, hello. Sorry, lots of fidgeting. It's probably going to be the same tomorrow. Hopefully not as much, but we'll see on this. Again, I am so terribly sorry that it's not as easy to sort all of this. It's a lot of toing and froing. As I am just getting used to trying to get this all sorted myself.
There's a lot of problem solving when you observe. I guess that's science in general, just trying to solve different problems, different challenges.
Well, I was mentioning at the start, I don't know if we had everyone there, but we had the issue with our macro with Jupiter. Okay, sorry, it's the cat. Where the macro stopped working because I wouldn't say the telescope broke, but because of the macro just no longer taking the changes we were asking of it, if I was correct.
Just coming a little late here to Henrik's earlier question about the moons of Uranus, pulling out all my GCSE astronomy PowerPoints.
Nice.
Here it says Uranus's moons deviate from the Greek-Roman nomenclature. I guess that's what's used for maybe other moons, but instead all the moons are named after characters in plays by Shakespeare and Pope. So there you go.
So Uranus is a very cultured planet, isn't it?
Very cultured.
Yeah.
Goodness. All right, we are nearly there on the output. Go.
That'd be good. I think we actually got some what looks like very low quality data right now. I think we might have something.
There we go. I may still fiddle. There we go. There we are. Oh, goodness. Okay, so that's Q1?
If
it's Q3, I'd be shocked. Yeah. Okay, so sorry, we're using the fancy words, technical words. So for our analysis for infrared, specifically with Uranus, we use a molecule known as Hc+. Hc+ is created essentially through two processes. One is through interactions with extreme ultraviolet light by the sun, or the second process is due to internal processes within the planet itself, usually to do with the solar wind and whatnot. So what we expect with the planet is there to basically be like a glow over the whole planet. And that's the interaction with the EUV, with there not being that much on the night side of the planet because the sun's not on the night side. But any interactions that are happening within the planet, the atmosphere, or such as the aurora, those should be very localized on the planet. So that means they just light up at specific points on the planet. So that's where we can actually determine the difference between what's aurora and what's just the interaction with the sun, or just the day glow of the sun itself. When we're looking at spectra, there are specific points or wavelengths. So if we look to the spectrocam, you might be able to see it. I'm going to put my mouse just there. So you see that there are these bands. We're seeing kind of staticky noise, then it's fairly quiet and staticky noise. Everything that's in the staticky noise is what we are taking in from the slit that you're seeing in Uranus cam. So just here. Basically, if you imagine that's been rotated by 90 degrees and then basically smeared across over many wavelengths. So along this line is basically wavelength, and along this line is basically spatial information across the slit. Going back to what I was discussing before about this A-B patterning, Uranus is basically here in the A frame and over here in the B frame. So we're doing an A minus B, which gives us one bright line where Uranus is and one dark line where Uranus is in the B frame. Now, going back to Q1, Q1 and Q3 discussion. Q1 is the fundamental emission line, and what I mean by that is there are certain orientations, I suppose you could put it, that HT plus emits at, or what I mean more specifically, there are set wavelengths where HT plus molecule will emit at. And at the moment, the brightest, especially when it comes to Uranus, or the easiest to see, is usually the Q1 line. So that's the fuzzy line that you're seeing here, just at the very bottom. It's just on the very bottom of the spectra. We're having a look out because usually around in this top band, you should then start to see Q3. It's very possible this could be a Q3 line just here. But as we continue to build up signal, we'll find that out. But that's very exciting. Sorry, I think that's me in the background. Sorry, gotta mute everything. But yeah, that's exciting if that is a Q3 line, because as I was mentioning at the very start of our observations, when it comes to observations at the outer planets, it's very difficult to try and get a signal to noise in comparison to big planets such as that of Jupiter and Saturn. For Jupiter and Saturn, you can take data, well, small with Jupiter, you can take data for about 10 minutes, 15 minutes, and you'll have a pretty strong signal that you can start working with. However, for Uranus, the last time we kind of did these kind of calibrations and our approximations is to get enough signal to noise to do our data analysis, which is essentially looking across the surface to see where we're seeing these peaks of light. Takes about an hour to an hour and a half to take enough data. So it's exciting that we've been doing this for, I'd say, half an hour, and we're getting some signal in.
That's really promising, isn't it?
Yeah, no,
yeah.
that's a sigh of relief for me, to be honest, because I said at some point I will be using this data and trying to get results from this, and it can be very frustrating coming to the data and just not being able to see anything, because it means a lot of headache trying to get it sorted.
Yeah, if we were to point a telescope at Jupiter, it'd take 30 seconds at Jupiter to get the same sort of quality of signal. It takes 90 minutes at Uranus.
Yeah, it's crazy.
Yeah, it's just, HU plus is just so faint at Uranus. And it's getting fainter with time as well. Sort of, HU plus was first observed at Uranus in 1992, and sort of we've been observing it. Well, not we, Emma and I, but people have been observing it over the past 3 decades. And it turns out that Uranus's upper atmosphere, that's the very top of the atmosphere, has been cooling for over 3 decades, and almost 3 decades, I guess. And that's sort of a mystery, and we don't really know why yet. And that's part of the reason we're doing these observations today, is to see what's the temperature of Uranus's upper atmosphere right now. We'll find out. So it's gone from really hot, basically at solstice in 1986, it was solstice, to really cold. The next solstice is 2028. So it takes Uranus 84 years to go around the sun, which is a very long time. And I guess you can spend your whole career sort of observing the motion of Uranus around the sun. That'd be a nice job, actually, if there's funding available. I'll do it. Yeah, I'll do it.
Goodness.
Right. So the upper atmosphere is cooling on timescales of decades, and it's one of the things we've discovered using HU+. So it could be related to Uranus's weird geometry. It rotates on its side. It has a magnetic field like a lot of planets, but the magnetic field is sort of offset from the rotational axis like that. So every day, a day on Uranus is 17 hours. So every day, the magnetic field sort of flaps around as the planet rotates on its side. So it is a weird and it is a wonderful system that we really know nothing about. I think ultimately what I want to see, I don't know if you agree, Emma, but we want to send a spacecraft to Uranus.
Oh, goodness, yes.
It's only really been visited once. So the Voyager spacecraft, Voyager 2, flew by in January 1986, and that's a long time ago. And if we send a spacecraft today, we can build modern instruments, not sort of 70s era instruments, modern instruments to really find out what the secrets of this planet are, including the upper atmosphere and the aurora, its moons, the deeper atmosphere. Yeah, so many fascinating things we have yet to learn about this planet. And some things we won't learn just by observing it from the ground. And some things you have to do in orbit around the planet. One of the issues, of course, is that Uranus is 19 times further away from the sun than the Earth. It's really far out. So it's going to take maybe 15 years just to get to the planet after launch. So it's going to be a mission for basically the next generation of scientists, like Emma, I guess. So, yeah, let's make it happen.
Something gets proposed. Yeah, exactly.
Yeah.
I was going to add, I think if we have time, we have a couple of questions. I will go to YouTube, but first we have with Zoom. I've got from Kevin Webb. Asking myself if I've always wanted to be an astronomer. That's an interesting question, if I be honest. Back when I was doing A levels, I actually wanted to be a doctor. Very, very different career path. Ended up not, because if I'm be honest, I was not doing very well in chemistry, and I didn't think I could make it if I was gonna need to get all of my science, or particularly biology and chemistry up. So I eventually went, okay, well, what's another science career path that I quite like? I was always kind of into space, but not. I feel bad saying it, but I'm not one of these people that was there like, oh man, since I've been born, I knew I wanted to do space. But back when I was a kid, my dad did his degree here at Leicester, and he did geology and astronomy, so he was always into space and would discuss a lot with me about kind of what was happening with the planets and what he liked and was very interested with, and very, very frequently remind me that he at Leicester was one of the people that got to experiment and look at the rocks from the moon. So yeah, he loved telling me that every time he possibly could, to remind me the special stuff that he'd done. So yeah, eventually it kind of came to when I wanted to make my decisions about going into physics or going into something area. And I remember at the time being like, you know what, I have the hardest time doing really well in physics, and it's the best way I find motivation for myself. If something is very hard to do, I want to do it. So I was like, yeah, you know what, I want to ace my physics. I want to do really well with my maths, and that's what I want to do. I want to go off into physics. So I went to Leicester. I only did straight physics rather than doing physics with astronomy, which again relies back onto this kind of idea, whereas they're like, I like physics, there is some space, but then I also am interested in knowing what's going on with some elements of the quantum side of things. I'm also interested in like, honestly, it was a lot of things at the time I was very interested in. I just have a natural curiosity for wanting to know how things work, and if they do work, why they work, and if they don't work, why they don't want to work. But yeah, what helped me kind of go into astronomy side of things was the third year project I did with Tom, which was actually the very start of this project was known as the hidden aurora of Uranus, and I worked along with some colleagues trying to find evidence for the aurora in the data that I've been working on for the last year, and that's kind of got me off into this area. So I guess now, yeah, I it feels weird saying it that I am an astronomer. I am. I've worked with telescopes. Still doesn't feel very real. I hope that's answered the question. Feel free to keep pointing stuff my way. If you have any more, I'm having a look now at YouTube if we're okay to head over there. I'm seeing, so I'm just scrolling through comments.
There are a lot of questions on YouTube, and I'm just answering some and also trying to pull them out for you. So would you want me, do you want me to handle that, or it's up to you?
You can feel free to pull out. I will promise I can't. I don't know if I'm going to be able to answer everything correctly.
I think I'm going to paste them into a document just because some of them are really good general questions, and then I'll feed them to you in the chat. How's that?
Yeah. I've just spotted there's a couple things. I did see one saying, never mind Uranus, let's have a look at the cat. I promise you she's going to be about. She'll probably continue to mutter away.
See, we talked about this. We talked about how popular cats are. Astro cats. We should have set up that cat cam.
I don't think she would have been very pleased, unfortunately. She's a very picky cat. I will see if I can say hello, but I've got to make sure that she's not going to jump. Hi. Yeah, you're not best pleased that I've disturbed you whilst you're looking at something else.
Very intently as well.
Yeah, well, I said she's going to be 17 next month. So she's a very, very old cat. Had her since I was 11, I want to say. No, possibly even younger than that, 10 or so. So she's been in the family for a while, but yeah, unfortunately, it's only been recently that I am now her owner. So I've been learning on top of this year how to be a proper cat owner rather than being a kid going, oh, a cat. It's okay. I promise, Mum and Dad, I'm going to feed her every day, and then, forget. I say forget. I did my best, I'd like to say in my defense, on remembering. But there's only so many times when you're going to school that you could feed the cat in. I've noticed we have some more questions in Zoom. If it's okay if I take those on, or should we?
Absolutely. We have about 10 minutes or so before we start to think about the school joining us. So you go for it.
Okay. So we have, why is Uranus always blue? From an anonymous attendee. So, oh goodness, I already pressed on. Sorry, apologies on that. So Uranus, if I remember correctly, is the atmosphere, and that's because of the amount of methane, if I recall correctly. I don't know exactly why it would be that it would reflect back blue, but I presume it's due to the composition of the molecule that it causes the light, or every other light, to be absorbed and only the blue light to be reflected back at us. But that is more of a atmosphere question, which we do. Obviously, our work is with the upper atmosphere, but unfortunately, we mostly focus on the hydrogen side rather than the methane side. But I wouldn't be surprised if NASA would have more discussion, or at least kind of more sources that you could directly have a look at online if you would like to know further on exactly why it's the hue that it is. We have one for everyone on the host, which is what is your favorite planet? Everyone, including Lucinda, and why is it Saturn? Is another. It's the end of that. So yes, I guess I'll start with mine. Yeah, I'm going to be very biased. I would say it's going to be with Uranus and Neptune, simply for the fact that we just don't know that much about them, and they get so ignored with missions. You wouldn't believe it, but as we were saying before, Voyager 2 is pretty much the only one that's gone past both of them to take any data, and that's been well, it's going to come up to 40 years in the next 5. So it's been almost half a lifetime for someone that we last went to Uranus and Neptune. So I feel like they get ignored a lot. I understand why, discussing with colleagues, a lot of them go, well, you know, Uranus and Neptune are oddities. We don't need to know the oddities when we're still trying to understand how space physics works in general. It's best that we get the foundation before we start looking at the extremes. But I'd like to counter that, almost going, well, it's nice if you've got a foundation, but if the extremes help you understand the foundation, then it's not much worth getting that foundation if it's going to get blown out the water by the extremes. I guess I open up to Henrik. What's your favorite planet then?
It's a great question. It's like picking your favorite child, isn't it?
Yeah.
There's no kind answer, but yeah, I think for me it is Saturn. You know, I worked on the Cassini project, the mission to Saturn, for a number of years, and it's just partly because it's a stunning planet with really funky moons, and yeah, it's also working on the Cassini project. It's such a great community, and that sort of colors my view of the planet as well. I think, yeah, a lot of good times. And you know, there's going to send there's a mission called Dragonfly, I think, that's going to go to Titan, like a hovercraft, like a quadcopter, I think they call it, fly on Titan. So we are going back to the Saturn system as well. So I think, yeah, looking forward to that.
Do I get to weigh in?
Yeah, no, you were included in this. Go for it.
I also have a visitor. He just said, this is Kepler, my cat, and he just decided to come and have a visit. I'm going to put him down.
That's a great name.
two cats, Kepler, Hubble and Kepler. So
Awesome.
You can name your cats after astronomy figures too, and telescopes. Mine is Mars. I know I'm as executive director of the Mars Society. Of course, I want humans to go to a planet, and I love Earth, of course, but Mars is very geologically interesting. I mean, all planets are. They're so amazing, and I'm so excited that we're looking at gas giants today. And I do, even though I love Mars, you know, I want to know more about the solar system, and I'm so surprised that the observations of the gas giants, we haven't done enough of them. And I know it takes a long time to get out there. So Mars has been getting a lot of attention, but I think it's time, you know, that we understand how important it is to know more about all of our solar system. So great. And we've got Miss Calhoun's, and apologies if I'm pronouncing that surname wrong, Callan, maybe Miss Callan. She's setting up her camera, I think. So she's with us, and so she's ready to go. Thank you so much for being with us. We'll visit her in about 8 minutes. So you guys have 8 minutes. I don't know if more questions have come into the queue.
We had another one, I believe. From another anonymous attendee, I just wanted to confirm if the Uranus cam is an ultraviolet camera, which displays ultraviolet map of the image, or something else. Apologies on this. So we tend to like to use the red to purple coloration on our images. It's more than pride, just because we work in the infrared, that we try and use something that's in those colors, but it's not actually an ultraviolet camera. I think the image is in the K spectrum.
This is J, which is
J,
1 microns, basically. Fair.
So we're still in the infrared, but we use a violet color. So apologies, it is a little bit confusing. Yeah. But no, this is an infrared look at Uranus rather than ultraviolet look.
We're only picking this color because it's pretty, right?
Yeah, essentially. It's pretty, and we've always done it. Yeah. So tradition. I was just going to quickly comment. I spotted a couple of good questions on YouTube. I will probably just take 2 more before we then start thinking about handing over. So from John Murrell, we had, what is the orientation of Uranus in the image, i.e. where are the poles and the equator? So in the Uranus cam, we currently have the slit lined up with the North Pole and the South Pole rotational poles rather than the magnetic poles. So what we're looking at, so well, I forgot my orientation, so the North Pole may be on the right or it may be on the left. And again, this is probably something that we'll discuss later on in the either today or in the next coming days, depending on talks wise. I wouldn't be surprised if we're not going to have it today. The North Pole and the South Pole at Uranus has its own debate. Back in Voyager, we used the ULS orientation for a lot of the results. So that meant that the North Pole is actually facing, or the North Pole is tilted by 98 degrees or more than 90 degrees basically, and essentially is almost pointing south, whilst the South Pole is up in the north, where you'd expect the North Pole. However, the Institute for Astronomical Units, I think, or basically the big people, the big folks, didn't quite like that because it didn't line up with how the rest of the solar system works, where basically all the planets' north poles point north. If we look at the Sun-Earth plane, so that says the planets go out, so you have the Sun, Mercury, Venus going out that way. They want all of the north poles for each planet to basically point that way and all the south poles to go that way. So IAU have the other definition where essentially the pole that is facing downwards is now the South Pole and the pole facing upwards is the North Pole. So it can get very confusing in the field when somebody says, oh, I've looked at Uranus's North Pole, because you'll have to ask them, oh, do you mean IAU or do you mean ULS? If they're doing observations, a lot of people like using ULS because that's been done in the past and it makes it easier rather than having to invert everything every time. But if you're talking in terms of like a mission or strategizing on stuff, you usually have to use IAU, so it can get very confusing very quick. I hope that's answered that question. We also then have, are there any missions planned to explore the moons? To my knowledge, there are not any that have been, I say accepted, but in the sense of like are on their way or are being in motion. Tom, who will be coming along shortly, was part of the team that was trying to send a mission to Triton. 97.7 degrees, sorry for the rotation. Thank you very much, James. Tom Stallard was part of the team for Trident, which was to send a mission to Triton and to Neptune to have a look at the moon there, if I'm remembering correctly. But unfortunately, that hasn't managed to make its way through, but we're hoping perhaps that will keep the door open for more missions to have a look at these interesting moons, because yes, we do have moons, obviously, in our solar system that we can look at ourselves, but I think it would be really interesting to see what happens to the moons, especially so far away from the sun, and into the further realms of our solar system. I think we are nearly coming up to our first section for today, which is with the first class that we have. I will do a very quick roundup of what we're seeing. So very nice, as we're getting lots of comments from the HD Plus team. At the moment, we're getting very lovely HD Plus spectra coming in, which is a relief for myself. I'm not going to lie. I'm going to bring in my mouse here. So that's the Q1 line, which is now beginning to see a lot brighter. I'm getting a little bit hopeful, but that's probably getting a bit too hopeful. We're seeing kind of a slight brightening on one edge, but that might just be the noise at the moment. So I've got to hold my breath. And we're starting to see the Q3 line come in, which we're now been running for about an hour. So that's a positive for me. Hopefully the next half an hour, we'll start seeing more defined lines. And that's my roundup. I believe we can now start looking to go towards the Q&A with the school. I will clarify, we will be coming back to questions with YouTube and with Zoom. Thank you for your patience with this. Please do feel free to send those in, but for the next half an hour, we're going to be prioritizing the questions from our first class.
Thank you. Thanks all for that, Emma and Henrik. Yeah, let me get our classroom up. Miss Kellen, if you are able to turn on your, I'm going to ask you to start your video. I have a feeling you might have had difficulty with that. So I've enabled your video to start. I'll ask her again, ask her to unmute maybe as well. So we have our own technical difficulties here on Zoom. I know.
May have to
She might be
have the
getting
same
her
issue with Teams where you'll have to have the participant.
no Teams.
The
So
children are just coming in
just
from play,
play,
so
yeah,
we'll be
so
with you
the-
shortly.
exactly.
Okay, no worries. I can
Thanks,
take another
Emma.
question.
Okay, no, I think it'll be okay. So yes, so as Emma said, the children are just coming in from play. Will be with us. She'll be with us shortly. I'm trying to get this up on Spotlight here, but I'm having not having a good time trying to figure out Spotlight because I'd like to make sure they get up on the screen. I'm not sure. Henrik, I see your message, but I'm not sure who that's for. So I'm just
That's for me.
okay.
Okay.
Let me see if I can spotlight you guys. Do I have a spotlight on someone? I can spotlight you. I can spotlight Henrik. But for some reason, I can't spotlight Miss Calhoun's class. I just love to make sure we know she is there since she's got her, she's just sent us a message in chat. Perhaps she needs to have her video on in order for me to spotlight. And it's probably difficult when you're trying to get your class in. Oh, lovely.
I'll change the view for the moment for a slight bit of
Lovely on your panels.
distraction.
I'll spotlight that for a little bit because that's gorgeous.
I can discuss this a little bit. This is basically a little collage of the view from last night. These are all the gifts that we have, basically a good couple of hours at Mauna Kea. So we're seeing, I think Gemini is the north view and the west view. I think we may have IRTF in the lower panel, lower left panel, more towards the middle. But I thought it was a good way to kind of demonstrate how it all kind of works on Mauna Kea in the sense of how busy it can end up being, as well as the local town that you're seeing in the bottom right in Helio. Just seeing how it's quite mesmerizing, to be honest. It's quite mesmerizing seeing all the traffic and all the lights come on. But I'm not gonna lie, it's also kind of crazy to see the north view because all the lights that you're seeing zipping through almost like bugs are airplanes and kind of elements that are just flying in the air with their lights on, but they just zip by so quickly. But yeah, I thought it would be nice to kind of show this panel as well, just to see kind of, yeah, that one day, hopefully myself and a good couple of the others, and the 80+ team will be able to make our way back over to Hawaii to take in-person observations. Yeah, it was something that I was really looking forward to with the whole yeah,
They're
we've got a lot
here.
of kids. They're here.
Yeah, so and I do, it is like when you have the camera. Here we go.
Hello.
Hello. Is Miss Callan there?
Yes, I'm here. Hello.
Hello. Thank you so much for being with us. Can you? Hi. And is this the Garris School? Is that how you pronounce that?
Yes, Garris Primary.
Garris Primary. Welcome to joining us with the Royal Astronomical Society and Emma Thomas, astronomer from Leicester University, as well as Dr. Henrik Mellon, a planetary scientist also from Leicester University. So I think, Emma, you are going to have a chat with the students and maybe show them some information about Uranus. Is that correct?
I'll do my best. Yeah. Yeah, no, I'm very happy to discuss them. I will do my best to bring up pictures. Bear with me if it may take a little bit.
That's okay. While you're doing that, I'll let the students know what we're doing is we're doing a live remote observation from Mauna Kea. And I was going to pull up an image of that. Let me just, there we go. Let's see, actually, if I can go back. So this is where we're observing from today. This is atop Mauna Kea in Hawaii, and we're using this telescope called the infrared telescope facility there. And we're looking at it in a different wavelength of light. Let's see. Henrik, maybe there's something that you could tell us a bit more about Mauna Kea, perhaps?
Yeah, sure. It's basically a massive volcano which sort of shot up from the ocean floor and then started peaking up above the ocean. And it's now dormant, so not quite extinct. So it's not going to go off like at any time soon. So it's 4,000 meters high, which is really high. So from that sort of altitude, you get really clear skies, and that's why we build telescopes on big mountains. You want to be above the clouds. In that picture, you can actually see the clouds, can't you? So the telescope is above the clouds, and so you get really good views of the stars and the planets. And it's in Hawaii, which is tropical. So below the clouds, it's like really nice and warm. Like you get beaches and stuff like that. But when you go up to the telescopes, you get freezing temperatures. So you have to wear like massive jackets, hats, and gloves. Otherwise, it's just too cold. And it gets really windy as well, which is why you sit inside with a nice cup of tea or something. Yeah, it's a beautiful, beautiful place. You can see on this image as well, there's an island, like just beyond the telescope. There's like a little thing sticking up on the horizon. And that's another mountain. And that mountain also has telescopes on it. It's called Haleakala, which is sort of Hawaiian. And that's on another island. So lots of astronomy in Hawaii because they're really high mountains. And yeah, it's a cool place to go.
Thank you so much for that, Dr. Mellon. How's it going, Emma?
It's okay. Well, I've got some bits and bobs, but again, it's all right. It's gonna be technical. It's gonna be fun. It's gonna be interesting.
You are juggling so many things. We're all juggling. Yeah, it is difficult to kind of get back into the swing of this, figure everything out. So we appreciate your patience.
Sorry, I said worst case is I'll bring up some pictures if I can on this. So this is my main video screen. So I may have to dart out from being on screen and share my screen instead. But I will hopefully give a heads up. But otherwise, I should be ready to go.
Okay, great. I can see your panel.
Awesome.
Yeah.
Sorry. Light. There we go. Perfect. So yeah, ready to go. I don't know how we want to do this. If we have any questions in the classroom, I should say hi again. Welcome to me and my cat. She's in the background. I'm afraid we can't hear anything from the classroom just at this moment.
Yeah, I do see hands up.
Right, hands up, boy. Who has a question they'd like to ask?
Oh, wow, that's a lot of hands.
Give me 1 second. Can I have Iris, please? Read it out voice.
Can you see every planet?
Oh, that's a good question. Can we see every planet? I suppose I should ask, do you mean can we see every planet today, or are we able to see every planet with a telescope?
Like, are you be able to see every planet in the solar system?
Sorry, I think he said, can you see every planet in the solar system on the telescope?
Okay. Well, apart from on Earth, because that one's a bit of a difficult one to look back into the planet. But we use satellites to look at Earth rather than telescopes. We usually use those and they orbit around Earth to take lots of good pictures. But otherwise, that's a good question. I know with our work, we look at Jupiter, we look at Saturn, Uranus, and Neptune. So that's four out of the 8 or 9 planets, depending if you want to include Pluto or not, because obviously that's its own debate. I would be surprised. I'm fairly certain we do have telescopes with Mercury, but I think that one's a bit hesitantly because obviously Mercury, because it's the closest to the sun, will be in front of the sun for parts of, so I would imagine that has its own difficulties. But unfortunately, I don't look at Mercury that much. I do have a colleague who does look at Mercury, but they look at the rock samples or how they would expect Mercury's surface to be. And otherwise, yeah, I would imagine there's probably observations with Mars, but we don't take any infrared observations at Mars because the magnetic field at Mars is very different to that of Uranus.
Thank you. Emma, do you mind quickly explaining? Because I've actually pinned the telescope images. Could you just explain those a little bit to 4A, please?
Yeah, no worries, no worries. Okay, so what's going on in the live stream I've got here? I'll see if I can. There we go. There's my mouse. So here in the left-hand side, we have our Uranus camera. Basically, the very bright ball of light we see in the middle is Uranus. So we're actually looking at the planet itself. And around it, the green box. So we have one of the moons that is Umbriel, if I remember correctly from what Henrik said earlier, and we have Ariel that is next to it. Henrik's probably going to tell me it's the way around. I tried. I think over here-ish, although it's much, much fainter now, we did have Miranda, and that was pretty close. But we'll keep an eye out for that. But this is what we are observing at with Uranus. The black line that we're seeing in the middle is what we use to take our data. So basically we have a line across the planet, and any light that's coming in, we then basically will put onto our spectra, which I will move over. So here's my mouse again. Our spectrocam is basically, we have wavelength along the bottom here on several lines, and basically that's with increasing numbers. So we're looking at about 3 going up to 4-ish or so on the spectrocam. Yep, I will be doing that, Tom. Sorry, I'm getting messages on there. Sorry, we'll be getting to this. What is useful here is basically we have that slit. We basically will keep copying and pasting it at different wavelengths to produce these very long stretchy lines. And what we're very interested in, and I'll see if I can move it to the other, no.
Wow.
There we go. So that's the closer view. So you see, in fact, I think I have my other one. No, that's not the correct one. Sorry. Again, technical views. But yes, we have the spectrocam here. So we have our 2 lines at the moment that we're very interested in. You can just see them. They're very, very faint. But the bright line and the dark line are basically 2 copies of Uranus, or the light that we're getting. The reason we have one yellow line and one black line and one purple line is because we're taking pictures of Uranus at 2 points on the slit. So basically bouncing back and forth on our line. And because we end up with 2 pictures, one with Uranus on the left side of the line and one on Uranus on the right side of the line, and then we basically minus one from the other, so basically take it away, we end up with one dark line, and that's like a negative number, and the yellow line or the bright line is the positive number that we get from it. And if I go back to my original one, we then have very finally, we have the inside the IRTF. This is basically a GIF, or like a loop of the 8 hours from the previous night, last night, of inside the telescope. So you actually see how the telescope is moving and taking observations from inside. Whilst to the very right, we have the sky above IRTF. This is from last night. Basically, it's a camera that is pointing straight up into the sky, technically at the Gemini telescope, which is on around the same area as that of IRTF, but it's a time lapse of basically the night sky from the previous night.
Thank you, Emma. 4A, any more questions? Do you have another question? Yeah.
How long did it take you to build the big telescope?
Oh, wow. These are some really good questions. So I should probably stress, I didn't make the telescope myself. I just work on parts of it. But that is a very good question, because the telescope, I may have to pass to Henrik on this one because I don't know the history that well, but the instruments on the telescope, it's intriguing because the telescope is made with an original set of instruments. What I mean by instruments are basically You know, like you can use a thermometer or you can use a stopwatch. That's what we call instruments with telescopes. In this case, we used to have an instrument called seashell. And that's basically the prior version to that of iShell, and that's much, much older than that of iShell. However, iShell has only been around since 2016, I believe. So it's about 5-6 years old. So it's actually not that old in comparison to some of the telescopes that have been around. But I will pass to Henrik for the exact idea of IRTF.
Yeah, well, the IRTF was built in 1979. Well, it was opened in 1979. I think it took a couple of years to build. So yeah, it's an old telescope. Like Emma said, though, it gets upgraded every so often with new fancy instruments that do new things. So it's a great telescope, and it's a big telescope too. Its mirror is 3 meters long. you know, really, really big. Yeah, so you can see really faint things with a big mirror. That's why they make them so large.
Thank you. Harry?
Can you see that like Sun 6 or 8 or other black holes using the telescope?
Did you catch that?
I'm afraid I didn't quite catch that. I did hear there was something about the telescope. I'll apologize.
Go louder.
Could you see Sun 618 and other black holes using the telescope?
Oh, okay. So can we see exoplanets and black holes with the telescopes? Okay, that's a good question. So I do have colleagues who look at black holes, look for evidence of black holes, as well as with exoplanets. That one's a difficult question. I'm not going to lie. That's a very good question. It's a very difficult question. It is difficult to observe or look specifically at a black hole. I don't know how much you guys know of black holes, but the main thing with black holes is that they suck in everything, including light. Although I know in that field there's a lot of discussion in terms of Hawking radiation and bits and bobs from there. But again, that's outside my field, so I'll apologize, I don't know too much. So usually they look for the evidence that there is no light somewhere, or that there are things orbiting around black holes to kind of give evidence that you're seeing one in that area. For exoplanets, it's similar in a way. They look to see if, to my knowledge, again, this may get overwritten by somebody else, but they look for stars. So they look for stars that they think are at the middle of such, solar systems, like other solar systems and our planets. And they'll look to see if there's evidence of wobbling with the star. And the reason they're looking for that wobbling is because everything in our solar system has its own gravitational force on the objects around it. So if they can see evidence that the sun itself is wobbling, they can usually have a good indicator that there is something with enough gravitational force that it's called like pulling and pushing away on the planet itself to hopefully be able to observe exoplanets. But I don't know if you can directly observe exoplanets, unfortunately. That's outside my field, but I'm sure we will probably have someone coming up in the next couple of days who may be able to go, oh yes, here it is. Or maybe able to even say, no, we haven't yet, and that's the next thing.
Thank you. Questions? Eileen, please. Are we really loud? She said, how do you use the SpectraCam?
How do we use the SpectraCam? Okay, I'm guessing that's how do we use it for our work? Yeah. Okay, cool. So from this SpectraCam, we will usually, sorry, I haven't fixed it, sorry. From the SpectraCam, we will, I've got my mouse here, we'll basically take a line straight through to produce like a line graph. I'll see if I can get a pretty picture of this up. I did make one yesterday. Give me 2 seconds whilst I find it. But put it somewhere about here. So this is a good question, and I would like to try and get a good image for it. I just need to make sure I've grabbed the right one. Yeah, there we go. So we'll have this image come up, I think, on Sunday as well. I'm just going to share my screen just as a heads up with Cinda. There we go.
No problem.
There we go. So this is like one of the lines that you take straight through one of these lit up ones rather than these darker patches in our spectra. And everything that I've put with a green circle is essentially peak points where we're seeing these emission lines come from Uranus. So that's basically specific wavelengths of light that Uranus will say, hi, I'm doing something, have a look at here. But it can end up being pretty noisy. So we usually have to go through what's known as data reduction. The nice and simple thing is basically we have to go along with a lot of cleaning products, a lot of coding cleaning products, and try and make it look better so that we can start getting out signal to noise or enhanced signal to noise from our data, or be able to get something out of our data, which are these kind of big points. When we zoom into these big points, we actually get what are known as curves. And from those curves, that's where we get our data, that's where we get our numbers from. And we do a lot of comparisons with the numbers that we get from them, as well as testing what we would expect versus what we get from the data to get ideas such as what the temperature is in the atmosphere, as well as what the amount of molecules in the atmosphere is at that time.
So Emma, you get a whole bunch of stuff and then you strain it in some ways to get the things you actually want?
Yes. So we will normally get about 10 strips or about 10 strips worth of data from the spectra that we're seeing. If I unshare, stop sharing, there we go. So what we're seeing in the spectra, we're seeing only about 1, 2, 3, about 4, 5-ish strips of data or spectra that we get through from IRTF, and we will basically take those strips, clean those up, make them into 10 very nice strips of data, and we'll go through each one to try and see where these peaks are, which is where we get our data from.
Thank you. Any questions for Emma? Shiv.
How did Uranus get its name?
Oh.
Apologies. I got a name, but that was as far as I got. So.
Shiv said, how did Uranus get its name?
Oh, that's a good question. This reminds me why last night I was thinking I needed to do my research. Well, I know originally Uranus was called the King's Star, if I remember correctly, when William Herschel first saw the star, but I don't remember exactly what the specific name. I just know that it was translated to the King's Star.
I also heard that it was originally named George.
Yes.
And then I wish it was still named George. I wish we had a planet George in the solar system. You know, let's see. Mercury, Venus, Earth, Mars, Jupiter, George. So, did I do that in the right order? Saturn, did I miss that? Saturn, George, and then Neptune. So maybe I should start calling it George from now on, just to start a new naming campaign. But I thought it was related to, is it Zeus? Uranus, I thought was related to.
Yes, I was going to say, I would imagine it's probably in line with the rest of the other planets that are named after Greek and Roman gods. That it was probably to bring it in line, that they went with Uranus.
Someone in the chat said that Uranus was Zeus's grandfather.
Ah, there we go. I wonder, I don't know that I got the planets in order, Miss Callan. Does your class know the order of the planets from the sun?
Do we know the order of the planets from the sun?
Yeah.
Does somebody want to try? Pressure? Somebody wants to try? Abney, you want to try in order?
So from the sun is first Mercury,
Good.
Venus, Earth, Mars, Jupiter, and then Saturn, and then Uranus, and then Neptune.
Oh, well done. And thank you so much. You helped me because I think I skipped Saturn there. So thank you so much for helping me remember the order of the planets from the sun. Well done. Good job.
Oh yes, Emma. Yes, we weren't really sure what a spectra is. If you don't mind.
Yes.
Thank you.
Sorry, I'm very sorry for not clarifying on that. So spectra, this is a good question because I'm trying to, because I've been working on it for so long in my head, I'm like, spectra is a spectra, which is not helpful at all. So what I mean by spectra is it is essentially the light that we get in from a planet. I think the best way I could kind of describe it is, have you guys had like a prism or like a piece of glass in front of light and been able to see it change into a rainbow?
Yeah, we've seen
Yeah, awesome. Well, when a glass or when a prism changes light into a rainbow, it is actually causing the wavelength that you saw light coming in at to diffract. That's the fancy word, but it basically causes the light to spread out into multiple colors. And that is kind of what we're doing here with spectra, where we're taking in the light that's coming from Uranus. So that's the single wavelength or the single bit of light that's traveling through, and we're spreading it out over lots and lots and lots of colors. So imagine you have the color, like the amount of colors that we have within a rainbow, and then add on, I could only imagine like thousands more colors, but but unfortunately our eyes can't see an infrared nor an ultraviolet, so we'd only be able to see the rainbow part of it, but the stuff that we're seeing is in the infrared, and if we could see it, I'm sure it'd be very, very magical indeed. But instead here, to give us a better idea, we have with the SpectraCam, we've done basically an artificial coloring so that we can actually see what these bits of color look like. So in fact, we can start seeing what it would look like with the infrared side of things with the rainbow as well. But I hope that's answered it. I'll apologize on that. It's been a while since I've done any kind of discussions with telescopes and whatnot. So if I haven't made it clear, just let me know.
Thank you. I'm going to be cheeky for you. I'm going to squeeze a question in quickly. So at the moment, we're learning about sound, and we're talking about sounds and waves and vibrations. I know this one might be a bit of a broad one, but what could you tell us about sound and space? Sound and space. Interesting. That's a very good question. I'm pretty stumped on that one, if I'm gonna be honest.
Is this like when you watch a Star Wars film? You can hear all these big explosions, and then physicists go, "You're in space. You can't hear explosions."
Yeah, exactly. Well, I mean, when it comes to those things, the big thing that everyone always will come back with is, oh, well, there's no atmosphere, there's no molecules in space. So how is it that a sound wave can, move in space? But it's, I don't know, I don't want to full stop say, no, you can't hear anything in space, because I feel like there may have been some special topics. Here at the University of Leicester, we get the fourth years to in depth with a model known as special physics topics, where they'll bring up their own discussions on topics. I wouldn't be surprised if somebody in the past has gone, okay, can you hear things in space? How much can you hear in space? So I would definitely have a look. I think those are available in the university's journal.
Yeah,
and there are a lot of good topics that are being brought up.
I don't know if Hendrik is going to chime in, but
I was gonna say that you think about the giant planets, and they're actually quite loud places. If you were to go into the atmosphere of a giant planet, you'd hear the roaring of these giant storms, like the Great Red Spot on Jupiter, for example, is the largest storm in our solar system. Is larger than the Earth, and the twirling in the atmosphere generates an enormous roar. So if you're in the atmosphere of Jupiter, it'd be very loud. In addition to that, you have thunder and lightning going off in the distance around you. So yeah, the sound certainly, and a lot of it on the giant planets.
Oh, thank you very much. That's really interesting. Thank you. More questions? Yeah. Oh, loads. Ashir, please.
Does Uranus have creatures living on it?
Okay. Did you catch?
So does Uranus have creatures living on it?
Yeah, that was it.
Oh, excellent. No, that's a really cool question. At the moment, I don't think we have any papers that have told us that we've detected life at Uranus. I mean, one of the things that I think we're going to imagine here is if there were going to be aliens, they're probably going to be very different than the aliens that we usually see coming from Mars in science fiction. Mainly because Uranus itself is actually pretty much made of gas. So there wouldn't really be anywhere to stand on for them. But it would be interesting. We might even see very, very small microbial life. And what I mean by stuff like that is thing like life underneath a microscope. Anything that's like that we might see, but it would have to be very resistant to the cold because it's very chilly. And they'd have to be okay with not too much sunlight because Uranus actually takes it rotates every 17 hours, but because of how Uranus is orientated, I'll see if I can get a fun picture. So I'm going to share my screen again. I'm going to use one of James. Yeah, there we go. One of James's. Actually, no, I don't know if that's the best one to use. Apologies on this. Bear with me. Nice, there we go. Which one's going to be the best one here? I don't know if any of them would give you that helpful. No offense to James on this, I do have them. I just don't know if it's going to show my point very well. So apologies, I'm going to stay with what I have. But because when Uranus is rotating around the sun, one pole, so imagine if you lived in the Antarctic, let's say, on Earth, one pole will be in the sun for about 21 years non-stop. So imagine you were just stuck in sunlight for 21 years straight. And then as we rotate by about half a cycle or half a rotation around the sun at Uranus, that's about 42 years, you would then be stuck for about you'd be then stuck in permanent night for 21 years. So if you were life, you'd need to be very happy about being in the dark for a while and being permanently in the sun and have a lot of suntan lotion, I can imagine.
Thank you. So very different to Earth for you. We were just learning about Earth and its poles and geography a few weeks ago. So that's a really interesting one. So planet Uranus gets, what was it, 21
years of sunlight at one pole, and then half a rotation around the sun, and then it's another 21 years in the dark.
Imagine on Earth, 21 years of darkness or 21 years of sunlight. Do we have another question? We've got lots of questions here for you. Isha, please.
How was Uranus born?
Oh goodness, how is Uranus born or created? Yeah. Okay. That's a good question. I actually don't know the answer to that one. That's not to say there isn't an answer. I know James has given me a simulation, but I don't know the full context. I'm trying to think if somebody on our panel is going to tell us, or at least I would imagine perhaps one of our speakers later will be able to kind of mention the creation of Uranus and probably Neptune as well, because how they are finally formed is kind of the key knowledge of why they're so funky in comparison to that of Earth. So that is a good question. I hope you'll stay around or at least be able to look at the video later if hopefully one of our speakers will be able to cover that later.
I wonder if either of you know, as scientists, do we ever really know? We're always learning new things and there's always new theories coming up about how things form. We have a general theory for the formation of the planets. But I think as we're looking at being able to observe planets around other stars and get more information about planet formation, we realize that maybe our theories are different from what we thought. I don't know. Henrik, do you have anything to add to that?
Yeah, I'll admit to not knowing a lot about this either. But I think Uranus formed out of the same sort of disk of dust that the Earth was formed from. So we have the similar building blocks on Earth as we do on Uranus, at least initially in the early solar system. someone else knows more about this than me, but it's fundamental. Understanding how the solar system formed will make us understand how other planetary systems forms. So yeah.
Okay, thank you.
All right, I'm just switching between cameras here, so apologies. There's going to be a slight bit. There we go. I've done a quick job. Sorry.
I love how your students have so many questions. I love curious minds. I think it's fantastic that so many hands are up. Who's next?
Okay. On Uranus, is there water or trees?
Oh goodness. Okay. Did I hear that correctly? Is there any water or trees on Uranus? Or
Yeah, that's it.
okay. That is a good question. To my knowledge, we haven't seen any trees on Uranus at this moment. That would be really cool if we did see an atmosphere tree. It would lead to a lot of science questions. I'm not going to lie. There'd be a lot of papers. Perhaps that's their next research project. Water is a difficult question. I don't recollect seeing anything because our main focus with water is looking for places where we would expect to see life. But we have seen evidence with, I believe, with our moon, I think. Don't quote me on that. But definitely seen it at Mars. There's been a lot of the interest lately. So perhaps that's something that we could look at with Uranus. But I think it's that is up in the air. I can't confirm or deny. Oh, I'm sorry. Was that a question?
Our teacher's outside. Yeah.
Oh, okay. Oh dear. I'm afraid I won't be able to pick out people just because I've only got a very small camera, so I have to wait a bit. I'm trying to think. Henry, do you have anything to add to there being water at Uranus?
Well, like you said, there could be water on a moon.
Mm-hmm.
So Uranus has how many moons? 47?
Yeah.
A lot of moons. And we do see water on moons around the giant planets. Of course, if we're going to see trees on these moons, we also need an atmosphere like we do on Earth. And these moons don't really have an atmosphere. So we're not expecting trees at Uranus. That would be cool, though.
Definitely. I agree.
Can I choose someone? Can I choose someone if I can see them?
Yeah.
Yeah.
There's hello, hi, I'm Lucinda Offer from the Royal Astronomical Society. Let's see, I see someone way in the back over there next to the window with their hand up.
Has anyone stepped on Uranus before?
Oh, interesting. Has anyone actually gone and walked on Uranus? Well, we haven't had anyone go that far. We're certainly looking at sending astronauts to Mars. That's the key bit that we're looking at the moment. I'm sure you guys have seen there's been lots and lots of movies and people, I say lots of people, been some people that have gone to the moon, but I'm afraid we haven't made it to Uranus at the moment. I think the next step is first we'll go for Mars, and then we'll go from then onwards. I don't know if you have more to add for that, Lucinda.
I would say that definitely no humans yet to Uranus. It's so far away. It takes a long time just to get an observation, something sent out, a satellite, a probe, whatever, what have you, to get to Uranus. Does either of you know how long it takes to travel a mission to Uranus anyway? I think we had to wait something like 12 years plus or something for it to get that far out into our solar system. What is that? Is that 10 astronomical units or 20 maybe? I think
19
almost 20. So almost 20 astronomical units. So one astronomical unit is the distance from our sun to the Earth, and we had to wait until it traveled 20 of those before it got to Uranus. It's actually only like 6 months to get to Mars or so, 6 to 8 months. So we launch something in August to Mars, and then we get there by January. But to Uranus, it takes a lot longer time. So scientists have to wait before it gets there. And then I don't know how. So if it's how the distances and getting data back from Uranus. From when you send a probe out, and if I'm doing 8 minutes for every astronomical unit, does that work out to 8 times 20? That pretty much it? I don't.
Yeah.
Yeah, matches something similar. Yeah.
Yeah. So no humans are yet to Uranus right now. Scientists want, I would say, more probes, more missions to Uranus and Neptune, and to find out more about those planets, because we're still learning. Even from planets that are close to us. I think we're going to be doing some missions to Mercury or Venus, because there was an announcement of finding the building blocks of life in the clouds of Venus. So it's so exciting. Venus is much warmer because of this dense clouds on top. Now I know we have gases on these ice giants, and actually Dr. Mellon here, he's going to be looking at the temperature of Uranus. So all very interesting, and still so much to know. Really great question. We have about 5 more minutes or so, but does that, I don't know, Henrik, do you want to choose someone? Can you see someone for a hand?
They're really small. Well, front row on the left.
Are they in a yellow t-shirt?
Yeah.
T-shirt front row left. Rittle? Are you Rittle?
Are there any aliens in the space?
Are there aliens in space? Yeah, that's a great question, and a question we don't know the answer to, really. We've not seen aliens yet, but the universe is just so big, isn't it? There's so many planets in the universe. And so we think that maybe some of these millions and millions of planets could be a bit like the Earth. And if a planet is a bit like the Earth, it can probably develop life. So yeah, we don't know, but we think it could be likely. I mean, what do you think? Do you think there's aliens out there?
What do you think, Rittle?
I think.
You think there are? Yeah? Okay. Who else thinks there are? Hands up. Who thinks there's aliens in space? Who thinks there are no aliens in space?
All right.
Oh, wow.
That's interesting. Yeah.
Controversial topic here in our class. Okay.
That's cool. I was going to add to that, if you don't mind, Eric. One of the really cool things with, I believe it's the Voyager missions, is that they brought along messages to anyone that would find the Voyager missions. They put it onto, if I recall correctly, the giant disk. And they basically left a lot of messages from Earth saying, hello, we are here. If you're alien life and you'd like to get in contact, please find us at these coordinates. And they sent lots of very, very, very fascinating pictures. I think you can find them on NASA, basically demonstrating how life and our cultures and how diverse we are, not only as a planet, but also what our understanding is and just the general history of humanity. It's really, really cool. So hopefully alien life might pick that up and send us a text message or a call at some point.
Okay. Have we got time for 1 or 2 more? Is that okay?
I need to check with Lucinda on that one.
Oh, okay. Do you need some help? Yeah, let's see. It is hard to see. You guys are all right. I see. I'm trying to look for different colored shirts, but everyone's like wearing yellows.
Yellow for World Mental Health Day today. So it's
Oh, how
excellent.
wonderful. Well done, everyone. Okay, so there's one kid near the front who's been dying to ask a question. He's got a yellow shirt on with black sleeves. So he's wearing a black shirt underneath his yellow.
Faz, please.
Have you spotted other planets out of our solar system?
Good question.
Fabulous question. I love that. So that is a really good one. That's kind of into what we were discussing before with exoplanets. What we mean by exoplanet is like planets outside of our solar system. There is a very large field of this where there are lots and lots of exoplanets. I couldn't even begin to name them all because there are that many that people have found and looked at. I've just been having to listen to this, over 4,000. Thank you. So that's a lot of numbers to go through for planets. So they are definitely there. It would be great if we could look at all of them and see, because hopefully that's the exciting thing with a lot of the exoplanets, is that they may be the answers of where we can find life in outside of our solar system. So that's where the key interest is with these exoplanets. So yeah, hopefully we'll get to see more in detail. But short answer, yeah, we have seen other planets outside of our solar system.
So we have time for one more question. Miss Callan, do you want to choose someone this time?
Ray, do you want to do it? It's got to be really loud. Off you go.
I'm afraid I only caught the end of that question.
Said, are there clouds on planet Uranus?
Oh, that is a good question. We have one of our speakers, Dr. Lee Fletcher, who will be discussing elements with Uranus and Neptune. But in his Q&A, you could probably ask more because Lee does a lot with the atmospheres at Uranus. I'm afraid myself, I don't know in terms of the clouds themselves at Uranus. I don't know. Henrik, do you have a better idea on that?
Yeah, I mean, there's loads of clouds at Uranus, a bit like the Earth. On a day like today, at least in Leicester, is quite hazy, and Uranus has a lot of haze. If you look at a picture of Uranus, it's like a blue ball, essentially, and that's because there's hazes covering the entire planet. And like Emma said, it's the methane that makes it blue. So there's weather on Uranus, just like we have on Earth, like storms, fog and haze, rain, things like that. So yeah, there's clouds and there's weather on Uranus as well.
Awesome. Thank you very much for that, Henrik.
Excellent. Thank you so much to Miss Callan's class and Garris Primary School. I heard your class 4A. So thank you so much for joining us. I hope you learned a lot today. And again, thank you to Emma and to Henrik as well for answering all your questions. And it was so nice to have you. Thank you, Miss Callan, for being with us today. We appreciate it so much to have your students with us. Raise your hand. How many of you think you might be interested in becoming an astronomer when you grow up? Wow, look at all those astronomers you just made. Emma and Henrik. That's fantastic.
That's great to hear. Thank you. Thank you, everyone.
Okay, well, thank you very much, Miss Callan. Miss Callan, did you have a question? I thought I should ask just in case.
I had the sound question from before.
Right. Okay, well done. Thank you so much. Okay, bye.
Bye, everyone.
Bye. Bye.
Awesome.
Wow, that was amazing. Okay, it is 11:15 or somewhat after that. I don't know if what's on the schedule because I can't see it.
It's just a quick check-in with us before we have our first speaker for the day.
Excellent. Okay, well, back to you two. The work never stops.
Yeah, so I mean, I'm happy to go through what I vaguely think is happening. I apologize because again, I have the talk with the TO and everybody else in the team, but I don't have the actual sound for it, so I'm having to guess a little. But we're getting very good signal now. We're now at, I want to say, just over an hour and a half, hour and 3/4 into observing at Uranus.
Yeah.
So we're now at where we'd start seeing some very decent signal from Uranus, and I think it's a great way to demonstrate if I get my mouse over. So we're back to that Q1 line, Q1 and Q3 line. which is where we get most of our data. If anyone was about, whilst I was discussing with the kids, about the line graph, where we will basically take like a long, I want to say a part of our data, we'll basically take a long line through one of these strips and see where it'll peak up. So our Q1 will basically have like for a dark line here, it will basically have a straight line, it'll go along and then it'll dip down and then back up and then straight-ish line. Obviously with actual data, we end up with a lot of noise and a lot of variation, but that's the rough idea with it. I think though we are starting to see it's more prominent in, again, it's going to be difficult to see on the Zoom because I'm looking at it on my interface, but on what I can see, there's some brightening perhaps on the top of our line here.
I can see it. I have put a spotlight on, so I know on YouTube I see just your panel, and so I can see your arrow and I can see it highlighting a vertical band. The top is purple and the bottom looks yellow orange in that bottom right corner.
Yes, I'm going to see. I think I quickly made this morning. I'll see if I can.
Ooh.
I have a little circle that I can
that's
use.
great.
So if I can do that, I don't know if it's great now because it's red on a purple. So I completely apologize to anyone that has difficulty discerning red from purple. But I'm just highlighting, I think I can see at the moment in the data, there's like a slight brightening. It's like 1 or 2 pixels in this area that's slightly brighter than the rest of the slit itself. And Henrik, you said before the left, was it? The left of the Uranus cam, if I go back to it, is the southern pole.
Yes, so west, which is down on the spectra.
Okay.
Does that make sense?
I think so. So the southern pole is on the bottom? Or
the visible pole should be on the geometry, trying to get everything right in my head. I think the visible pole should be at the bottom.
Okay.
So
yes, okay, I've got you. So the visible pole is on the bottom. So in ULS, that's the southern because the northern has started to move away out of view, if I recall correctly.
Right.
Hopefully.
So what it could be that we're seeing the aurora of Uranus, because there is a big, isn't that right? Sort of close to the limb.
Yes.
Of the northern aurora.
If our attempts of mapping and doing everything else is correct and our theory, then we expect the northern aurora to mostly be on the limb because the North Pole is facing away from us in our observations. I have hopefully a video here, that James sent.
Oh wow.
Yes. Yeah. So we can see here, as we just kind of rotate around, the northern aurora is actually kind of on the limb. That's this kind of area, whilst the much smaller southern aurora at Uranus is more close to the middle of where we see the planet. So if we put like a giant rectangle, I don't know if I have a giant rectangle on hand, unfortunately, to demonstrate this very well. But
I have a question actually about this picture because, I'm used to seeing aurora on the poles, and I have seen another picture of that James posted, another animation where he shows that the magnetic field on Uranus is also in a different orientation than we normally see on planets, and I'm assuming that's why the aurora are where they're at.
Yes, so I think this might be the one that James sent.
Yes, that is it.
Yes, so the darker blue line is the representation of where the magnetic field is aligned to the rotational axis on Uranus, which is in the light blue. Uranus's magnetic field is actually rotated by 59 degrees, if I recall correctly, from that of the rotational axis, which is rotated by 97.7 degrees, as James said earlier. So everything is very out of whack. So it ends up with, rather than what we see like at Earth or at Uranus or at Saturn, where the aurora are pretty close to the top and the bottom of the planet, Uranus, the aurora kind of move pretty much all over the place on the planet itself. So we end up with, well, I said, with aurorae in very unusual places.
Yeah.
Those are great animations.
Yeah.
Thank you to Dr. Donahue, who will be with us, I think, later today, I hope, and definitely tomorrow. He's hosting half of tomorrow, and he does all these great animations, and I'll have a chat with him about all that work that he does, and hopefully you'll join us then.
Yes, hopefully. Well, I'm sure he's going to have a lot of good input on this. We had, what was it, 2 years ago now? Just over 2 years ago, there was the Ice Giants conference where myself and a lot of the other HCA Plus team all came along. The whole idea of that conference actually was to kind of inspire a lot of a discussion into looking at sending orbiters and sending satellites, sending at least something to Uranus and Neptune to kind of get more readings and get better data rather than from what we're having to do.
That brings up another question I have. Like, do we normally just send flybys? Have you crashed anything into Uranus? Do we have anything orbiting Uranus? I don't know that, but I'm sure we've done a flyby at least.
So yeah, this kind of going back to what Henrik, we have had Voyager 2 go by in 1986, which took pretty much the best pictures that we have. I'll see if I can quickly bring up that map. We're getting into the technical stuff a little, so apologies on that. But
my apologies.
No, it's not too technical. I'm just going to be bringing up the paper that we usually refer to when we do Uranus's aurora. I should stress, though, that this is in the ultraviolet spectrum, so it's going to be a little bit different. Well, again, that's its own area. We don't entirely know if the infrared or the ultraviolet aurorae are the same or are different at Uranus. We would expect them to be similar because we do see similarities at both Jupiter and Saturn in terms of how the aurorae look. But even then, in comparison, there are differences between the two wavelengths each planet. So that's a big question with infrared and ultraviolet aurorae at Uranus. Is there a massive difference? Is there no difference? Is it because it's so weird? Is there going to be absolutely, are they going to be completely different from one another? Or is it going to be, two very similar aurorae that we should be kind of expecting here? So I'm just saving the image so I can hopefully grab that. There we go. So it's gonna probably be I'm gonna zoom in. There we go, and I'll share this on the stream properly. There we go. There we go. Hopefully we can see that. Hopefully, just get a confirmation on that.
I can see it.
Awesome. So this is essentially what we, with Uranus aurora, will always refer back to. This is the map of the ultraviolet emissions that we got from the flyby from Voyager 2, and it gives us pretty much the best idea of where we would expect the aurorae on the planet if we're looking at like a 2D map across the surface of the planet itself. This is what we have a lot of the animations and kind of our expectations where we see the aurora. Just trying to think if there's anything to add to this. I mean, it's probably going to be a lot of questions. I'm going to apologize. We're probably going to have a Q&A a little bit later because I know we've got, cannot see the screen in full. What's another question? Okay, I think it's because we've got everybody else up at the moment.
Because you're sharing the screen now.
Am I just sharing my screen now?
Oh yeah,
goodness.
I probably wasn't. I think I've changed views now, so hopefully someone from our Zoom. Was it from Zoom or was it from YouTube?
Zoom, I saw, cannot see the screen in full.
Oh, I see it now. I just changed the view for attendees, so hopefully that worked.
Okay.
Let us know if it didn't. Thank you.
I'll see if I can unpin myself for a little bit, but yes. So, if you are interested in doing any kind of work with Uranus Aurora, or you go kind of into the area, then yeah, this is kind of the defining image that we always refer back to understand if there has been long-term differences, any kind of comparisons. More recently with Laurent Lamley, who has been doing a lot of investigations from Earth similar to us, but within ultraviolet, who has been redetecting the aurorae from Earth to kind of continue those observations, but also to see how the aurora has differed in time. Oh no, sorry. I don't know if you heard that. That's my cat gone to go find my other half to go complain at her that she's not awake, even though she's upstairs trying to avoid being too much in the background.
No, I couldn't hear it very clearly. Not a problem at all.
Oh goodness. I said she may start coming downstairs to yell at me because I'm not where I'm supposed to be in her books. I don't know if we have time for, I guess, a question or two regarding kind of
Well, we have Dr. Sean Prosser just waiting out in the sidelines, so I will
Okay.
Introduce her when you're ready.
Yeah, no, I'm
think we
happy
should-
to go now if you want
Okay,
to.
great. All righty, so let's I will turn on my camera. Hello, everybody. We're back here. I am going to share my screen just to give you an update on where we are in the program right now. Let me do this here. So many different things that we have to do. So many different things that at this time in my life, maybe, or maybe it's what we're dealing with in the world, but brain fog, a lot of that. So so thank you for being with us, just to kind of give you an idea of what we've been up to today. Again, we are on day one of the Weird and Wonderful World of Uranus, this live stream, fantastic, with Emma Thomas and Dr. Henry Mellon today from the University of Leicester. We are observing Uranus from the IRTF atop Mauna Kea, Hawaii, and we have all these wonderful collaborative people with us. And actually, we have Dr. Sean Prosser from the Royal Astronomical Society with us, as well as Charles Draper from the Herschel Society. And the Herschel, he's going to tell us a little bit about the Herschel Museum as well. And so this is where we have done so far from 9 a.m. watching the astronomers set up things. We've had an update on the science, and we've even had a good long time with a classroom in London, which was fantastic. And now at 11:30, we're here with Dr. Sean Prosser, who is our Royal Astronomical Society librarian. Sean, are you there?
I am here.
Excellent, and we can hear you. I'm going to stop sharing my screen, and you're going to be talking to us about kind of the history, the connection of Herschel to the Royal Astronomical Society. And you're sharing your screen. Let me just make sure that turn off some spotlights here, and that you're in full view of everyone. And I'm going to go ahead and turn off my camera. Are you good to go?
I am good to go. Thank you so much.
Thank you for being with us,
Lucinda. Yeah, and I've absolutely loved listening to you and the astronomers talking about the real-time observation work that you've been carrying out this morning. With hundreds of people watching alongside, and now it's my pleasure to take you back a couple of hundred years to some of the earliest observations of Uranus, thanks to an astronomer that you might have heard of called William Herschel. He was born in Germany, and he started out as a musician in a military band, and ended up, due to various circumstances, making a living for himself as a musician and a music teacher in Bath, while also developing an all-consuming interest in astronomy, which motivated him to make some of the finest telescopes in the world at that time, which allowed him to see further and deeper into space than anybody else had been. And that allowed him to make some truly remarkable discoveries, including Uranus. And until his discovery, as far as astronomers and as far as people in the world were concerned, there were 6 planets in the solar system. Now, I must say, I am going to be sharing with you some of the handwritten records from our archives, and much of what I'm going to say is going to be complemented by Charles Draper's later contributions. He'll be taking part just after me, and he's president of the Herschel Society in Bath, and he's actually going to be showing some really fascinating objects from the Herschel Museum, which is the house where William Herschel and his sister Caroline, who I'll also be talking about, but where they lived and where they made many of their discoveries before they moved to Datchet and then a house near Slough, where they could be, you know, easily accessible by King George III, who had made him the king's astronomer, basically, based on William's amazing discoveries. So I have a picture of the library here. I'm going to be showing to you some of the handwritten observations made by William Herschel with an overhead camera. I'm going to go next door into the library to show them to you and just show you some of the, you know, the notable events over the years. And yeah, just to give a really quick introduction to the library itself. The Royal Astronomical Society was founded in 1820, and last year we celebrated our bicentenary. And as well as activities like, you know, publishing astronomers' observations and research, and holding scientific meetings where astronomers and geophysicists can get together and discuss their latest findings, and making awards of gold medals, we've also been collecting printed books and journals and handwritten observations since 1820. We have a really rich historical collection, and I think that the actual the Herschel archives, which the Herschel family so generously donated to us in the 20th century, are the jewel of the crown of that collection. So I am going to walk next door. I will be that'll take about 15 seconds for me to go next door. So Lucinda,
I am here.
I'll hand over to you, and I will be back online in a second. And also, Charles, if you would like to make any comments as well, and if you have any questions as I'm going through the documents, please chip in. Thank you.
Thank you, Sean. Just so she is at the Royal Astronomical Society, which is at Burlington House in Piccadilly, London, and you're seeing here a picture of the library. But what I believe is she's moving from her office to the library, which is on the same floor, and she will be then showing us from another camera. So I'm going to remove the spotlight from her office, and there you go. She's turned off her camera, which is excellent. And she's going to set up another camera, and we'll be hearing from her directly from the library at the Royal Astronomical Society. And she's got some documents she's going to share with us. So William Herschel was our first president of the Royal Astronomical Society. So as you can imagine, we must have a collection of items from the Herschels. So I'm going to spotlight the camera that she is setting up right now to show us that. So how are you doing there, Sean? I can see the ecliptic and also some constellations.
That's right. Can you see? You can see the star atlas, which I have laid out just to give you a bit of context. But this star atlas is going to be it's more significant than just, you know, an example of one of the amazing, you know, publications that we have in the library. First of all, what I'm showing here is an observation of Uranus before we realized it was a planet. This is the star atlas, the Atlas Coelestis of the Astronomer Royal John Flamsteed, who was working at Greenwich at the Royal Observatory in the late 18th century. He was one of the greatest observers of his day, and that's why he had the top job in astronomy. But he was very reticent to publish his results. He wanted to make sure that everything was completely accurate, and this atlas was actually it was published after his death. He also published a star catalogue. Now, that is basically a list showing the coordinates, the positions of stars in the sky, and these have been invaluable references, data used by astronomers over centuries, and that they're getting incredibly complex and detailed now. I mean, but back in the classical era, we'd have Ptolemy's star catalogue that only showed maybe a few dozen stars and constellations, and now we have the data released through the Gaia mission, which is showing millions, if not billions, of stars. I'm sure the astronomers can weigh in on the accuracy of what I'm saying here. But yeah, moving back to the 18th century, we have the constellation Taurus here, and I'm going to point out that these symbols here are basically representing stars in the constellation. You can see the Pleiades constellation here. That these numbers in red ink are, I believe, that they're based on the numbers in Flamsteed's star catalogue, and the star number 34 in this constellation here is on the ecliptic. If I've interpreted this right, this is actually Uranus, and it was just assumed to be a star at that time. It's such a slow moving object. It just took an observer like William Herschel to see that it was behaving differently to the stars around it. So I'm going to tell you something else about this very, very special book. It's actually, who wrote in here? Obviously, it's not very well looked on these days if you write in books which belong to a library, but this belonged to two individuals. Actually, it belonged to Caroline Herschel, and she used it alongside her brother William to help with his observations. And these pencil annotations and red ink annotations were made by her to help him with his work of observing the stars night after night. So I will move back to this item, but just so that everyone knows that William Herschel wasn't necessarily the first person to see Uranus as a celestial object, but he was the first person who used his observation powers and his insights to realize that this object that's behaving differently and looks differently to the stars around it was not a star but a planet. And I'm now going to move on to the actual observations themselves. I'll move this atlas out of the way. So in our archive, which contains, the Royal Astronomical Society's minutes and membership records, we also have these remarkable observations by William Herschel, including this notebook. It's called Observations on the Georgian Planet and its Satellites. So the Georgian Planet, that is what Uranus was known as when it was first spotted. William Herschel had the right to name the new planet, and it was deemed to be politically astute to name it after King George. It was referred to as Georgium Sidus for some time, until in later years it was recognized by the international astronomical community that it's it's not really appropriate to name a planet after one monarch from one country on Earth. So that they decided, actually, it makes more sense to call it after another classical god. So, you know, we have the family tree of Jupiter, who was, I believe, the son of Saturn, and Uranus was the father of Saturn. So it was, I think it was the Johann Elert Bode, the German astronomer, who suggested that alternative name in the 19th century. So here we are, March 13. Sorry, yeah?
Oh, I just wanted to ask you if the orientation that we see is the book on its side, so we don't see it, you know, the top is basically.
How about if I lay it out like this?
Perfect. That's perfect.
Okay, good. Okay, right. So this is March 13th, 1781. And I'm going to read out the top bit of the page, but basically William Herschel is saying in his very good handwriting, looking at a star in the quartile between Auriga's right foot and the left foot of Castor, these are two constellations, I discovered a comet. Now, obviously, at this time, there are many astronomers who are very interested in looking for comets. And if you could see a new object and it looked quite fuzzy, you were going to assume that it was either a comet or a nebula, which at that time was, astronomers only knew that there were, you know, fixed like stars, but there weren't a point of light. There were fuzzy, cloudy objects in the sky. So, of course, William did not immediately leap into thinking this is a planet. So this is March 13th, 1781. And he makes repeated observations night after night. You can see these calculations, these measurements, which he was using a telescope that he'd made himself. And I'm sorry, the shadow, because I've turned this around, the shadow is falling slightly on the page, but you can hopefully still see it quite clearly. The telescope that he had made, Charles Draper is going to talk about it in more detail. And I believe you might actually be able to see a replica of the telescope that he used to make this observation. He's constantly referring to the object that he's discovered as a comet. And all this time, he's also communicating with astronomers. For example, in London, the Royal Society has heard about his discovery of a comet. And there are astronomers on the continent as well, like Laplace, who was a great mathematician and astronomer. And, you know, they can see the behavior of this comet is not like a comet. And it's definitely not a star. And it's being observed that it's a disk. They can see that it's a disk and not a twinkling star, and they can't see the fuzzy tail of a comet here. So here we have April 3rd, 1781. It's just a few weeks later. I saw the comet with a 20-foot reflector. So William Herschel had made a very large and powerful telescope that's 20 feet long in the tube. And basically, it's taking months of measurements, observations, and communications to finally arrive at certainty that this is actually a new planet that's been discovered. Here we have August 29th, 1782. It's the first time that he refers to it in this way. I saw my planet full, as well defined, with 460, I'm not sure what the measurement is, as Jupiter would have been at that altitude with the same power. And the last bookmark that we have here, it's he's by now moved from Bath to Datchet. It's 18 months after the discovery. His life is changed massively because of this discovery. And you can see here the Georgium Sidus, that's the Georgian planet. It's been named, this is how it's being referred to. He's attracted the favour of King George III, and he's now been able to give up his 40 hours a week music tuition and composition and conducting and dedicate himself full-time to astronomy, which is, really valued by the community of astronomers. They've been like, he achieved so much just in his back garden in his very little spare time. What could he achieve if he was able to be paid to work full-time? And of course, he did not work alone. And I'm going to talk to you a bit more about Caroline Herschel. So let's have a look at the atlas again. So many annotations showing the numbers of stars. In the margins, it was frequently written whether something was whether a star was double or triple. So Charles is going to mention Caroline and her background. I'm not going to go into too much detail about her life, but she was basically one of the very young sisters of William Herschel. In that very large family, she was basically, she suffered from smallpox as a very young child, and then she was then struck by typhus, and this had an effect on her physical appearance. And because of her status as the youngest in the family, and because her parents thought that she had low prospects of being married, she was expected to spend her life basically taking care of domestic affairs and supporting her mother in running the house. Thankfully, William Herschel brought her over, asked if she wanted to act as his housekeeper in Bath. And over there, she was able to not just have more independence and run the house with him, but also train as a singer. But meanwhile, I did say, and we can see that William Herschel was becoming increasingly dedicated to astronomy, to the extent that he was making his own telescopes, which were far better than anything that could be acquired from professional instrument makers. And basically, when William was invited to become the king's astronomer, and he moved from Bath to Slough and set up his new large telescopes there. Caroline was transplanted from the social world of Bath, one of the cultural centres of the country, if not the world at that time, to a leaking roofed house in the middle of nowhere. It was really hard for her, but William had already been training her to assist him in his work, and she really came into her own after a year or so. So she's described as his assistant, but the role that she played was just really fundamental. I'm going to read out an eyewitness account by Jean-Hyacinthe de Magallanes from 1785, where he's describing how they worked together. Basically, William Herschel's large 20-foot Newtonian telescope is located in his garden under the sky with a very simple and convenient mounting. A servant standing below turns a crank lever alternatively forwards and backwards until a hammer strikes as soon as the telescope has been raised or lowered by the width of the field of view. And this motion is transmitted by a wire into a neighbouring room, and a hand is turned on a dial whose scale corresponds to the angle of the elevation of the telescope calculated in the table. This sounds incredibly complicated, but it definitely worked for William and Caroline. Next to this instrument stands a pendulum clock adjusted to sidereal time and showing right ascension. And in this room, so William Herschel is outside and Caroline Herschel is inside the house, sits the sister of Mr. Herschel, and she had flamsteed sky maps in front of her. This was actually being used in the course of these observations over the years. When he gives the signal, so that's when he's pulling the wire, she notes in a log the declination and the right ascension. That's another term for showing the coordinates, the location of a star in the sky, and also writes down the other circumstances of the appearance. Right, that's the end of the eyewitness account. But this is what she did. She was working she was his right-hand woman overnight for years and years, carrying out a sweep of the whole sky. So in the last few minutes, I'm now going to talk to you about what Caroline Herschel did in her own time. And these were amazing achievements. I'm going to move this atlas out of the way. Okay, Lucinda, how is this orientation working?
Yeah, that looks great. Thank you.
Okay, good. So Caroline Herschel had, she was given her own telescope to work with, and she was also able to work on William Herschel's telescope if he was out of town. And guess what happened one night when he was in fact out of town? Let's see. It's August 1st, 1786. And she says, I saw the object in the center of figure 1 like a star out of focus while the others were perfectly clear. And the preceding star is very faint, but the weather is hazy. And in a clearer night, undoubtedly, some more will be visible. So this is just a lovely insight into, real-time observations. She can see that the star is fuzzy. She's indicated that in her sketch, and that immediately alerts us to the fact that this might not be a star. It might be a comet, because a comet has a hazy coma and tail, which distinguishes it from other items in the sky. And also she's talking about the hazy weather, and as I'm sure Tom and Emma and Lucinda have been saying this morning, the weather for ground-based astronomy is just fundamentally important and has such a huge impact, and it's always been the case. So a few hours later on the same night, I think the situation is now like in figure 3, but it is so hazy that I could only imagine I saw the second star. But she continues to make observations, and she becomes clear that this is a comet, and this is a great achievement. She's not the first woman to have discovered a comet, but she was one of the first women in England to do this. I believe it was Maria Kircher who discovered a comet the previous century, and she was able to publish this under her brother's name in the top scientific journal of the time, the Proceedings of the Royal Society. And she basically says, my brother was out of town one night, I did some observations and I discovered a comet. And then she provides all the data. And it wasn't just, she discovered at least 5, maybe 8 comets, because sometimes it's unclear who might have been the first observer to discover a comet, depending on which time zone they were in. And she also discovered, do you remember I mentioned nebulae before? She was working with, she was working, as many astronomers did, according to a list of nebulae compiled by someone called Charles Messier. He was a great comet hunter who didn't want to waste his time tracking objects in the sky that turned out to be fixed nebulae. He wasn't that interested in them, it was the comets that he was interested in. But William and Caroline were interested in absolutely everything. They just wanted to track and trace every single celestial object in the sky, which led to great discoveries. So here we are. On August 27th, I saw the beautiful spot in the sword handle of Perseus, and she discovered basically, she discovered some known nebulae according to Messier's numbers, but it was actually, she discovered a new one this night known as M110 or NGC 205. So that's just a really quick overview of some of the amazing documents that we have, which were written by William and Caroline Herschel. I will hand over to Charles now, if that's okay, Lucinda. And but Charles, I have something else to share at the end. I think I might, if there's time, I'd like to show the first example of Victorian humour relating to the planet Uranus.
Yeah, that would be great. So we have Charles Draper with us. Thank you, Sean. We'll do a Q&A after Charles' talk. So we have Charles Draper joining us from, well, he's a representative of the Herschel Society. Hi, Charles. How are you?
Hi, Lucinda. I'm good. Hi, I'm just. Can you hear me? Okay.
Yeah, we can hear you and we can see you. Great. Yes.
Okay. Shall I kick off then?
Yeah, and then let me know when you want me to show something.
Fine. Okay. The idea we had was that it's wonderful to have this sort of connection to Herschel as part of this of observations going on, and of course to have Sean's great introduction, from the RAS. It's fantastic to be a chairman of a society where your main object was the founding president of the RAS, and they have this fantastic archive. So it's always good to hear Sean talking about it. I'm chairman of the Herschel Society, and we realized it makes sense if we could to show you some stuff from the museum. But it wasn't practical to film in the museum today. So what I have is a series of short videos, which I'll ask Linda to put up, which I made in the museum on Monday. And my thanks to Joe Middleton at the museum for allowing this to happen, and to my colleague Jonathan Hall, who actually did the videos. So there's a series of short videos, and the simplest thing probably is if you kick off with the first one, and that's a brief one about the Herschel Museum itself. So if you're happy to do that, and there we go.
Hello, my name is Charles Draper. I'm chairman of the Herschel Society. Our society was formed in the 1970s to rescue the house in Bath where William Herschel discovered the planet Uranus. I'm standing in that house because it's now the Herschel Museum of Astronomy. The campaign to rescue it was started locally, but also strongly supported by Patrick Moore, and it became something very successfully done, and the museum opened in 1981 on the 200th anniversary of the discovery of the planet. It is now a very successful museum with lots to see, including this fascinating object, which is a replica of the telescope that Herschel used to discover the planet Uranus. I'll say a bit more about that later.
Okay, the next video talks about William's early career and his move to Bath. So if you'll crack on with that one, Lucinda.
Hello, my name is Charles Draper.
That's the same one.
William Herschel was born in Hanover in 1738, and he, like most of his family, began their lives as military musicians. He first came to England in that particular role, and he liked what he saw. So when he got his discharge from the army, he came here as a musician, and initially went to the north of the country, where he could establish himself as a very successful concert organizer, music teacher. And he did very well for himself. And then he saw an advertisement in 1766 to be the organist of the newly built Octagon Chapel in Bath. And he applied to win that post, and he did. So he came to Bath in 1766. And he quickly established himself here as a very successful musician, director of music, and teacher. Bath, of course, was a great social hub in those days, so there's plenty of demand for entertainment, music included. And William did that very successfully, and quite quickly he was basically the key man of music in Bath. But as time went by, he slightly got bored with just music, and he had wide interests in things scientific, and particularly astronomy. And he took to see what he could do to pursue this interest. He tried to hire telescopes and to buy telescopes, but he found it very difficult to find one good enough. He had high standards, so he began to make his own. And increasingly, he was quite successful at realizing how to make good telescopes by just studying, getting advice where he could, but experimenting. And that is how he came to make the telescope that he used to discover the planet Uranus in 1781. This is a replica of that telescope. and I'll say a bit more about that shortly.
Okay, the next video is about the telescope itself and the discovery of Uranus.
So this is the wonderful replica telescope that our colleague Michael Tabb made for the opening of the museum. Michael sadly died very recently, but this is one of the museum's objects of great esteem and joy. And it's a very good way of illustrating the way Herschel worked. He was a very systematic man, and he worked systematically with his observing. He's built this telescope, as you can see on this wooden frame. It's a basic Newtonian style reflector mirror, specular mirror back here, and diagonal up here, and so on. But the mount is an altazimuth one, and it's basically designed so you can move things up and down a bit, and from side to side a bit. But it's very clearly designed to look at a particular part of the sky, and that's what William did. He used to do what he called his sweeps. He would examine a particular part of the sky very thoroughly for an evening, and do that night after night when he could. And he was doing one of those sweeps when he saw this fuzzy blob that he did not recognise in the constellation Gemini. And he called this place and looked again a few nights later and saw it had moved. He reported this, and that began a long process, but that was what the discovery of Uranus turned out to be, this fuzzy blob that William found in his garden. And he found it when Uranus happened to be very high in the sky. And some people said afterwards he was lucky to have happened across Uranus, because just by sheer chance. He said he was so thorough in doing his sweeps that he would have found it at some point. That's true, but Uranus takes a long time to get around the sun, so he was lucky in his timing. And Uranus, as it happened, was very high in the sky at the discovery date of March 1781, so it was well placed. So William was a fortunate man in that he made this discovery. But what he's very good was making good use of his fortune. He was very socially adept at seeing what he could take with the opportunities he had, and he took full use of them in his later career.
Okay, and the next video talks more about the partnership with Caroline and what that has meant for modern astronomy.
The discovery of Uranus made William famous, and one of the things it gave him was an appointment by the king as the king's astronomer. If he came to the Slough, so the king could be close to the king, so the king could see what he's doing and also use it to help entertain his guests. So William and his establishment moved quite quickly from there, from Bath up to Slough. One key part of that, of course, was Caroline, his sister, who he brought over from Hanover and had been in turn his housekeeper, an excellent soprano singer, and also a helper in terms of the telescope. When he moved to Slough, he used the money he had from the king and also the money he made from making lots of these telescopes, because they were very popular. He made lots of them with his brother Alexander and sold them around Europe. His own focus moved to still systematically studying the sky, but studying particularly stars, double stars, trying to help work out why it was, how you could measure the distance the stars were using the parallax method. But also those fuzzy blobs. Most people regarded fuzzy blobs in the sky as being things that were sort of a nuisance because they surprised you if you're looking for a comet. William wanted to know what these fuzzy blobs were, and he applied his systematic habits to doing so. So he would do his sweeps and he would track and look at all these fuzzy blobs and made bigger and bigger telescopes to help do so. After a while he realised the best way to do that was to work with his sister Caroline. He would be at the eyepiece observing stuff and seeing what he saw, and he would call down what he saw to Caroline. She would note that down and then write that up. And this was the start of a process that led to the production of the first catalogues of the deep sky. And they did this a number of times and produced very systematic catalogues, and Caroline particularly was very good at organising the information in ways helpful to observers. And this became the foundation of modern astronomy, because you have to have lots of data about what's out there and how to know where it is and what it is. And the work, the catalogues that William and Caroline produced this foundation that makes them so important to astronomy today.
Okay, the next video is actually about the telescopes that William used.
William made many telescopes over his career, and indeed he made most of his money from selling telescopes to wealthy individuals, or even around the courts of Europe, who wanted to have some input into this wonderful new hobby and pastime. So the 7-4 was a very good model from that point of view, but William realised that to see more he needed to have bigger telescopes, and he made several bigger ones. The biggest he made was the one he persuaded the king to fund. This is the 40-foot telescope, and he persuaded the king that it was a good idea to have a telescope that was as big as he could make it. So you have this huge tube, there's a 49-inch mirror at the bottom of it, vast wooden structure, still the same basic design, alt-azimuth telescope that you can sort of move from side to side a bit and up and down a bit. It's the same basic observing method, and the idea is he'll be up at the top observing, and Caroline will be down in the shed below noting down what William was doing. But it was too big, it was too cumbersome. The mirror was very difficult to make in the first place. It weighed half a ton. It lost its reflectivity very rapidly, because with specular mirrors you had to repolish them frequently, and it depended critically on the metal mix. So he discovered a couple of moons of Saturn with it, but basically it was a failure. It was a step too far. By far his most successful telescope was his 20-foot telescope. And there's a picture of it here in the corner of the room. And this was a telescope they used in Slough. Again, same basic observing method. He'd do the observing, Caroline would do the noting down. And it was this telescope that he used to make his amazing catalogues, all these galaxies and star clusters and nebulae that formed the basis of our knowledge of the heavens as we understand it today. And it was a great tribute to what he did. His son, John Herschel, took the same telescope to South Africa in the 1830s to expand the knowledge of this survey to the southern hemisphere. And it is still around today. It is in the NASA Museum of Science in Washington, DC.
Okay, the next video from me is one that's more focused on Caroline herself.
William came from a musical family, and all his brothers were trained as musicians, but sadly his sisters were not. And William was very fond of his younger sister, Caroline, Lena, he called her. So when he was successfully established here in Bath in 1772, he decided to go back to Hanover to rescue her from the life of drudgery she was stuck with her mother. And he persuaded her mother to bring her back. Now, William was acting partly for her sake and partly for his, because he brought Caroline back, and she initially acted as his housekeeper, and then began to also sing, because he realised that she had acquired the family's musical talents, and she became a very good soprano. She also became increasingly involved in the astronomical activities, helping him and his brothers make telescopes, and supporting him when he did. And in time, he actually made a telescope for Caroline to use, so she could make some discoveries of her own. And as this went by, this partnership became increasingly important. Caroline discovered 8 comets and did quite a lot of observing by herself. But the key way the partnership worked was with William at the observing end of the telescope and Caroline doing the note-taking, if you like, initially, and then turning that into the catalogues, and then actually organising the catalogues in a way that could be used very successfully by other observers. And this meant that Caroline, in those various roles, as William's assistant, but also as an observer in her own right, she became the first paid female astronomer. She got a pension from the king for doing so. And her role in doing this has made her very much an iconic figure of women in science suddenly appearing rather than just being sort of hidden behind the men. And she's increasingly recognised as a key figure in science. We tried to support that. We set up the Caroline Herschel Prize Lectureship for female astronomers early in their careers 4 years ago, and that's now very successful. And only this year, the government agreed with the German government to establish a new Caroline Herschel Medal to celebrate particular achievements by German or English or British female scientists. So she's now quite an iconic figure and very well regarded. This is a picture of her in old age when she went back to Hanover, and it's a very sensitive picture of her pointing at the solar system, and quite an iconic figure in history.
Now, there's one more video which is taken in the garden, or by the garden of the museum. Do you want to show that one as well, Lucinda? Which is my colleague Jonathan Hall.
Hello, my name's Jonathan Hall. I'm a local amateur astronomer, an enthusiast, and a member of the Bath Astronomers. And one of the really nice things about our local society here within Bath and the surrounding area is we're able to make use of the Herschel Museum of Astronomy here in Bath at 19 New King Street. The very home where on the 13th of March 1781 William Herschel discovered the planet Uranus from the very garden here behind me. He shared this house with his sister Caroline, who became a very capable assistant and later in life went on to become a very capable observer in her own capacity. The really nice thing about our club and society is we're able to engage with local clubs, organisations, community centres, schools, and put on events here at the museum for people to come and visit, and we're able to actually observe from the very garden where William first made that discovery. So it's continuing that long tradition of actually observing from the very garden here in Bath. And the nice thing is we can do both modern solar observing during the daytime as well as nighttime observing. And we actually use effectively modern telescopes very, very similar to the one that he first made that discovery of Uranus.
Okay, that's it for the video. So if I can, video. Okay. Just a few things to add, if I may. I talked about the Caroline Herschel Prize Lectureship. This year, the winner of the Prize Lectureship is Dr. Jenny Carter of the University of Leicester, so a colleague of the people who are doing the main work, if you like, of this. And Jenny studies the Sun-Earth relationship. Secondly, next year is the 200th anniversary of the death of William, and we're planning a whole variety of things to celebrate, well, not celebrate, but sort of celebrate achievements on this day. And one of them is a lecture we plan to have about the relationship, about new releases with the Gaia spacecraft, which is, of course, a great producer of data about celestial objects, and linking that back to William and Caroline and what they did. Because as I said in one of the videos, while William is famous for discovering Uranus, the real reason that he's important to astronomy, I think, is the start he made on just cataloguing the night sky, looking at what's there and identifying it. And indeed, one of the things, Michael Hoskin is one of the great biographers, if you like, of William, and one of the things he has said about him is that some astronomers are very famous as observers, and some are very famous as instrument makers, and some are very famous as thinkers about what's out there and conceptualizers about astronomy. And William almost uniquely did all three. the other thing about him is that he was actually, he comes across quite a nice person. One of the things about him is that he was pretty good at getting on with people. For his work in building telescopes, he had quite a large team of workmen, and he'd get on with them, and he would get down there, and do the cutting and the polishing and so on to help and he used his family very well. I say used, I mean, he helped them, but they helped him. So Caroline, of course, but also his brother, Alexander. I mean, lots of the telescope making was actually done by Alexander. But he also had a good relationship with the king and the king's guests. And he got to meet all kinds of people, apart from the king's court. I mean, he met, famously, Haydn came to, when he was in London, came to visit. And the story has it that Haydn was so impressed by what he could see on the telescope, it inspired him to write his creation a while later. And he traveled Europe when he could. He went over to France to meet Napoleon. So he is quite a character. And I guess one more thing I would say about him, of course, in terms of the observing that you're doing over this weekend with the infrared telescope, is that, of course, infrared itself was discovered by William in 1800. And the nice story about that is that he realized that the sun particularly produced a lot of heat as well as a lot of light. And he set up an experiment to try and work out sort of which of the colors had the heat, so to speak. So he got a prism and arranged it during daytime for sunlight to come through the prism and divide the light into its various colors. And he set thermometers up in the area where the prism was showing the light, the colors, trying to work out which of the colors produced with the heat. And he happened to have quite a wide array of thermometers doing this. And he happened to have some that went beyond the red. And what he discovered, to his surprise, was that the actual thermometers being lit up by the visible light didn't show much heat, but the one beyond the red did. And that's how infrared came to be discovered. That's the story. I think some people detest the bits of that. It's a nice story. And he was a very thoughtful character. There's another story perhaps I'll mention, that is that he did study double stars a great deal from the very start. And why he got into this was that all astronomers in the 18th century were trying to find a way of discovering how far away stars were. They realized by then that the stars were like our sun, just much further away. And you can sort of, calculate from that, how far away they are. It's a factor of millions. But no one in the 18th century managed to actually measure that distance, because you have to do it by the parallax method, which means having a very, very good understanding of the exact position of a star, and then seeing how that changes against more distant stars as the Earth goes around in its orbit. Now, conceptually, that's good. But actually, it was only discovered only in the 19th century did that begin to be feasible in terms of the accuracy of the measurements done. What William decided was he could use double stars, or things that appear to be double stars, to try and help that process. Because if you have two stars very close together, it's very easy to see what the distance between them is. And he hypothesized that probably all stars were about the same brightness, and probably all stars were actually separate in space. They weren't linked together gravitationally. And that's why he chose to study double stars. Now, both of those hypotheses are wrong. Stars vary a great deal in their brightness, and stars actually typically are linked gravitationally. Most stars are multiple stars, not single stars. So he was wrong on both those points, but he pursued the logic of his idea, and in doing so, discovered a great deal about double stars themselves. So I think it's quite a nice story of how you might make a wrong assumption, but if you pursue it logically, you can do a great deal of useful work to understand what we can know and what we don't. So I think I'll probably finish on that in terms of my presentation, if I may, and I'm hoping to have comments and discussion and questions.
Thank you so much, Charles, for being with us, and fantastic, amazing overview of Herschel and what the Herschel Museum offers us. I'm going to ask Sean, Dr. Prosser, if she's available. I'd like to open it up now. We still have about 20 minutes or so for Q&A. So I'm going to change to gallery view, and hopefully Dr. Prosser is around. I don't know if
I'm here.
can you turn on your, do you mind turning on your camera, or maybe I have to ask you? Let's try that.
I can start it, but it's
Oh, you're
near the book at the moment.
Do you want to move back to your office, or maybe that's good, because then you could show us some more stuff in the library, some more Herschel documents, if you don't mind. That'd be great too.
Yeah, if you'd like to, and if there's anything that Charles would like to expand on, Charles, I've got a specular mirror here. If you'd like to have a look at that.
Have you? Yes. Yeah. Why not bring that out?
Okay, cool. I'll bring it out.
Now, while I bring it out, I'll talk about it. I did say that one of the things that William learned to do was to build his own telescopes, and basically he did so because he tried to buy them or even hire them, and they were A, pretty expensive, and B, not very good. Now he was using a basic reflecting telescope, also the Newtonian one, which he also invented, Isaac Newton, which uses a metal mirror, and that's much simpler than using lenses, because if you use a lens, then you have to figure both sides of the lens, and you have to have very perfect glass itself, and there's a light distortion effect. If you can use a parabolic mirror, then all you need to have is one very good and one very and very well figured surface to actually do the reflection job. So then what you need to have is a good way of making the mirror and a good way of making the surface. And William became very adept at that, and also for his 7-foot telescopes and his bigger ones. But this is a specular metal, which is a mixture of tin and copper, and the exact mixture matters. It's very heavy, and as William made bigger and bigger telescopes, it became more and more sort of difficult to do that effectively. I mean, that's one of the reasons why the 40-foot was a failure. I said in the video that the mirror weighed half a ton. I think it's actually a ton. And imagine in those days, trying to cast a mirror of that size and then do the figuring. Quite difficult. Indeed, if you go to the Herschel Museum in Bath and you go into the workshop, what you can see there is the stone flag floor. And that is interesting, because there was an occasion when William was making one of these mirrors, one of the bigger ones, in a furnace, and the actual mold he was using, I think, cracked, and a great deal of molten metal poured out of the furnace onto the floor. And if you have molten metal falling onto flagstones, they break up and explode. So William and I think probably Alexander was with him, emerged, choking and coughing from the workshop, and that might have been the end of quite a nice story. And poor old Caroline had to patch them up, one of her many things. So that was was an issue. Now, Sean, you're showing one of the mirrors there, I think.
Yes, this is one. It's 6 3/18 inch diameter mirror. It's 3.73 kilos.
Yeah,
you can see.
And you can see it's pretty reflective. So if anyone has seen a typical modern mirror, which of course is glass, coated in aluminium, it's not as reflective as that, but it's not bad. And indeed, William did make the best telescopes of his day and became very expert at it. The business about why they're made this way is that there's no better way of doing it. So William's 40-foot was a very big one. The Earl of Ross, who made a 72-inch mirror, was I think the biggest ever made. But William's 40-foot was the biggest, and until that was done in the late 19th century. So it wasn't, it's a pretty good way of making a large reflector, but it requires somebody of William's application and systematic method to do it. I think he made lots of these, and he's flogged around the place. He didn't say very much about the detail of how he did some of the figuring. So I think he kept some of his sort of trade secrets to himself, which is fair enough, because it was a good way of making money. And there are many telescopes made still dotted around the world. The Whipple Museum in Cambridge has a 10-foot telescope. And one of the biggest ones survived was the 25-foot telescope that he made for King of Spain, counting £3,000 in those days, I think. I think that was destroyed by Napoleon's troops, sadly. But there is a wonderful replica they've rebuilt at the museum, at the observatory, I think, in Madrid, which you can see a YouTube video of. It just gives you a sense of the massive nature of this thing. One of the sad things is that there aren't that many images of the 20-foot telescope, which is the one that I talked about. It's actually at the NASA Museum in Washington, D.C., and the tube is there. The tube has been modified, I think, by John Herschel later. The one thing I'm trying to do is see if I can get together a sort of a 3D model of the 20-foot, because it really is. You can argue it's the most important observational telescope ever made, in a way, because it was what enabled William to do this fantastic work. So I'm trying to see if we can get a better image of it, and that's one of my tasks for the anniversary year. Are some questions that would be helpful for us to answer?
I have a question.
Yeah.
Charles.
Yeah.
Can you talk about the fame that William got after discovering Uranus? What kind of fame was it? Like, did he become an international superstar? Or
yes, he did. Yes, he did. And I think he became famous, certainly in astronomical circles, and well known for that. He became quite a celebrity around the King's court, and I think they're different ways in a way. One is the scientific establishment, and he will be writing to lots of his colleagues in English or German or French. It's a very international world. For example, I think the person who was the person who first confirmed that from its orbit that Uranus was a planet was a Finn, Dr. Lexell. So that this world in those days was a very international one of scientists, and even they were corresponding during war. It's a curious thing. We're used to sort of wartime being a sort of very total experience. Now in those days, I think the scientists said, "Well, our countries are fighting battles, but we are scientists." But also, I think in the King's court, I think one of the reasons why the King wanted him to come up to Slough near Windsor was the King also had lots of visitors, and I think probably things haven't changed now much. If you have a royal visitor and you come to see, and you're there for 3 days, what do you do with them? You have a few dinners and things and talk, and then sort of the small talk runs out. So what King George could do was say, come and see Mr. Herschel, and he'll either bring his telescope here, or we'll show things there. And he had himself a genuine interest. George III was a very interesting man, very intelligent man. He had a genuine interest in this. He was very supportive of William. They fell out a few times over money, I think, but it's also helpful to him to actually to take his visitors to see what William was doing. And I think if you also look at the telescopes that William sold, that sent around the place, I think they were seen quite a lot as trophy items. I think, if you ask the question, how many telescopes were actually used to do good observing, I think that might be a sort of embarrassing answer. So you can see these things as being a bit like sort of royal yachts or something, prestige object to show that you're interested in. Maybe I'm probably being unfair to some of them, but I think quite a few were sold on that kind of basis. But for William's point of view, it was a good money spinner. I mean, he had his salary from the king, but actually he earned less. He was paid less by the king than he's making from his music in Bath. So he had to find some way of increasing his income, and this proved a very successful way of doing it. There's another way which he was very good. So one question here is about what are the flaws of Herschel's telescopes, i.e. the 70, 20, and 40? Well, I think that it's a size issue. I mean, all telescope designs probably have an ideal size for them, and the 7-foot is fine, but it's quite small. And the 20-foot proved to be the ideal one. There actually were two 20-foot telescopes. The one he first built in Bath, which had a 12-inch mirror, and the one he built later in Datchet, which had a 19-inch mirror. And that's the one that really proved most successful. And this is a specular mirror. So maybe a 19-inch specular mirror, it would do about, would be about as useful as maybe a 12-inch or a 14-inch modern mirror, which has more reflectivity. But it was quite an instrument. If you look at all things he actually looked at and saw, I think the most distant object in his catalogue were galaxies 400 million light years away. So, and William himself said he looked further into space than any man before him. That's true, he did. And I think he was the first person to sort of look out that far, and indeed no one following him was looking that deep into space until the 20th century. So he was looking further than most. So that's
I have another question from YouTube, if you don't mind, Charles.
Sure, yeah.
So from YouTube we have, if I recall correctly, we have John Murrell who asked why Alexander Herschel does not get a mention, perhaps because he was a mechanic, not an observer, or not very socially adept.
Yes, it's a very good question. Alexander deserves to be better known than he was. There are two Alexanders. I mean, Alexander the brother. There's also Alexander the son of John, who became more famous as a meteor man. No, you're right. I mean, Alexander, another brother. I mean, there were many brothers actually who did come to the UK for a bit, mostly just to do the musical side. But Alexander is an interesting case. He did the musical thing too. He's a very good cellist, and he initially did that. But he's also a very good mechanic, and he was the man who probably made and designed quite a lot of the eyepieces, for example, that William used. He, in his personality, was, I think, a more troubled character. He also married quite late, but didn't marry very well. Had a number of sort of relationships almost didn't quite work. But he was a very much a key figure, and I think it's quite right to say hasn't been well enough acknowledged, and we're trying to do a bit to rescue it. He stayed in Bath when William went up to London, but fairly often would visit to help and do things and to help build more telescopes. So I totally agree. He deserves to be better known, and anything that colleagues can do to sort of spread his reputation, I would commend.
Awesome, thank you very much. I was going to say, I guess that's just especially as we're now obviously women in STEM, in Space Week being kind of a big one, is there's a lot of people that work in the background. I suppose it's a slight tangent, but even in modern day, a lot of the work that even we're doing today is on the backs of other people who probably unfortunately won't get always credited or acknowledged on these things. And yeah, it's everyone, I say everyone, but it's a big goal to do our best to ensure that everybody who has made an effort should be highlighted.
It is, and I think that's one of the things about women in astronomy, for example. Think of the famous computers, Harvard, for example, female people. And they, were very much hidden characters for a long time, and now being more acknowledged. So I think as we understand more about the way science has been done, and we understand more about the way that women in science and indeed people of minority ethnic groups in science have done things, we're better at saying actually, all these things are only doable because of this work done by individuals, and many of them did this work and worked knowledge for it, and maybe had no opportunity to go beyond it, which was a shame. In my earlier life, actually, I met Dr. Dorrit Hofflight, who was an American astronomer many years ago, and she started life as one of these computers, if you like, but became an iconic astronomer in her own right, and also was very helpful in helping other women astronomers get on. So, there are many figures back there in the past who are now becoming better known. But Caroline is certainly one of the big ones, and we were delighted when the government chose to have Caroline Medal in addition to the relationship we do, and we're looking forward to seeing how that comes to fruition. Because Caroline's quite a big one.
Fantastic, wonderful. I wanted to check in with Sean back at the RAS library.
Hello.
Hi, I was wondering if there's anything else you wanted to show us that's come to mind since, or maybe in talking about Caroline Herschel. I love that you shared all the annotations in the books that, things that we kind of gasp at anyone writing in a book, but it's fantastic that she left those markings or observational notes in the margins. Those are the wonderful things about the parts of the books that we have in our library.
Just before you do answer that, I mean, she was doing that because the Flamsteed catalogue was her starting point. So, and she noted many errors in Flamsteed catalogue, and that was what she was doing as part of her sort of making better catalogue. So I know it's sacrilege to write in a book like that, but it's a practical way of doing things. Sorry, Sean, after you.
Well, yes, I'm glad you brought up the catalogue, which is like the complement to the atlas, because I don't know if we've laboured the point, but she was the first woman of the Royal to be awarded the gold medal of the Royal Astronomical Society in 1828, and that was in recognition of the very meticulous cataloguing work that she'd carried out and which she'd had published, and which was of great aid to astronomers. They're recognising her own work, not just her role as the assistant or collaborator with her brother.
Absolutely.
And the work that she carried out in her own time, observing nebulae and comets. And another way in which she was recognised, have we talked about this, that she was made an honorary member of the Royal Astronomical Society?
I don't think we did mention it, no.
So that was in 1835. The society had been in existence for 15 years, and she was made an honorary member, not elected as a full member, unfortunately, but an honorary member. And at the same time, same year as Mary Somerville, who many of you might have heard of. She was a great science communicator, popularizer of science, who was the kind of person who was engaged by publishers to take incredibly complicated books, which were the equivalent of Isaac Newton's Principia in complexity, and she would distill everything but also expand and clarify the scientific thinking, so that it became that her book, The Mechanism of the Heavens, became like the default cosmology textbook for the next 50 or 100 years. So she made a huge contribution, and we have a lovely letter in our archive where Mary Somerville says, it's such an honour to be elected as an honorary member, and it's even an even greater honour to share this with Caroline Herschel, who I admire and look up to so much. So that's another example of how Caroline Herschel was she was very advanced in years at that time, but her name and her fame had spread certainly across the scientific establishment that Mary Somerville was a part of.
We might say a bit about John Herschel too, actually, because when William married Mary Pitt, and John appeared shortly later, suddenly Caroline went from being the housekeeper to being somebody who's still the assistant, but didn't have quite the same sort of intimate relationship, if you like, with William. I don't know. Sorry, in terms of sort of practical family relationship with William. She did destroy her diaries over a sort of period of years, and we don't quite know what she thought about that. We sort of infer it from the fact she destroyed them. But actually, in time, she became, she had quite a good relationship with William's wife, but particularly a very good relationship with their son, John. Everyone doted on John, and well, apart from sort of helping to bring him up, she's actually very helpful to him in terms of preparing updated versions of catalogue for him to use when he was doing the Southern Sky. And John, of course, in his time became famous as an astronomer, also a polymath, very important in the development of photography, and was really seen as a key man of science later on in the 19th century. And his wife had many children who went on to do their own scientific work. So there was quite a dynasty that flowed from William.
I believe it was John Herschel who co-founded the RAS.
That's right.
Yes, he's one of the ones who had that dinner, I think, and persuaded his father to be the first president. So William was the first president of the RAS, but he never actually chaired a meeting. But his name was certainly used at the very start. Of course, it was founded in 1820, only 2 years before William died. But no, both key figures for the RAS.
So we're both, organizations that keep the Herschel name going and all the amazing, important work that they did. And I think it's fantastic that a female had an opportunity to be a part of that, and an astronomer in her own right.
Yeah, absolutely.
Finally became. Yeah. So I just want to check in with the H3 Plus team and Emma. I know we have it in our schedule to do a telescope viewing with you, I think, an update, but where are you guys with that? Hi, Tom.
Yeah.
Very nice to see you. Did you have any questions for Charles or Sean?
I've been listening with fascination. It's been wonderful. Hello, everyone.
Hi.
Hi.
Dr. Tom Stallard from the University of Leicester. Do you want to introduce yourself maybe as sort of the, I don't know how to describe you, the 18 plus team. Please go ahead.
I wouldn't say I'm the leader of the team, but I'm certainly the oldest. I think this hasn't retired yet. We'll be hearing from Steve Miller tomorrow, who is probably better placed as the proper leader of our merry band of observers. But I have been studying the aurora of the gas giants for more than 20 years now. So, but today is very much Emma's observations. So I'm very much in the background today, I think.
I should mention that, this whole idea of remote observations, at least involving the RAS of the gas giants last year in 2020, July 2020, it was Tom who approached us to live stream the Ganymede crossing the disk of Jupiter, which has been amazing. And that brought us, thankfully, he brought us then this idea of sharing Emma's research and viewing Uranus for the 3 days now. So this is day 1 of 3. And so Emma, how are we on what do you want to do from here?
Yeah, so I guess an update since back, I think what was it, like 11 o'clock-ish, about 10:30 from then onwards. We did have a sorry.
I just want to say thank you and maybe goodbye to Sean and Charles.
Oh, of course.
Okay.
Sorry, apologies.
That's okay. No worries.
Okay. Bye, guys.
Thank you
Goodbye.
so much.
Thank you so much for
You're very
having us.
welcome. You're very welcome. Bye.
Very welcome to the library.
Thank you. very
Thank
much.
you so much,
Bye.
both of you. Appreciate your time.
All right, Emma, on to you. Thank you so much.
So yes, hi everyone. So a quick check-in. Unfortunately, we've had some clouds come in Hawaii, which for us means it is harder to see through Earth's atmosphere to get a clear picture of Uranus. I think that is getting better. You can see in the Uranus cam about, see if I can get my mouse to the right place. There we are. About an hour ago, possibly a bit more, we were struggling to see the moons. They have started to come back. So that's some good positive news there, certainly. Otherwise, our emission lines are looking pretty strong. I wonder, hopefully this isn't going to freak out anyone that's currently observing. I might quickly dart our line a bit. Again, it's going to look a little bit janky, apologies. I was just wondering if we might see another emission line along here, but I think it's a little too early to call it at the moment. Yeah, I think it's just a little too early to try and have a look for further lines. What I should stress when I mean further lines is when we're looking at the H3 plus molecule, that's what we work with as the H3 plus team. The molecule itself actually only emits infrared light at specific wavelengths, so at specific numerical values. At the bottom of these kind of stretched out lines is essentially like an increase in the wavelength number, so like 3.92 to 3.93, 3.94, etc., etc. So why we're seeing these lines is because, again, the H2 plus only kind of goes, hey, I'm here for this one instance, and then comes back out at other wavelengths. So in theory, or say in theory, we know that H2 plus has a lot of lines all the way through, but because the signal from Uranus is so faint, again, we've discussed about it a bit earlier with the fact that Uranus is about 19 AU away from the sun, which makes it tricky, trying to obviously get as much signal. Additionally, kind of added with that point is the amount of solar flux, or the amount of sunlight that reaches Uranus is much, much weaker than what we have here at Earth. Again, because it's so far out, that means that stuff like the aurora is actually much weaker, or weaker-ish in essence, to what we would see like at Jupiter, where it stands out. Like I think the best way I explained it a couple of days ago is comparing a little torch flashlight to a police searchlight in kind of the intensity that we almost see on these on the spectra itself. So it's an interesting change between planets, but certainly very fascinating. Anyway, I'm distracting myself entirely. We haven't seen, earlier we did see like this peaking, or what looked like a splodge almost at the top part of our line. I originally had a circle around it to kind of go, hey, we might be seeing something. That seems to have gone. But that isn't to say like, oh, it's never appeared. What you're seeing here actually is a total. So all of the images that we've taken with spectra, we basically put one over the top, over the top, over the top, over the top, over the top to basically strengthen the signal so that we can see what's going on. That's good news for us because it means that we've seen something and then it's gone away or gone off from the slit itself. So that hopefully strongly means that we perhaps saw something at the beginning of this morning. Me and Henrik were discussing about the fact that that could possibly be the northern aurora, as we think the south pole is at the bottom of this image, at the bottom of the line, sorry, and the north pole, rotational pole. I think, sorry, I noticed you had a question. John Moore, is that Miranda just above the slit? Yes, so we have, yes, Miranda is, let's see if we get my mouse in the right place. So this little bit of patch here, as John Moore said, is, yes, Miranda. We had a slight discussion earlier. I think Miranda was just over here and that has now rotated more towards the slit, but it's a little bit difficult to tell. I apologize. Yeah, there we go. Got my screen box to try and highlight it a bit better, with Ariel just underneath and Umbriel just above the U in the Uranus cam title.
I think that's Puck.
Oh, is it Puck?
Box. Yeah.
Oh, my apologies. Okay, it's Puck.
And then
I was
down from
totally
there,
wrong then. Sorry.
Down from there is Ariel and then Umbriel.
Okay, so Puck. My apologies then. Puck, Ariel, then Umbriel.
If I'm right.
So I think, so yeah, that's the positive that we have seen that brightening go, means that there's something localized, and localized tends to hint towards that of aurora. As soon as you saw it at the north, that might have been the northern aurora. So that's positive news. Hopefully we might see some more brightening towards the middle of the line, as that's where we expect the aurora to be. I'll see if I can get up the video that James did very kindly. So yes, you see here the southern aurora is more kind of in the middle of, if you imagine this Uranus is like a circle, as a disc like we're seeing. You can see the northern aurora, that's the one that's just on the very edge of the planet, but the southern aurora is actually more towards the center of the planet in this instance. So if we see brightening in the middle of the line, we think it would be southern aurora that we're observing, and if we're seeing brightening towards the end of the line, as we saw earlier, that may be the northern aurora. But as a fun point, because obviously this is only so many pixels, it could very possibly be that we're just seeing the southern aurora, but more towards the edge. So it's the fun part of observing Uranus. It's difficult to know where everything is. I think that's going to be a point that's probably going to be touched on later today, or perhaps even tomorrow. But the rotational phase of Uranus has such a large error on it that we actually don't know where things are on the planet, in the sense of where we expect the aurora to be. Last time we had a specific idea of when that was back in 1986. That's with Voyager 2, and it's one of the big pushes at the moment as to why we need orbiters and satellites to head over to Uranus and Neptune so we can get a better idea. I think
so. There's a really good question from YouTube about the sky above IRTF in the last panel that you had, and I think it's really it's the view above IRTF. Is it a live view? So want to talk a little about that. What we're seeing.
So I have two panels. I have this one, which has the GIFs. Now this is of the previous night. So this is a section, like this isn't as fast as it is going overhead at the moment. This is about a 10-hour time lapse, I think. And this is with the Gemini telescope, but Gemini is in the same location of that of IRTF. Frustratingly, I did have a second setup that you're seeing here, which has live images from the telescope from inside IRTF and the sky above. However, the link to the sky above doesn't work very well at the moment, because this is back at 4 in the morning, I think.
Okay.
For HST times. There is a better image currently online, but their webpage where they have it connected to at the moment doesn't show the sky above at the moment. It is a couple of hours previous. I don't know how to quite fix that, apart from message Gemini Cams and ask them if they can update their page, please.
There's some wonderful pictures online. If people search for the Mauna Kea Weather Center, they'll see the same kind of webcams that we use to look for these kind of things, and you can see that most of the sky is beautifully clear, but there are some thick bands of high up cloud in the horizon, which may be what was getting in our way a little bit earlier. I think maybe you should talk a little bit about what kind of clouds are bad and what kind of clouds are terrible, because we're seeing predictions for Sunday that are a little worrying.
Yes. Just trying to think. Sorry, I'm just getting some stills up and putting that into the.
Well, while you do that, I'll talk about that. How about?
If that's okay.
So there are high ice crystals in the top of the atmosphere of Earth, which block our way. That's called cirrus clouds. Those clouds we see from the UK if we're lucky and everything else is out of the way. But generally, we have much thicker clouds lower down. And those clouds can be very destructive to observations depending on how thick they are. But usually we're able to see through them. What they don't do is actually impinge on our ability to be at the telescope and open the dome. Generally speaking, Hawaii is a very high mountain. It's 4 kilometers high, so it sits well above the cloud deck in Hawaii. Normally, Hawaii has clear skies anyway, but if you have significant clouds, they are much further down. So you can see on this picture here where IRTF sits, and the clouds are effectively almost like an ocean of cloud sitting way below you. But you can have the right or maybe the wrong observing conditions that allow those clouds to rise up. So if there's stormy conditions, there's a lot of upwelling of those clouds, and they start getting higher and higher, closer and closer to you up the mountain. And if they get high enough, then they start impinging on the mountain itself. And then as you have on a frosty morning, you can have those clouds starting to form dew, on the surfaces. So not only the rock around the telescope, but also the mirror itself, and that's a disaster. So if the humidity in the air reaches a certain level, all the telescopes on the summit of Mauna Kea will close. So that's most detrimental of all. And sometimes you get into the terribly frustrating situation where the skies above you are beautifully clear, but the humidity is high enough that it would start forming dew on the mirror, and so you can't open, even though when you stand outside you can see beautiful clear night skies. So today we're very lucky that we've got very, very dry conditions at the summit, but there are a few of those clouds sitting further up, so that doesn't affect our work too greatly. What it does mean is that sometimes it's a little bit more difficult to get an assessment of just how much material we're observing, because the brightness can change, but we're still able to get a very good measure of the temperature of the atmosphere, which is one of the other targets that we have, just because that only absorbs the light in the same way across the whole of the range of wavelengths that we're looking at. So that's what we're aiming for, the two different types of weather, that one that is very bad and one that is allowing us to still take these observations.
So thank you for taking that, Tom. So I think we have one more minute before we're moving on to our second speaker for the day. I don't know if Lucinda is with us, or if we...
I am here. Oh, and we do have Dr. Lee Fletcher here with us in a panelist. So he is, it looks like he's ready to go. I was wondering if Tom, would you do the honors and letting us know who Dr. Fletcher is?
Sure, absolutely. So Dr. Lee Fletcher is a very esteemed infrared astronomer who looks at planets. We have similar research interests, but I look at the top of those planets, and Lee looks further down at the wonderful swirling clouds that sit underneath. So hopefully he's going to be able to tell us about all of those wonderful clouds for Uranus and maybe Neptune. I'm not sure. I will pin Lee so we can see him. That seems sensible, doesn't it?
He's right there. He's right next to you.
Hi, Tom. Hi, Emma.
Hello.
So I have been watching along in the background whilst you've been doing this incredible live stream. Well done for balancing both running a telescope and talking to the general public and even school kids at the same time. Well done for doing that.
Thank you.
So would you like me to share my screen?
Yeah, if you don't mind, that would be awesome.
Okay, so I'm sharing now. I'm going to go into presentation mode. Can you tell me if you can see the full screen, or can you just see?
You can see the presentation mode, so we can see your comments on there.
Okay, let me swap around. How's that look?
Perfect.
Yep, that's awesome.
Fantastic. Okay, so thanks, Tom, for that introduction. As you're probably aware, myself, Tom, and Emma all work together at the University of Leicester. We're in the Planetary Science Group. And although my particular area of research doesn't really touch upon H3+, which is the target of today's observations, I have spent the last several years trying to, let's say, persuade the international community that we'd like to see a future mission to Uranus and Neptune. So my job today, when Emma invited me to take part in this, is to try and persuade everybody who is listening that the next big step in our exploration of the solar system should really be an ambitious mission out to either Uranus or Neptune, something that is similar to maybe the Cassini exploration of Saturn, or at least could develop our understanding of these two enigmatic worlds far beyond what we currently have. So over the next half an hour or so, I shall take you on a bit of a journey through these ice giant systems. And at the end, I'm very happy to answer any questions that you might have about the ice giants and about the future exploration of our solar system in general. Right. So I just wanted to start with an idea of how our understanding of the ice giants, or how our imaging, should I say, of the ice giants has changed over the last 30 years or so. Back in the late 1980s, in a golden 3 years of exploration, the Voyager 2 spacecraft flew first by Uranus in 1986 and then by Neptune in 1989. And what those incredible flybys did was it took something which had been merely a wandering point of light in people's telescopes in the pre-space age and turned them into fully resolved planetary systems that were, sorry, I'm just moving the screen out of the way so it doesn't keep interrupting me. Systems that had rich complexity. They had satellites, they had rings, they had a magnetosphere that we're still struggling to understand. And they had an atmosphere which was shifting and changing, evolving over a whole range of timescales. Now, of course, Voyager 2 was just a fleeting glimpse of what these ice giants were like. And ever since that time, we've had to rely on both ground-based facilities, as you can see in the central column, and also space-based telescopes, such as Hubble, as you can see in the right-hand column, to give us glimpses of what these atmospheres are doing. And we're doing a relatively good job now at trying to track the evolution of storm features, to give us an idea of what their climates are like and what the conditions are like within those atmospheres. And we can do these things remotely. So you might therefore ask, well, why do you need to send a mission there? And that's because although we can see what the atmospheres are doing, we can say nothing about what's going on down in the deep interiors. We can say very little about what's happening in the ever-changing magnetosphere. We're not resolving the icy satellites of these systems. We're certainly not seeing anything on the dark, hidden night sides of the satellites that are out of view from Earth-based observers. And we're not able to really tell you very much about the rings. So although you can do remote observations of their atmospheres, the rest of the system remains hidden to us and has done now for the past 30 years. Now, the ice giants Uranus and Neptune are a different category of object compared to the gas giants Jupiter and Saturn. The gas giants have been well explored over the past several decades by large spacecraft missions, things that have been in orbit around Jupiter and Saturn and giving us unprecedented views of what those worlds are like. But they are hydrogen and helium dominated. There's more than 90% of the material within those worlds is hydrogen and helium gas, with just a few trace elements like nitrogen, sulfur, oxygen that form the plethora of cloud features and structures that we can see on Jupiter and Saturn. They presumably formed relatively quickly out of the protosolar nebula so that they could suck in all that surrounding hydrogen and helium gas from the nebula before the sun expelled all that material out of the solar system back during the epoch of planetary formation. And one of the other things to remember is because Jupiter and Saturn are so large, the pressures and temperatures in their interiors build up to such an extent that even hydrogen takes on an exotic form. It's something known as metallic hydrogen, where the electrons get stripped off from the protons and can flow around like a conducting soup of material down at great depth. Now, that doesn't happen on the ice giants. They're fundamentally different beasts. As you can see from the numbers here, they're about 14 to 17 times the mass of the Earth, about 4 times the radius of the Earth. And we think the hydrogen and helium there comprises just a much smaller amount. And that the majority of what makes up an ice giant are things like methane, water, ammonia, hydrogen sulfide, and possibly other rocky elements buried down within their deep interiors. Now, what that suggests is that they didn't form quickly enough to accrete all that hydrogen and helium from the surrounding protosolar nebula. And in fact, they formed just slowly enough to get to this size of 3 to 4 Earth radii across. Now, because they're not that big, that means you don't get the metallic hydrogen. And in fact, it's then the properties of water under high pressures and high temperatures, which might be dominating the physics of their interiors. So the thing I want you to keep in mind throughout this presentation is that the ice giants are very different beasts compared to the gas giants. Now, we've had a fantastic few decades of exploration in the outer solar system. I mean, Voyager really kick-started it back in the late 1980s, but then in the 90s, we had the Galileo spacecraft at Jupiter. In the 2000s and 2010s, the Cassini spacecraft did incredible work in orbit around the planet Saturn and exploring Titan, the largest moon in the Saturn system. Today, scientists at the University of Leicester, in partnership with our colleagues over in the United States, are working on the Juno spacecraft, which has been in orbit around Jupiter now for the last 5 years and will hopefully continue for several years into the future. And we're looking ahead to something called the Jupiter Icy Moons Explorer, which is the JUICE mission, Europe's first mission to the giant planet Jupiter and the first ever mission that will actually go into orbit around Ganymede, the largest moon of Jupiter. So having said all that, you can see that the ice giants are kind of the forgotten worlds. They're out there in the distant solar system. And unlike Jupiter and Saturn, they have not had a visitor in more than 3 decades now. So it's high time that we tried to make a change to that. And one crucial thing that has changed since 1986 and 1989 to the present day is that there has been a tremendous explosion in the number of planets known around other stars. The census of extrasolar planets is now at 4,000 plus and is only going to grow larger and larger, meaning that the worlds that are present within our own solar system are fabulous templates for understanding what the environmental conditions might be like on those worlds, and crucially, how those worlds may have come to form in the first place. Now, this chart in the center of your screen shows the frequency of planets with a certain radius being discovered in those extrasolar planetary systems. And what you can see is that these aren't all objects like massive Jupiter and Saturn. You might argue they're not all objects like massive Uranus and Neptune, but actually the most common outcome of the entire planet formation process is something down there between 1.8 and 3.5 times the radius of our Earth. Sometimes these are known as mini Neptunes, but by calling them mini Neptunes, that might be a little bit misleading because we don't truly know what worlds of that size might be like. But what we do know is that Uranus and Neptune are possibly the closest representatives that we have of the most common outcome of planet formation throughout our entire galaxy. And so the fact that we have not been to thoroughly understand and explore those worlds means that there's a huge missing piece of the puzzle of planet formation right now that we would hopefully be able to resolve with an ambitious future mission to somewhere like Uranus and Neptune. So it's a window, if you like, on extrasolar planets as well. So I'm now going to take you on a journey through an ice giant system to try to reveal to you what we might be able to learn from a mission that would go out to those destinations. This cartoon shows the richness of both of these systems. Today, with the observations that we're taking with the IRTF, we're thinking really about the planet itself and it's interacting with the surrounding magnetic field. But in addition to that, you have this rich collection of icy satellites, some small, some large, some with evidence of geological activity, cryovolcanism, enormous events which has reshaped those surfaces that we'll talk about later. They have a delicate ring system which must be interacting gravitationally with those attendant satellites. And they have deep, dark, hidden interiors, something that we can only get to grips with if we get up close and personal with one of these ice giants to measure its gravitational and magnetic field. So let's start from the inside and we'll move slowly further out. We mentioned a little earlier on that the ice giants appear to have huge enrichments in the amount of heavy material within their interiors. And when I say heavy material, I really mean in an astronomer's sense of everything that's heavier than hydrogen and helium. So things like water, things like methane, things like ammonia and hydrogen sulfide. Now, as you go down deeper and deeper inside these ice giants, those molecules will take on rather exotic forms that can only be reproduced in a laboratory for fleeting instants under extremely high temperatures and pressures. So getting to grips with what water is actually like when it's down in these deep interiors is quite a challenge. And there's ideas out there of forming this kind of slushy, hot, dark material, a kind of icy mantle deep down there within the interiors of Uranus and Neptune. And when you think about how large these two worlds are, what that suggests is that the water in this form could be the most common form of water throughout our entire solar system, buried down there beneath the fluffy cloud layers of these two ice giants. There is an enormous question mark, though, over the amount of that heavy material present within the ice giants. And to our embarrassment, after several decades of study, we still don't actually know if the ice giants are icy. It's possible that the majority of the material down there can be thought of as rocky material, so silicates and iron-rich materials, for example. After all, when you look at some of the seed material out there in the distant solar system, the material is making up the satellites, the material is making up things like Kuiper belt objects, Pluto, Triton, etc. They have a 50-50 split in ice and rock or thereabouts. So it's possible that our most basic concept of the ice giants, whether they're icy or not, is still a huge question mark that a future mission needs to resolve. Now, that's treating both ice giants in a very similar way, but actually, once the two giant planets formed, they went off down very different evolutionary tracks. So we have two very different looking ice giants today. The IRTF right now is looking at Uranus, which has this extreme axial tilt. It's tilted over onto its side and therefore rolls around the solar system like a spinning wheel. And it has a collection of what we call classical icy satellites. These are icy satellites that must have formed alongside the planet back in the early days of planet formation and are still there today, bearing witness to the whole evolutionary process that shaped Uranus. Now contrast that with Neptune, which might be a more typical ice giant. It doesn't have this enormous axial tilt. In fact, its axial tilt is similar to something like planet Earth, which means that it experiences spring, summer, autumn, and winter, but each of those seasons lasts for 4 decades, as Neptune takes 165 years to go around the sun. And unlike Uranus with its classical system of satellites, Neptune instead has Triton, an interloper from the outer solar system, potentially from the Kuiper belt, that's more like what would have happened if you took Pluto, the dwarf planet, and brought it in towards Neptune and captured it into orbit. So think of Triton like the cuckoo that arrived within the original nest and expelled all the original satellites that would orbit around Neptune. So two very different worlds that might have started out the same, but their evolutionary processes would have eventually led to them being rather different places. Now, for Uranus in particular, we might ask, well, what exactly went on to give it this axial tilt? And the best idea out there, even to this day, is that back during the epoch of planet formation, when these worlds were jostling to get into their current positions, maybe Uranus was hit by a gargantuan collision, maybe another forming giant planet that tilted the entire world over onto its side. And these are some wonderful simulations by our colleagues up at the University of Durham, which have simulated what might have happened to such an impactor, such a cataclysm. And in fact, they suggest that some of that original impactor material may still be present down at depths within Uranus itself. But the consequence is that with Uranus over onto its side, it has the most extreme seasons, the most extreme climate, the most extreme magnetosphere of any destination within our solar system. So let's look at that atmosphere for just a little bit. Slightly complicated diagram this, but you've got some movies of the churning atmospheres on the left-hand side, so you can see storm features coming and going. And then the cartoon in the center of the figure here tries to make one point rather clearly, and that is that Uranus only gives off as much energy as it receives from the sun. So the sun provides all its solar heating to the planet Uranus, and then reflected back at us is the same amount of energy. There doesn't appear to be any additional source of energy within Uranus that's contributing to the emission. Now that's unusual because Neptune, and in fact every other giant planet in the solar system, gives off more energy than it receives from the sun. We call them self-luminous. The suggestion might be that something about that early collision that tilted Uranus over onto its side somehow interrupted the regular evolution of one of these ice giants, meaning today that there's basically no heat source down at depth. Or maybe something about the composition of Uranus is such that there's like a lid on top of all the churning convection down at depth, which is just keeping all that energy pent up inside the planet and not allowing it to escape to be detected by our telescopes and our spacecraft. Whatever the reason, every now and then we see explosions of atmospheric activity, which suggests there is a lot of pent up energy down there within the atmosphere of Uranus, just waiting to be released. The final point I want to make on this slide is that because these planets are smaller than Jupiter and Saturn, and because they rotate slightly more slowly once every 16 or 17 hours compared to Jupiter's once every 10 hours, they're in a different regime of weather and dynamics compared to Jupiter and Saturn. So they occupy a different region of what the atmospheric scientists might like to refer to as parameter space. Take a world and spin it very quickly, and you have something like Jupiter. Spin it very slowly, and you have something like Venus. Spin it just right, and you get Earth. And spin it just between the rates of Earth and Jupiter, you get something like Uranus and Neptune. And by studying therefore Uranus and Neptune, it allows us to study how climate works in general across all planets in the solar system without just looking at one specific example. Some more observations here of storm phenomena within the atmosphere of Uranus taken by ground-based telescopes over the years. But that little movie on the left-hand side shows 25 years of Hubble Space Telescope observations tracking from summer in the southern hemisphere back in the late 90s through to equinox in 2007. Then the north pole of Uranus starts to come into view. It's springtime in the north right now, and you get this beautiful reflective polar cap of aerosols forming as sunlight is falling on the north polar regions just there. And in fact, if you fast forward all the way through to the last image, which is 2020, that's the vantage point that we have today with the IRTF with Emma's observations. Now going to Neptune as well. Neptune has one particular feature, or I should say had one particular feature, which made it really stand out. And that was a huge swirling vortex called the Great Dark Spot, similar potentially to the Great Red Spot on Jupiter, but rather unusual in that it was observed by Voyager back in the 1980s. But then 5 years later, when the Hubble Space Telescope got its first really good views of the atmosphere of Neptune, it had gone. It had vanished. We now know that these large swirling anticyclones on Neptune come and go with time. We've seen several additional dark spots over the course of the last 25 years, but they seem to migrate towards the equator. Then they get sheared apart by the winds that are present at Neptune's equator, and they completely vanish. Now, Neptune seems to be changing all of the time with tremendous storm activity. And all of this could come back to the fact that Neptune has that internal heat source providing extra energy compared to Uranus without that heat source. And that extra energy is powering some of the most extreme meteorology anywhere in our solar system. Now, moving from the planet itself and going further out. And I know there's been a few questions today in the chat about the satellite system of Uranus and Neptune. So I'm going to take you through the classical satellites of Uranus right now to give you a flavor of some of the incredible stuff that we can see. We're going to start with Miranda, which is just about 500 kilometers across. And it looks like it's been completely reshaped over many, many eons by rifts, by some kind of cryovolcanism, by tectonic processes, which are creating all these stripes and grooves that you can see in the various images just here on screen, including potential cryovolcanoes in panel A. We've got a huge cliff, some 12 kilometers high, down in the bottom right-hand side, maybe up to 20 kilometers high, actually, that appears to have one of the largest cliff faces anywhere in the solar system. And again, it's due to this moon appearing to have been fractured and sheared and changed over the course of time. Moving slightly further out, we have Ariel, which could potentially be an ocean world. And this term has a lot of credit at the moment within the planetary science community, because if you have a thin or potentially thick layer of ice forming the crust of one of these satellites, that could sit above a deep, dark, hidden ocean down at great depths within the satellite, where the water would be in its liquid form. And of course, when you have water, that's one of the best places to go looking for signs of life. These conditions might be what we call habitable. Things like Europa in orbit around Jupiter and Enceladus in orbit around Saturn are classed as ocean worlds because of this potential presence of liquid or water down at depth. And on the surface of Ariel, at least on the side that we've seen with Voyager 2, we can see grooves and evidence of cryovolcanism, which might suggest some kind of connection to a slushy interior. The thing to keep in mind for Uranus's moons is that we've only ever seen the sunlit hemisphere of these worlds. And this beautifully processed image actually shows sort of hints of structure on the dark side of this moon Ariel that's actually being observed in Uranus shine. Okay, so this is light reflected off Uranus that is illuminating, if you like, the backside of Ariel. So there's regions on these satellites which no robotic eyes have ever been able to bear witness to. 3 additional satellites here on this slide. You've got Umbriel, which is characterized by this extremely bright material inside of a crater floor, the Wonder crater, seen at the top edge of that heavily cratered moon. Titania, which is the largest of the satellites in orbit around Uranus, with various chasms crisscrossing across the surface of the icy satellite. And then Oberon, it's 760 kilometers radius. And in fact, just down there on the bottom right-hand side, you can see sticking up over the Terminator region and a mountain that appears to be some 11 kilometers tall. That gives you some kind of sense of scale of what it might be to be a rover trundling around on the surface of one of these icy satellites. And in fact, when you take all five of these classical satellites, you get a sense of just how diverse all of those environments are. Now, remember that Neptune is a slightly different system with this interloper that came in potentially from the outer solar system, something like a Kuiper belt object that could be a twin to Pluto, albeit heavily reprocessed by the powerful collision or whatever took place to bring it into Neptune's vicinity. But we see terrain across the surface of Triton, which is rather unusual. It's clearly been shaped by geologic activity over time. And in the south polar terrain, there's tantalizing hints that there are active plumes or geysers pulling up material from the subsurface of Triton and depositing it into a very thin atmosphere that surrounds this moon. In fact, you can see in the image at the very top, you can see dark plumes that raise some 8 kilometers high above the surface and are then blown around by the very thin atmosphere of Triton. And all across that south polar terrain, there are dark smudges and streaks which appear to be remnants of former plumes that might have been erupting. So maybe the action of sunlight falling on this icy terrain where you've got ices of nitrogen and carbon monoxide and water all blended together, maybe that's causing fractures, maybe it's causing something to release all that pent-up energy into the surrounding environment. Triton is therefore a truly fascinating destination for future explanation, and is a great reason why we'd one day want to be in the Neptune system to go and explore, and to contrast what we find there with what we discovered at Pluto with the New Horizons mission a few years ago. In addition to those large satellites, there's also a collection of minor satellites, smaller bodies, which even with the capabilities of Voyager 2, remain as simply points of light within the images taken by that spacecraft. We know next to nothing about them other than their orbits, their mass, their radii, and potentially their gravitational interactions with the very delicate ring systems that we find around Uranus and Neptune. Here's a high-resolution image of those very fine dusty rings that you can see in orbit around Neptune. And in fact, we refer to this system as being dynamically full. There's a whole load of objects all crammed into a very small amount of space, respectively, compared to something like the Saturn system. And yet they appear to be sculpting this delicate dance of objects between the rings and the satellites themselves. Neptune, even more perplexing, appears to have not just complete rings that go all the way around the planet, but clumps of material, what's known as ring arcs. In fact, there were 3 ring arcs that were identified by Voyager, but later Hubble observations now suggest only 2 are still in existence. So what is going on? There must be some kind of formation and removal of these ring arcs, maybe clumping of material and then spreading back out again over timescales, which we as human beings can understand. This is just a 30-year period. Who knows what a spacecraft in orbit around Neptune might be able to observe in terms of this dynamic, ever-changing process within the delicate rings of Neptune. And finally, all of this, all of the rings, all of the moons, the planet itself is all bathed within these extensive and very, very complicated magnetic fields. Magnetic fields quite unlike Jupiter and Saturn. We think they're being formed by convective, conductive motions somewhere in the outer regions of the planet itself. But because of the unique configuration of Uranus, for example, instead of having a nice magnetic field that's north-south and then interacts with the solar wind, like we see in the top left just there to create this extended magnetic field appearance, because Uranus is bowled over onto its side, you can have this bizarre curling up or helix-like phenomena that form it downstream of the planet itself as the magnetic field is being squished up by the rotation of the planet, and systems where you can have the poles, the magnetic poles of Uranus, either open to the solar wind that's coming into it or completely shielded from the solar wind that's coming into it. And all of this is changing on daily timescales for the Uranian system. That magnetic field configuration is totally unlike anything else seen in our solar system. And imagine trying to understand all of this complexity with only a single flyby spacecraft and not something that is there in orbit around the planet for many years, sampling how all of this is changing with time. That's another fantastic reason why we need a mission to the outer solar system. So let's talk about that very quickly. There's a lot of challenges involved in trying to get all that way out to Uranus and Neptune. The first is the trajectory itself. With conventional chemical rockets, the best way to do this sort of mission is to do a flyby of Jupiter on the way out there. Okay, we do a gravitational assist, borrow some of Jupiter's energy to sling us out to Uranus or Neptune. We can get a lot more mass out to the system if we do it that way than just trying to fly there directly. But there's a problem. Jupiter is only in the right place every 12 or 13 years to get out to Uranus and Neptune. And even with Jupiter, the timeline to get out there still takes more than a decade, in addition to then wanting to be in orbit for 3, maybe 5 years or so. So these are long-term missions, okay? People who are listening today, school children, might be the ones who are involved in the working on this spacecraft if it was ever to actually be there in the ice giant systems. Another problem, even out at 20 or 30 astronomical units from the sun, sending your data back, all those precious images, all those precious spectra, is a challenge because you need either an enormous communications antenna with lots and lots of power, or you need a more clever way of sending back your data than just using radio waves, which is the current way we get our spacecraft to telephone their information back to Earth. So communications are a challenge. And finally, you can't use solar power out at Uranus and Neptune. You'd need solar panel arrays that were just gigantic, absolutely enormous. So what we rely on is the radioactive decay of isotopes to produce the electrical power that we need to keep the spacecraft warm and to keep all the instruments with electricity to be able to take their data. Plutonium is hard to come by, as anybody who's watched Back to the Future will know, and there's only so much stockpile to be able to be used within the space program. So there's a huge competition on for any mission that wants to go to the outer solar system to get this plutonium, these what they call radioisotope thermal generators, to provide you with the power. So for all of these issues, what we really need is a collaboration between agencies, between NASA on the one hand, ESA for us, but also other agencies around the globe as well. In particular, just this year, the European Space Agency have recommended that because of the importance of trying to get a mission out to the ice giants, they're recommending that every effort be made on the European side to set up an international partnership mission to try to make sure that if, for example, another agency like the US decided to go ahead, that European scientists could also be involved. But the key challenge of, say, ESA doing it by themselves comes back to the challenges I've got on the screen in front of you: the duration, the communications, and the need for radioactive power sources. There's no shortage of good ideas. In fact, earlier on today, people were talking about the Trident mission, which would have gone out to Triton had it been selected last year. There's been various studies by the NASA on the left-hand side, by the European Space Agency on the right-hand side, that have all suggested that these missions are entirely possible using today's technology if there was just the political and financial will to go ahead and do it. And in terms of the politics, these studies then feed into large-scale strategic surveys that might be taking place on both sides of the Atlantic to prioritize which destinations in the solar system we should be going to next. One of those surveys has just finished. That's the European Space Agency's Voyage 2050 process, which recommended that partnership mission. And another is still underway as we speak. The Decadal Survey in Planetary Science is currently underway, will report early next year. And of course, there's a large community of people out there who are desperately hoping that a mission to either Uranus or Neptune comes as the top priority so that we can get started on that mission. And there really is no time to lose. I mentioned about those windows that occur every 12 or 13 years to get out to the ice giants. Well, all of those studies have suggested that the next best opportunities to do that are in around about 2030 for Neptune, which is coming up very quickly, or in the early to mid 2030s for Uranus. Okay, if we were able to launch within those timeframes, we'd be able to get a gravitational assist by Jupiter and get out to Uranus or Neptune by the early to mid 2040s. And that's crucial timing because it means we get to see the northern hemispheres of those moons that we've not seen before for Uranus. And for Neptune, that south polar terrain of Triton, where those plumes were apparently erupting, would still be in sunlight by the time we arrive. Leave it any later, we'll miss the Jupiter gravity assist. Uranus will be in the same configuration as it was when Voyager 2 flew by, and that south polar terrain of Triton will now be hidden to us in darkness, potentially for the next 80 years. So there really is no time to wait. An international community of people is therefore trying to lobby agencies on both sides of the Atlantic to try to make this happen. And before the coronavirus pandemic, myself and Tom and Emma and all the other people on this call were down in London for a large international meeting of scientists to try to further this ambition of getting a mission out to the distant solar system. And whilst we were there at the Royal Society, we were very lucky to be able to view Herschel's notebook from over 240 years ago, which did describe this potential discovery of a comet that he thought he'd observed in the night sky through his telescope. And in fact, there's a lovely line in there, which I think Emma and colleagues, you should take note of. He at first suspected some disorder in his telescope before making any conclusions about the kind of thing that he was seeing in there. And of course, then concluded that it was a comet only for later astronomers and discussions to basically reveal that this was the 7th planet in the solar system that he had discovered, the first classical planet in history through telescopes. So how do we make this all happen? On the left-hand side, those were our last observations of Uranus and Neptune taken by the Voyager spacecraft when they left those systems in the late 1980s. And as we've seen, exploration of those worlds will touch on the origins of planets, not just in our solar system, but all across every solar system. It will look at the exotic conditions within atmospheres, magnetospheres, the satellites, the rings, and it will touch on themes that are much broader than even planetary science, how the solar wind interacts with planets, particularly those with magnetic fields as complicated as something like Uranus and Neptune. And whatever we learn from the ice giants, because objects of that size appear to be the most common outcome of the planet formation process, they will be of use for 21st century characterizations of extrasolar planets as well. So the question is, can we make this a reality by the early 2040s for a mission that would get there, the early 2030s for a mission that would then get there in the 2040s? Well, I genuinely hope so. And events like this, hosted by the Royal Astronomical Society, will really help get that key message out that this is the next big thing for us to be working on in the coming decades. So with that, I'll say thank you very much and open it up, if we've got time, to any questions.
Thank you, Lee. That was a really fascinating talk that covers in detail a lot of the persuasive arguments that we're trying to make to get people to understand why it's so important to get out there to Uranus and Neptune. I think it's worth pointing out that you would never have time to explain all of the wonderful science that we could do. If you look back at what Juno is doing now, what Cassini did, the thousands of papers that have been written, the vast wealth of information that we've gained, that hopefully another mission like that would do. I haven't seen any questions come up yet, but you have a picture of the James Webb Space Telescope behind you. I'm assuming you're not actually sat on the ship on its way over. I have to say that they're going to be very disappointed when they find out that the James Webb Space Telescope main mirror is here in my office in Leicestershire. Yeah, they're hoping it's going to be on a spacecraft in the not too distant future. I know a lot of the people I've spoken to are really fascinated by James Webb, and it's going to do some amazing science. But of course, what a lot of people don't appreciate is that it isn't a panacea. It isn't the best telescope in the world for everything. So do you want to talk about maybe the top 3 things that, in terms of, Uranus and Neptune, you think it's going to answer that we haven't been able to before, and also maybe the 3 things that people might be surprised that it can't do?
Okay. So James Webb Space Telescope has been being prepared for over 2 decades now. It's finally scheduled for launch on December 18th. And it's going to be carrying the hopes and dreams of many scientists across the globe when it finally launches from French Guiana on that date. It is the largest space telescope ever constructed, so large it's going to have to unfold and expand in space. But even with that large size, the primary mirror is 6.5 meters across. It's smaller than some of the ground-based telescopes that we're familiar with using in our community. So, for example, the very large telescope out in Chile, the Keck telescopes, the Subaru telescopes, the Gemini telescopes are all bigger than the James Webb Space Telescope, but they're on the ground, they're on Earth. So Earth-based telescopes are always going to be challenged looking through the turbulent atmosphere, prone to cloud cover, as we've seen during the H3 Plus observations today. Whereas James Webb cuts through all of that, albeit with a lower spatial resolution. So the things that we're going to be doing for the ice giants, for Uranus and Neptune in particular, we in Leicester have guaranteed time observations planned, which means it's going to happen at some point next year, to observe the atmospheres of both worlds, complete global map, in as many frequencies of light as we can possibly get our hands on, all the way from the near infrared, which sounds the clouds and the composition of the cloud decks, all the way through to the mid-infrared, which sounds the temperature and chemistry of the atmosphere, along the way picking up the sort of H3 Plus observations that yourself and Emma are interested in. So I won't labour the point anymore, but just say watch this space for the JWST. Those spectra are going to be of exquisite quality, and we're really looking forward to seeing them.
Great, thank you. We have a question from Chris Lee asking, how can we get to the ice giants more quickly, and what do future technologies hold that could speed up the journey?
Yeah, so obviously we're talking at the moment about conventional rockets, things that are available for us today if we wanted to get a launch slot. And in most of those cases, we're talking about needing that Jupiter gravity assist to do it. However, there is the push towards larger rockets that would be able to take much more fuel and be able to get out to their destination, therefore faster. Because the more fuel you take with you, the more mass you can then slow down as you're trying to get into orbit around the system later on. So, for example, the SLS, which has been developed in the US, you can also take existing rockets and add future further stages on top of those rockets to increase the amount of power you can use to get out to those distant destinations. However, we're still limited by celestial mechanics, because even with those large rockets, okay, that maybe take a direct trajectory out to something like Uranus and Neptune, you're still talking about 15 to 20 years in terms of Neptune timeline before you even get there. So for a community that's used to designing missions maybe for Venus and for Mars, or potentially even the Bepi-Colombo mission to Mercury, these are things that happen on, or they can get to their destinations much faster than you can ever do with a ice giant system. So we need to change our mindsets just a little bit and recognize that it's all going to be worth the wait when it happens.
Yeah, there's a certain frustration for people like me that we know that we'll be retiring when any of these missions start to happen. But that just tells you how important it is that, you know, people watching now that might not even have gone to university yet could be the key people running these missions when they're actually taking data, which is absolutely maybe a hopeful message.
The story of Cassini actually goes down quite well on this front, because I was born at about the same time as the Cassini mission was first formulated as an idea back in the late 70s, early 80s, and I was in school as a teenager when it was being actually built on both sides of the Atlantic, and then I was just about doing my A-levels when it was launched. So, you know, these are real lifelong missions. It only came to an end then 5 years ago, and something like an ice giant mission will have the same long duration, I think.
Yeah, definitely. There's a lot of discussion about possible technologies, and we always have to be very careful, of course, because when we're proposing these missions, we want to make sure they will actually happen. But I'm sure we've all been watching the work of SpaceX and these big new rockets that are being developed. We can't rely on them yet, so we can't use them to plan these missions. But once they come online and start proving themselves, I think it will change a lot about what we perceive as being doable.
Yeah, there's a risk aversion, isn't there? Whenever you're talking about spending lots and lots of money, you try to go for tried and tested technology, which often means that you're using technologies that are a few years behind where you would hope them to be. There's no shortage of great ideas out there for doing things faster, doing things with less mass, novel instrumentation, for example. But you'll find when these are large strategic level flagship class missions tend to go for heritage instrumentation, heritage techniques in order to get it done in the least risky way possible. You would hate to see choices that we make now then hamstring us years in the future, but who knows?
Really great. I'm looking to see whether there are any more questions. Emma, do you see any questions?
I saw we have 2 questions from 2 people on our wonderful HT Plus team. We also have one on YouTube. I was just going to touch on that, which I think have somebody asking to clarify on the Vasmir engine. VASMIR, Vasmir engine.
Sorry, that one's completely beyond me. I think that would have to be an internet search.
Okay, no, that's totally fine. No worries.
I mean, it is interesting. There's a lot of these ideas. I mean, certainly there's been ideas about ion engines and things like that could certainly shorten. But as you say, I mean, ultimately we are stymied by vast distances in space, and there's only so much you can do. The faster that you get there, the more you have to slow down once you arrive, and there's only so much physics that we can throw at the problem before we just start breaking things. So.
Exactly.
So I see a question on here from one of your H3 Plus colleagues, from Henrik. Should we go to Uranus or Neptune?
I wasn't going to ask that. I thought that was a little mean.
Well, as I think I tried to point out in the presentation, there are very, very compelling regions to go to either one of them. Okay, if you want to study Triton, of course, you have to go to Neptune. If you want to study a classical collection of ocean worlds, you want to go to Uranus. If you want to study the most extreme place in the solar system, you go to Uranus. If you want a more typical ice giant, you go to Neptune. Let me say this loud and clear. Whichever target the space agencies decide they're going to go to, the planetary community, the exoplanetary community, the heliophysics community, the general public will all be excited about it. So either, both, whichever, doesn't matter.
I have perhaps a cheeky question to ask, because I have a couple of friends who are also listening in and are messaging me very kindly, are backing me up and letting me know it's going okay. But I've had one of them ask, I would say a really good question on this, which is, what is the difference, I guess, especially with ice giants, between having a rocket or an orbiter around the planet versus actually sending a probe into a planet? So I guess in similar way that when Cassini finished off, we sent Cassini into Saturn to get the final readings as close as we could. But yeah, I think the main thing is like, what's the difference? I think I have understood that correctly.
It's a good question.
For those approaches.
It's a good question. All of those various approaches have been studied in the past few years to see which architecture is not only doable but also going to deliver the biggest bang for your buck. Okay. Now, flyby mission like the one we had with Voyager 2 simply wouldn't really be justifiable at the moment in terms of trying to deliver on the scientific questions that we have about these two worlds. Okay, you might be able to see one single destination, but you certainly wouldn't be able to study its evolution over spans of time. So what you can do then is you can send an orbiter around each of these worlds. That orbiter can last for 2 to 4, maybe longer years. And that's, whilst it's there, it's taking all of its remote sensing observations. It's studying the atmosphere, studying the satellites, studying the rings. It's also measuring the gravitational field of something like Uranus or Neptune. And it's able to measure the magnetic field of something like Uranus and Neptune, the kind of thing that you can't do really from just a single flyby mission. That's kind of a must, I think, for this next step. But then you mentioned about an actual probe into one of these worlds, so either Uranus or Neptune. And I think that is essential, okay, because there are several things you cannot do remotely. You can't sense the individual gaseous species that are present down below the clouds, for example, not without tremendous challenges. And you can't, there are some gases which you simply cannot detect in infrared spectroscopy. You need to actually have a mass spectrometer in there sucking in the gases and trying to detect what's there. So having something like the Galileo probe, which descends under parachute through the cloud decks of either Neptune or Uranus, will really give us a great handle on what these worlds are made of. And go back to that big question I raised at the beginning, we still don't know whether these worlds truly are icy. And by measuring the bulk composition, we'll be able to crack that particular nut. So you do need an orbiter, and we should send a probe along with the orbiter.
Wonderful. Thank you very much, Lee.
That sort of resolves a question that came up on YouTube to some degree. But Astro Dave talks about how Voyager went to both. So is that something we could do again?
So there has been some really cool ideas out there of having one launch with two spacecraft on, both use the same Jupiter gravity assist, but then just tweak their trajectories slightly. One goes to Uranus, one goes to Neptune. And of course, if you're designing two identical spacecraft, it's not as expensive as designing two very different spacecraft. So I think there is some mileage in that. The problem is the price tags associated with them. Okay, so the scale of the cost is commensurate with the challenge and the scientific potential of this particular one. And you could have a flyby of Uranus and Neptune again, like we did with Voyager, but you'd have to wait at least another century and a half for them to all be in the right place, like the Voyager, the classic Jupiter, Saturn, Uranus, Neptune trajectory. They only come around once every 175 years, I think it is.
Yeah, absolutely. So incredibly lucky that we were sending these first probes out at the perfect time.
Yeah, and I think the story goes that there was a postdoc at JPL who was doing these calculations on the back of the envelope and sort of, wow, saw this particular conjunction taking place and went to tell his superiors, who initially went, go and check your calculations again. But it turned out he was right, and the Voyager missions really kick-started our exploration of the outer solar system, and everything we've done in Leicester, for example, since all of our involvement in the Juno, Cassini, other missions as well, has all stemmed from those first questions from Voyager being answered then by later spacecraft.
Exactly. Wonderful. Thank you. I realize we are at 10 to 2. I don't know, because at the moment we have a slight section in our schedule for Q&A with the HT Plus team. Obviously, we appreciate if you have any time to spare with us, Lee. We can continue doing Q&A, but we do appreciate you have your own teaching and whatnot today. So obviously, we don't want to keep you for too long.
I can certainly stay for another 10 minutes, and then we can go through other questions.
Awesome. Tom, did you want to take the next question? I spotted, I think we've
Sure.
got one or two on YouTube, and then
Fernando
we have
was
another
asked
colleague.
on YouTube whether it's possible to send a rover-like probe to serve as a base station on Triton or Ariel.
So have a rover on the surface of one of these satellites as a base station. I'm not so sure, but it's certainly possible to have some landed element on the surface of an icy satellite. The challenge is with this that we can all be forgiven for thinking about things like the Huygens lander on Titan, for example, which obviously did fantastic work. But the beauty of that was you had a really nice thick atmosphere to slow you down with a parachute so that you could then land somehow on the surface without having to take massive great amount of fuel with you to slow yourself down. Any landed element on an icy satellite, and the same is true of the Jovian system, versus the Uranian and Neptunian system, you have to take that fuel with you, and it all adds mass. And so if you have to add mass for fuel for a lander, you got to take mass away somewhere else, and that might be someone's favorite scientific H3 plus detecting instrument, for example. So that's a real difficult one. And there has been some interesting ideas of, well, what if you don't slow down? What if you just send a ballistic impact, basically an enormous bullet with a few devices on to crash into the surface of Triton or of Ariel and then communicate its finding back? And I think we could certainly do those, but it's all over so fast, right?
Yeah.
I'm not quite sure it's as satisfying as having a rover having a ballistic projectile like that.
Yeah, it's fascinating. I think I think we should be aware that you have a certain bias, right? So your demands that there has to be a lander, there has to be a probe that goes into the atmosphere of these giant planets. Well, I would not disagree with that, but I have a similar bias. And there are other people within our community that argue as vociferously for some form of lander on a large moon like Triton. And I think you're right. All of these things are achievable. We've done all of these kinds of missions. So, yes, Titan was easier because of the thick atmosphere, but we've managed it on Mars before. There are plans to land on one of the moons of Mars, which have very low gravity. All of this is within scope of technology, but it's whether it's within scope of finance, and as always, it's the finance that limits what we can do.
I like to think as well about, the ice giants were at the stage of that initial reconnaissance, aren't we? Talking about landers on Europa or something to get onto Enceladus, for example, makes sense because we've had, or by the time we get to those things, we'll have had very detailed orbital characterization of the terrain, of the environment. We've done as much as we can remotely. Whereas talking about that for Uranus and Neptune and their satellite systems right now feels like we're going too many steps at once. We need to complete our initial characterization of the whole solar system.
Absolutely.
And that's where the orbital science comes in. And of course, when agencies are talking to each other, when you've got participation, not just from one agency, but multiple agencies, it opens the door to these clever ideas that can fly alongside you. Another one we haven't spoken about is having some kind of CubeSat element or small spacecraft, because when you're talking about the magnetic field environment, multi-point measurements simultaneous in that system tell you so much more than single point measurements. But there you've got the same issues of communications and of power. How do you keep those things powered? Maybe batteries would work after charging it up in the first place. But there's no shortage of clever ideas. But as we said before, I think slight risk aversion will mean that the first big missions we get to Uranus and Neptune will be not dissimilar to the kind of flagship style Cassini-esque missions that we saw in the last decade.
These are the first steps that we're making towards understanding a class of world that we currently think is probably the most common worlds in the galaxy, at least the ones that we've been able to detect so far. And if you think about what we haven't stopped looking at Earth, we have literally hundreds, if not thousands, of satellites now measuring and attempting to understand and characterize the Earth as a planet. And there are huge new fields opening up in terms of those observations. So, in terms of the magnetic fields, we've had multiple spacecraft missions like Cluster and Themis that have done all sorts of detailed measurements. And the Earth, for all its graces, is a fairly uncomplicated place when you compare it to something like Uranus, especially the magnetic fields, or the weather systems are uncomplex compared to gas giants and to Neptune, certainly. So there is no reason why in the future, when money becomes available, we shouldn't have 10 or 50 or 100 spacecraft all orbiting, giving us information, and we will still struggle to understand the details of everything. But at the moment, we know almost nothing. We are very much at the cusp of any understanding about these places.
I think we're doing a tremendous job with the tools that we have available right now, which is, that brings it back to these long-term studies of how the atmosphere and ionosphere are changing that we can do from ground-based facilities. And that's been your bread and butter and my bread and butter for several years now, is filling the gap between these enormous missions by doing long-term programs on great facilities like the IRTF in Hawaii. We can't do everything from those facilities, but we certainly are doing some cutting edge science with the data that we're pulling back from them. And it's raising questions that one day we'll say we need a mission to those destinations to go and answer them.
Definitely. Well, thank you so much for spending your time with us, Lee. It's been fascinating. I'm sure everyone has gained a huge insight in. Hopefully everyone who's been listening will now go out into the world and tell them of the importance of a mission to either Uranus or Neptune, and not one or the other, but whichever. Absolutely.
So best of luck to all of you. I hope you have clear skies for the next few days, and I'll be listening along every now and then with interest. So take care.
Awesome.
Thanks, Lee.
Thank you, Lee.
Take care. Bye-bye.
Bye. Awesome. So we are now 4 minutes to 2 here in the UK. Let me just see if I can get my camera back up on the main Zoom call. There we go. And I will just pin. There we go. So hopefully that is pinning the main one. I don't know how to quite spotlight my specific one. Hopefully you can see that in the background. We'll find out.
I have pinned it and we can now see things again, I think.
There we go. So we're now at the section. We're now at the section where we are, I believe we're a bit of a kind of what we feel like doing. So I think we're doing a bit of a Q&A section with the H3 Plus team. But before I do that, I do want to introduce, we have another member from the H3 Plus team who has been very patiently waiting in the sidelines. We have Dr. Rosie Johnson. Hello, can you hear us?
Hello.
Hello, Rosie. It's nice to see you.
Nice to see you both.
Thank you very much for coming. If you don't mind, I'll introduce you a bit so that everyone kind of is aware. So Rosie is was one of Tom's students who did their PhD specifically looking at Jupiter's auroras, looking at how the solar wind interacts with Jupiter's magnetosphere. So something very similar to what I'm doing, but at Uranus, and well, I'm doing Uranus and Rosie did it at Jupiter. Outside of that, Rosie is currently an associate lecturer, if I remember correctly.
Yeah.
At Aberystwyth University, and has been in the past the education officer, wasn't it, for
the Royal Society of
Chemistry, which helps with all school teachers who teach chemistry across Wales. So yes, I'm sure we're going to be incredibly enlightened. It'll be nice to hear from your perspective. I know that we've had a couple of discussions about looking at velocities on Uranus as a possible concept with H2+. So it'd be great to have your insight on any kind of questions we get thrown our way. I should also highlight, if we have any schools, that would be great. If they are in the Zoom or on YouTube, it would be really great to hear from any schools that have any questions for us about any of the work that we're doing today, about Uranus, about looking at infrared auroras, about the whole space. That'd be absolutely great. I shall stop the talking there, and we'll have a look to see if there've been any questions. Otherwise, I'm very happy to move on to an update.
So I don't see any fresh questions coming up, but I think it would be really good if you could just give us a brief update of what's going on in terms of the observations right now.
Of course. So what's going on at the moment is, well, I should first kind of point out, I put a red circle. Now, frustratingly, the signal's gone again, I think. But when I was last looking at our cameras, I could faintly see just here in the corner. I don't know if I can move it a bit better. But in this corner, I was seeing possibly another line coming through, but it is incredibly faint, and that might be just me hoping that there's a line. So
I think I see it too.
It's faintly there. We get very excited with H2+ if we can see another line coming through.
Just like on the other side of like the green arrow, on the left-hand side of it. Obviously, people who are viewing through the tinier windows might not be able to see.
Oh, there you go. Yeah. There it is. If you want to move it back slightly, I think I could see it over on the left-hand side a bit more. There's one there too. Yeah.
I believe that's
I mean, I don't think anyone watching will believe us, but the joy of this job is that you tend to spare hours and hours staring at screen, hoping that something will appear, and so you get very good at being in believing you can see something, even if maybe you can't. But I'm very convinced that we're seeing something right where you're pointing there. Definitely.
It's a good part. In terms of cloud and anything, I haven't heard anything, but I haven't checked in with Nahid and Riyang to see if there's been any dramatic updates on that side.
So looking at the webcam right now, there's some really useful webcams available, and one of the ones that I really like is one that points upwards and then subtracts what it saw about 5 minutes earlier from what it sees now. And basically, it's very boring unless something is in the sky, and there is a bank of cloud somewhere up in the north, which is good for us because we're sort of looking from east to west as the planet switches over. So we might hit something as we move right down into the planet's setting, but usually observations down there are pretty messy.
Yeah.
But right overhead at the moment, there's no cloud at all. It's a beautiful, clear night.
We'll keep our fingers crossed, certainly that it continues to be so. I should probably stress with these observations, the useful thing is, and I suppose it's something that I haven't done before, is that we are trying to fully map across or around the whole planet itself. So every minute that we can get information from Uranus is incredibly helpful as it basically produces a more detailed and much fuller map as an end result, giving us probably the best map of the infrared aurora at Uranus that we've probably had in the last 20 to 30 years. So that's the major update, that we have another line. I suppose that's the big news flash. Other fun news flash is, after a bit of fiddling, I finally have a still image of the sky above IRTF. I think this is from about 2-3 hours ago. So again, that's probably changed since, but it's better than the sky that I was just getting beforehand, which is clouds. I do have, if I flash back to, I got rid of the background on that one, my apologies. Yeah, I still have the GIFs going on if people would like to see those instead. So a bit more stuff going on, I suppose.
I always like the GIF of inside IRTF. Because at the start it looks like a robot, and it's like, oh, I'm ready to observe.
Yeah, it just moves on its own, almost looks like.
Yeah, like this bit. It's like, yeah. What's it doing?
Exactly. So I'm just having a quick check. So we have a couple of questions. Which frequency is being used in the spectrocam? Okay, that's a good question. If we're okay, I'll take that one. So there is a frequency, but we tend to refer to things in wavelengths. So at the moment in the spectrocam, it's difficult to say the exact, but we're about 3.94 microns for the spectra. Yes, about 3.9 to about 4 microns. The exact points would take me a little bit to figure out on this, but we are using what's known as the LP3 filter on iShell. This filter just basically goes, okay, from where to where do you want to take light in from? So do you want to look between 3 to 4 microns? Do you want to look between 1 to 5? And whatever you decide to pick is what the filter name, or whatever filter you're going to pick for that night. But yeah, for these ones specifically, it's 3.9 to about 4 microns. We have another question.
So Emma, I'm going to follow up on that. Why 3.9 to 4 microns? What's special about that wavelength that gives us really good observations?
Oh no, I feel like I'm in the middle of
this is your Viva exam.
Yeah, Viva exam. Exactly. Oh dear. Well, the main reason for Uranus we go for 3.9 to 4 is what's known as the Q branch. But that gets a bit too specific. The brightest emissions we get from Uranus from the H2 plus molecule can be found between about 3.9 to about 4. But as they're called that Q branch more scientifically. So at other planets, it's a little bit different. I know I think it's either the Jupiter or Saturn, because of the methane, which kind of just blots out a lot of the light that we get from the planet. We have to use other wavelengths. So we have to use, I think, longer or shorter. I may need Tom to guarantee on that one.
Yeah. Well, I mean, we have another expert in the room, but I think let's move this away from an exam question for you. Rosie, maybe you want to talk a little bit about why we're only seeing like a vertical line, and why we're not seeing any light elsewhere, and also why can we look at this wavelength from Earth? Why can we see it at all?
Yeah, that's pretty handy. That we can see our favorite spectral emission lines from Earth, and it's all to do with like this atmospheric window. So the Earth's atmosphere, it absorbs different wavelengths of light, which does help us out in our day-to-day lives, that, you know, we're not zapped by particularly harmful wavelengths of light. But then I guess that means the X-ray observers, they get a bit annoyed that they can't just observe from the ground like us infrared people. So we're pretty lucky that we have this, we call it like an atmospheric window. So this wavelength of light can come all the way down to the Earth's surface, so we can observe at this wavelength. Yes.
And I mean, why can we only see those H3 plus lines? Why is it everything else so blank? I don't know if you'll know this because this is Uranus rather than your specialty.
Is this my Viber now? But now I'm.
This is now your Viber.
Getting flashback.
I mean, to talk about what you see and when you look at Jupiter in this way.
Yeah, well, at Jupiter there's like quite a lot of like reflected sunlight and stuff, but that depends on like which wavelength, because obviously, like, so Emma's zoomed in on this part of the spectra because obviously this is the most exciting part because we've got our lovely emission lines. But then one of the big differences when we observe Jupiter, like the whole spectra will be lit up with lines because Jupiter's, I don't know, I want to say better, but no, I'm joking. I want to make sure I stay friends with everyone here. No. Yeah, so I think Henrik said like a while ago, so like in 30 seconds at Jupiter, we get all this like emission from Jupiter, but at Uranus it takes like so much longer to build up the signal, and Jupiter's aurora is so super powerful. We get like a whole bunch of like emission lines, but then also next to our emission lines we also have this like reflected sunlight stuff, and I'm wondering if that's what Tom is wanting me to say. Sometimes at Jupiter that reflected sunlight's like a little annoying because then it kind of gets involved with the emission lines, but maybe it's different here at Uranus.
It is different here at Uranus. Basically, Uranus is incredibly dark in the infrared. So whereas you'd be used to seeing some reflected sunlight, and if we were looking at Saturn right now, those lines that have been highlighted with the orange, with the green square would not even be seen because the reflected sunlight would be so bright it would swamp them completely. Uranus is this incredibly deep methane atmosphere, lots of hydrocarbons, and basically completely absorb all the sunlight in this wavelength. So if we take images of Uranus, they can often get very dark indeed, and it's much harder to see what's going on than something like Uranus, Jupiter or Saturn. Jupiter has a nice sort of interim balance between having some reflected sunlight but not too much, so you can tell where you are. You can see lots of interesting structure from the lower atmosphere. So the image that we have here is incredibly boring to someone like Lee. Lee would loathe this picture because he can't see anything, and in fact that's one of the difficulties with observing Uranus, is that it's so dark and it's so absorbing that it's really tricky to get good information about what the spectra looks like in this sort of near infrared. So that's why they have to move towards more mid-infrared, something longer wavelength, and that's especially why James Webb is going to be so powerful, because James Webb has a sensitivity about 1,000 times as high as what we're looking at now. So if they observe for 1 second, they get the equivalent of 1,000 seconds of our observation. So first of all, lots of things will come out more clearly, but also you have a lot of mid-infrared observations, and those can be done from Earth, but they're much harder because those absorption windows you talked about, basically as you look up into space in the visible, we can see space very clearly laid out, and we're at this wavelength looking through another window in the infrared, but there's whole regions where the Earth's atmosphere is absorbing infrared, and that's global warming right there. It's the absorption of the infrared light, and so that prevents us doing these observations. And in the mid-infrared, those windows are even narrower. There's only a few narrow regions where you can look through, and lots where there's huge absorption. And that's one of the big things that James Webb will be doing, is getting above that atmosphere so we can see all of this stuff as it comes in.
So how do you think the data from James Webb will look different to this data?
So James Webb,
everyone is always saying like, oh, it's going to be better, it's going to be cooler and stuff. And so how are these like
James
shiny
Webb is
lines
amazing,
going to look?
But you have to be realistic with your limitations. James Webb can do some things vastly better than ground-based telescopes, and so other things not as well. So James Webb has a lower spectral resolution than this by a factor of at least 10. So basically all of the spectral lines we're seeing will be smeared out by a factor of 10. So for Uranus, that won't matter because you could see them very clearly with no background. But for Saturn, that makes things more tricky for sure. But mostly it is just the sensitivity. The Earth's atmosphere just absorbs a lot of light. Even in those windows that we think of as transparent, it's soaking up a lot. And so we look through the Earth's atmosphere, and when we look at something like Uranus, this is a corrected image already that we're seeing. The spectra we're seeing here are where we've taken one frame and subtracted another to get rid of the Earth. The Earth completely dominates at this wavelength in terms of brightness for almost everything except maybe Jupiter. That won't be true. In fact, will be L2. And so just even though it's a smaller dish, and it's a bigger dish than the IRTF, by the way, you know, the James Webb Space Telescope is bigger than the IRTF, so it will gather more like than the IRTF, but it is significantly smaller than the largest telescopes in the world. But what it does is just allow us that massive increase in sensitivity. So Keck is the largest telescope in the world. It used to be the clear largest. Now there's lots of caveats and asterisks on everything because there's all sorts of different kinds of similarly sized telescope, but it's basically the same kind of size as the largest telescopes we have now. It's incredible sensitivity. It's got at least 10 times the sensitivity of IRTF in terms of its gathering of light, but it's 100th what we will see from James Webb. So James Webb is just able to soak in light an incredible level, which is why it's so important for a lot of the deep space missions and you know probing the edges of the galaxy. But what we see here is that, you know, when we're looking at these planets, we're looking at this thin transient layer of the atmosphere that's well above the bottom of the planet, and it is often very hard to see anything from these worlds. And you know, here we're taking data, we're trying to understand it. If we have adaptive optics switched on and we have a really big telescope, we're able to get much better sensitivity. So the very best images that you see from Keck, for instance, like those Lee showed a little bit ago, you could see beautiful bands of weather on Neptune, for instance. We won't get that level of sensitivity in terms of the resolution. We won't be able to see those weather bands as accurately just because the telescope is smaller. But the depth of the measurements that we can get, and especially with the wavelength coverage, will be profoundly better. So my hope is that for Uranus, we can see there's these beautiful bright emission lines. We see these transient aurora that seem to pop in and out. We maybe saw a few of that earlier on tonight. We saw some brightening on one edge and not the other. And so if you take that and you times it by 1,000, the potential is that we'll be able to clearly see the aurora for the first time. The hope that I have is that in a single image, we will resolve out a whole new auroral structure that we've never really been able to see anywhere from Earth with Hubble or with any of the ground-based telescopes. And it should just be very clear what's happening. And we should have the first ever mapping out of what the magnetic field lines of Uranus look like in detail. That might not happen. Maybe the aurora are much less interesting than we think, and we will see nothing. But that in itself will be really interesting, because it will tell us something important about whether our constraints and understanding of these aurora is realistic. But everything that we've done from these observations on the Earth are priming us for that. And what they're priming us into is a belief that at least at some points there are really very bright aurora in the infrared. We see a few bright sparks and spots from Hubble, but the indication is that they should be much clearer in the infrared than they are in the UV, which is something that you guys are used to in terms of Jupiter observations. We can never see the brilliant bright arcs of emission that you see from Hubble as clearly in the infrared, but we see the weak stuff that is, all of the stuff that's sputtering in the polar region much more clearly in the infrared than you do typically in the UV. So I see a question from Ben Stokes asking what the shortest wavelength James Webb Space Telescope will still be able to detect. I keep looking this up. I may have this wrong, but I'm fairly sure in terms of the science instrumentation, it comes down to about 1 micron. So it's all beyond the visible. It's infrared at the nearest level outwards. So it's able to go out to very long wavelengths, but it's certainly not good. I don't believe it has any visible instrumentation. So people often talk about Hubble being replaced by James Webb, and nothing could be further from the truth. There's almost no overlap between the two spacecraft. One, Hubble has been focused largely on visible and UV observations. They had a few infrared instruments at times, but generally speaking, it's this higher energy stuff, that gives us these beautiful images of the aurora of Jupiter, for instance. Whereas James Webb is focused much more on the long wavelengths, which at its core are super important for answering and understanding the early universe, because the early universe light comes to us significantly redshifted. People always talk about redshift, but it's a real, redshifting. So things that were in the UV vastly far in the distant past have shifted into the red far enough that you can see them in the infrared now. So that's why there's such a keen interest in it.
Awesome. Thank you, Tom. I think that's answered that one. I don't know if we have any more questions, so we could probably just shoot each other questions. I mean, I was going to highlight on both YouTube and Zoom, don't feel you have to ask scientific questions. This can be just a QA as well on just, why we went into observing with HC Plus or why we went into physics. If there's any questions academically people want to ask, I don't know. I'm happy to answer. I don't know if Tom and Brizzy are also happy to answer on that side of things.
Absolutely.
So ask how the weather is.
Askadir asked a question about the mirrors on the James Webb, which is an interesting question. It's clearly got a golden yellow hue to the mirrors, and they ask whether there is a compensation needed. I'm not sure the answer to that, but my feeling is that it's likely that those are colored in a way that is allowing the best possible reflection in the infrared rather than in the visible. So we're not interested in how the light reflects off of it in the visible, because that's not what we're measuring. The aim is ultimately to get the best possible reflectance. There will always be compensation. So we should say that all of the data that we're taking now is not perfect, and we are taking calibration data at the starts of the night in order to combine the data afterwards in a more scientific way, so that we can correct for the fact that there's hue differences in the different colors that we see spread throughout the spectra. And so similar things will be done there. But there's always a trade-off with things like space missions, because you want to make sure that you've got the best transmission possible, but it also has to be a material that can fly in space and not be destroyed by high energy particles as they zip through your machine. We're very used on Earth to not have to worry about high energy particles, because we've got this wonderful thick atmosphere around us that absorbs all of that. But there are such concerns when you're out, especially over at L2, where you may not even be inside the magnetosphere of Earth.
We've got another question here. When you planned the observations, did you have to check for stars in the field of view, or is this too unlikely to worry about? And I remember thinking this question when I first did my observations when I was doing my PhD. So Emma, did you have to check for stars?
It's a good question. I mean, I did have to check for calibration stars. Those are always the must. I think we're just basically saying, obviously, that's what you got to do at the beginning of your data so that you have a comparison rather than going, oh, it was about 5 CCD counts, which doesn't really mean much to anyone. But in terms of stars actually coming over and possibly like, I guess the question is just if there's stars in the background that will kind of oversaturate your image. That's a good question. I know with the Keck data that I've been working with back in 2006, a star does appear in the bottom. I would say it is what I'd need to worry about is if the star interacted with the slit than anything in the background. Typically, you won't have a star in front of Uranus unless you're specifically looking at the sun. So that situation shouldn't
in front of Uranus.
Yeah, exactly.
You definitely want to check for the sun.
Yeah, exactly. But that's not to say there couldn't be stars in the background. It certainly does happen. I hadn't looked specifically at this one to see if we may have a star in the background.
Yeah. I mean, something we've not traditionally done for IRTF, and that's one of the big jumps that I found going to Keck, was that you basically can't check for the stars. When you look at the images that you see, and if you look at the catalog, they don't come up. I think nowadays with Gaia there are no stars that you could ever see that won't come up because there's billions of them now. But we wouldn't see an obvious star. Obviously, if there's something really clearly in the way, we might try something different. But when you look at the spectral data, you often see weird striations in your data, and I'm convinced that often those are stars moving in and out of the frame of view. One way around it is to take long periods of data like this. And of course, Uranus is moving relative to the background. So any stars that happen to be in our slit will be moving in and out of the slit. And so as we add up over longer periods of time, they should blend out. I would say that there's something we don't check, and we probably should check more, but we don't think about it because generally speaking, the planets sit in front of stars anyway. So it's not that the stars will ever get in the way of our observations. I did once not check whether the moon was going to get in the way of one of our observations, and I was observing Saturn, and then the guide camera started crashing because it couldn't guide on Saturn anymore, and then we realized it was because Saturn was moving behind the moon, which doesn't happen very often, but somehow I'd managed to time our observations to coincide with a conjunction between Saturn and the moon, and the moon actually got in the way of observations. So that was a little embarrassing, but it was at the end of the night, so I didn't worry about it too much.
Got another question. So how much did the telescope cost and how does it work?
That's a really interesting question that's got a lot in it, right? So there's two costs to a telescope. One is how much it costs to build the telescope, and the other is how much it costs to run the telescope. So, for instance, the UK used to have a telescope on Mauna Kea, and we built it. We spent all the money building it, but we couldn't pay the continuing running costs, and so we sold it for a very small amount of money to someone else. The IRTF was funded basically out of what is described as pocket change from the Voyager missions. So the Voyager mission was built to investigate the planets around in the outer solar system, and that had a budget of billions. There was an amount left in the budget, left at the final stages of the mission. I can't remember the specific numbers, but it was in the range of $100 million, something like that. Which was then used to build the IRTF. And that's the reason why we continue to use this telescope to look at places like Uranus and Neptune, because it's the only telescope that I'm aware of in the world that has a dedicated remit to looking at solar system science. So at least 50% of all the observations it takes has to be of objects inside of our solar system, which means that for us, for these long-term monitoring campaigns and where we want to go back again and again, it's really useful resource for that. And in terms of how much it costs on an ongoing basis, that very much ties in with the question of how it works, because all we're doing is sitting and using those instruments from our houses in the UK, but there's a very significant staff that work to maintain these telescopes. So there's a director, a sub-director, there are a whole slew of support astronomers that support the observations. If it's a new technique that you're using, you can call up on those and get them to help you with the observations. Then there is a whole slew of engineers that work daily up at the telescope. You have the support, the telescope operator support. So there's always at least one person on site. So right now at the summit of Mauna Kea, we have a telescope operator supporting our observations sitting in the control room. Then you have machinists who build the instrumentation and maintain the telescope. You have computer technologic people who are running all of the backbone data management and running the website, running everything like that. Then you have, all the admin staff that monitor and maintain all of these people. It becomes a very large enterprise, and that means that even a small telescope like this has a very significant running cost, which is why these things are so competitive. We all want time and access to these telescopes, but there's only so many telescopes you can build in the world of this caliber because they cost so much to run. So we are beholden, as always, to a fantastic effort on the part of a huge range of different engineers and scientists, mostly based in Hawaii, that continue to maintain these telescopes and do an absolutely fantastic job in allowing us to literally just log in and start taking data.
Great, thanks, Tom. Hopefully that covers that question. I always remember I had to do some remote observing from a friend's house, and they wanted to know how much the cost was per minute of using this telescope. And they were like, can't believe you're using my Wi-Fi to connect this really expensive telescope.
Yeah, the classic number I remember, which is probably underselling the Keck now, it's probably more than that now, but it used to be the Keck was $1 a second to use.
Yeah. And then that makes you feel really powerful as an astronomer using it.
It makes you feel very guilty if you've missed something and you've done something wrong. You went for a coffee, it's a very expensive coffee,
Yeah. There's another question in the YouTube. So could James Webb Space Telescope detectors be damaged if they look directly at Sirius? And I think this is an interesting question because I remember asking you, Tom, about whether we can use James Webb Space Telescope to look at Jupiter, and Jupiter being pretty much too bright. So I just had a quick look, Sirius is minus 1.46, and then we've got Jupiter minus 2.9. So that's their magnitudes. I don't know whether there's going to be a difference because of the infrared or...
Yeah, it could be. There's always been concerns about that. I think that those concerns for the planets have been assuaged, and we have a really good understanding of what the spectral characteristics of the infrared spectrum, partly because there's a lot of absorption from methane. It damps down the brightness to some degree. Lee would also be someone that could have answered questions on that really well, I think, because he's looked into this more. But my feeling is probably not. I mean, you probably would be able to get away with looking at something like Sirius because it's going to give a fairly bright signal, but it's not as bright as Jupiter, for instance. What I do know that
in the infrared,
they're very concerned about the sun. So the real limitation is the directionality of the sun, and it's not just pointing directly at the sun. There's quite harsh limits on the range of angles you can look out into space from in order to ensure the heat from the sun never heats up the telescope. So that's a very strong limit on what you can do. I mean, there's classic stories about it. IRTF is a 3-meter telescope on Earth, and there is a telephone that people leave out as a warning now on the deck of the IRTF that has a melted line through it because they were opening the dome up and the mirror was pointing upwards, and so the light from the sun didn't hit it directly. Actually, the light hit off of the side of the dome onto the mirror and focused it down, and because it was a glancing light source, it didn't go straight into the telescope. It went off at an angle and basically melted in rather like a James Bond death ray. Wow. Melted its way through a telephone. So definitely something you need to be careful about. And I mean, you could never point something like this at the sun. It would literally melt the instruments.
Yeah, I remember with the Juno observations, obviously everyone is wanting to support the NASA Juno mission with observation, like observing Jupiter at the same time as Juno with IRTF. And I know there was some astronomers that were trying to work out how they could use the dome to sort of like, and the to kind of like shield from the sun. And I think maybe even like using the covers to try and so they could observe Jupiter for longer in the daytime. Because it is possible to observe bright sources like Jupiter in the infrared in the daytime. I did a bit of that, but it wasn't very good. You don't get a very lovely signal.
Very difficult to do.
Yeah. I didn't appreciate it, how difficult it was until I did it, and I was like, this is terrible. A bright, noisy sky. Someone saw something bright in the
yes, I was gonna touch up on this actually. Yeah, there's a bright object.
Did you work out what it was?
I haven't worked out what it is. I think I understand what they may be referring to. It'll be
bright thing coming up after Orion, because you can see Orion. Yeah. Is it this one? That one?
I believe, yeah, that may be what you're referring to. It's a good question. I don't know if it may just be an extraordinarily bright star, but it could also be. Well, I don't know if we're going to have any planets that would be that bright, but I would imagine perhaps a star in some sense. Trying to think how I could go about.
So pretty sure the dog star is there, Sirius, isn't it? I'm trying to remember my mythology. I'm pretty sure Sirius is the dog of Orion, the hunting dog. So over on the left you have Taurus, because it's the bull. So you often see the bull's eye. And that's the bull that Orion is hunting with his bow or his shield, depending on who you believe. And then he has his dog following him, because obviously he's hunting. And then obviously that is all entwined with his ever-going battle with Scorpio. So Scorpio always rises when Orion sets, and vice versa, because they are caught in a forever battle against each other.
Okay. This is the problem when you ask professional astronomers, like, what star is that? I don't know. When I observed the sky, I asked the telescope operator to lure the telescope to Jupiter.
We did we had Simon mention that it is Sirius, the belt stars point to Sirius, which you can just see beforehand. So thank you very much for that confirmation. Just trying to see, we have a.
So I should say that all of this information I've gained is not from any of the astronomy I've ever done as an astronomer, but because I've wandered down to the visitor center at Mauna Kea. So halfway up Mauna Kea, there is a visitor center very close to the dormitories we stay at, where they provide fantastic talks about the night sky. And so everything I know about the night sky comes from those wonderful stories.
Awesome. I spotted another question from Edwin Lanson, who asked a very good question, which is, would researching Uranus be useful for the future? I would say immensely useful. We've had Lee's talk mentioning about having orbiters and missions sent off to Uranus, but I guess this leads back to a point that I was making earlier, which is that Uranus and Neptune themselves are very fascinating planets from the fact that they are just so unusual. They have both rotational poles that are completely I wouldn't say completely on their side, but very much rotated from where we see the rest of the other planets in our solar system, which is already one unusual factor. They are incredibly far out in our solar system, and as we are finding in our research of just space in general, there are an incredible number of of exoplanets known as exoplanets, but sub-Neptune type planets, which are similar to Neptune in I guess I say configuration, but how they are. So any work that we can do here at Uranus and at Neptune will be immensely useful in understanding how those worlds work and what we could expect at those planets if we're looking at reaching out further and beyond our solar system. I don't know if that entirely encapsulated the point there, but as someone who's doing Uranus, I feel very strongly in that. Yeah, I feel that this is going to be immensely useful, and it would be a shame if we never managed to get something out to Uranus in the next 10 to 20 years. I don't know if Tom and Rosie, if you had anything that you wanted to add.
I mean, well said, basically. I think that, we could, the usefulness of these, of the work that we do in understanding these worlds is so broad. It's very difficult to answer a question like that. What I could say is we could answer that question for what we're doing right now. So we're looking at an aurora, or attempting to find an aurora at an ice giant, and that has a slew of different ways it could be interesting or useful. Earth has an aurora, and Earth has complex magnetic fields that stretch out into space, and they're dominated by processes that we understand fairly well. But there are all sorts of secondary processes that are obscured by those primary processes at Earth. And so being able to reflect on something like Uranus or Jupiter really gives us key indicators of what else is happening. It's giving us a different vantage point on the processes that happen on our own system. So in the case of Rosie's work at Jupiter, there's some really interesting work going on now, looking at the equatorial regions of Earth and showing how the magnetic fields interact with the ionosphere and the neutral atmosphere. And as we know, the neutral atmosphere of the Earth is, we consider very thick, but if you compare it to Jupiter, it's a blemish, nothingness. Jupiter has this vast neutral atmosphere. So when we look at Jupiter, we can see writ large what happens when the neutral atmosphere interacts with these magnetic fields. And there's so many surprising similarities between what we're starting to see at Jupiter and what you see in the Earth's neutral kind of coupling down near the equator. So we're in many ways, the observations we do at Jupiter are kind of leading and are ahead of what we understand from the Earth, because it's so much more tenuous at Earth. At the same time, Uranus is even more complicated. There's even more going on. And so that's going to tell us something else about both Jupiter and about Earth, I think. And then, as Lee talked about, there's this vast array of moons, of planets around other stars that have all sorts of diversity, but many of them seem to be somewhere between Earth and Uranus. So bracketing Earth and Uranus gives us an understanding of the differences. They must have aurora of some kind. They must have magnetic fields. And so in the future, we may detect the auroral signatures from these worlds. And the only way to understand that is by understanding what we see in our own solar system.
Awesome. Thank you. Thank you, Tom. I think we have... Well, we've had a lovely little discussion at the moment currently in YouTube about favorite planets, and we do appreciate that. I think, yeah, okay, that's interesting. We have a question from Wengriff going, would love to know what a typical day in the life of a Uranus spotting astronomer is like. I wonder if that's more a question for me.
I think it is.
Oh goodness, that's a good question. I mean, for PhD students in general, whether it's looking at Uranus or the gazillion other projects that I bump into PhD students with, we don't normally have typical days. Our typical day is quite all over the place. The last week has been a lot of me sorting out and scheduling and checking the observations. So that's making sure that I have the right coordinates, making sure how the weather is going to be on IRTF. And hopefully I will get the opportunity if I was in person, then prior to that would have been me flying out to Hawaii and then getting myself used to the time zones before then going up onto the actual telescope and getting more familiar with how it all works. But general day-to-day, I'm afraid it's quite boring. They're usually ending up going to Starbucks in the middle of the day to go get something to wake myself up. And otherwise, it's a lot of coding, a couple of emails as well will be thrown in there, but it's a lot of coding, a lot of trying to get the data from our code to understand what's going on at Uranus, and just the back and forth of arguing with your coding until it works, and then you change one thing and then it breaks and then it works again. So it can be quite different day to day, but I'd say there's a lot of code, a lot of getting drinks, depending on which PhD students. We're getting a lot of drinks, and a lot of talking with people, which has been, I think, one of the great parts I've really enjoyed with the PhD is getting a broader idea of how all science kind of interconnects. You'll have one PhD student, like we have our own journal clubs that we all go to every Tuesday, where all the PhD students will come along and discuss a topic that they are doing from a paper or from a journal specifically. And in that time, we will mention really interesting things. I know the last one was trying to chat with brain because it's on Tuesday. We had discussions about looking at H3+, but at Jupiter and Saturn. We've had discussions on the moons of Jupiter and how they've been trying to discern the percentage of water within the ice. I believe that was correct. We've also had discussions about Earth's magnetic field, looking at how the current systems work within the magnetic field and the theories behind that. But the great thing has been looking at other people's work and going, hey, that looks similar to what I'm doing. And you end up having quite a long conversation about it, where originally at the start of it, you're like, oh, I wouldn't understand anything. But the more that you talk with people, the more you're like, actually, there's a lot that's interconnected in the wider space. So that's an overall day. Apologies, that was a long-winded version. A short-winded version is coding, food at some point, more coding, lots of emailing back and forth to people, a lot of good discussions, and group meetings, especially on Teams these days.
Yeah, I think it's interesting because, what is a typical astronomer looking at Uranus anyway? I think each of us has a different role in these observations in a different place that we work. And so my typical day is very different from yours, just because of, we all have a day job effectively. This is what we live for. The observations are why we want to do this job. And we have to pay the piper in different ways. So I do a lot of teaching, I do a lot of admin, I work a lot with making sure that the lives of PhD students like you are better, but both within the school as a whole and, across the university. So that's the job that, pays me money. And the joy that comes out of that is being able to do these observations, which is, the fun bit, basically. We had a question about whether it was Miranda we were seeing on the right, just below the slit. And yes. I had a look, and I'm fairly certain that it is Miranda just below the line.
Oh, okay, my apologies. I think we've been having a back and forth on whether it's Miranda or Puck. So yeah. I had answered that. That was Puck. My apologies.
Orientation is.
So the orientation's upside down compared to what we see on the sky, because Umbrel and Ariel are down at the bottom.
Yeah.
Oh. Okay, so if that's the bottom left is Umbro, and then above that's Ariel.
Yes,
I think so. Yeah.
Yes.
Then yeah, that should be Miranda.
I think it's either Miranda or just a star that happens to be in the field of view. One of those two.
Yeah.
Fairly certain it's Miranda because we've seen it since about 9 o'clock this morning.
Yeah. Cool. Miranda is off of. I think Uranus is looking slightly larger than it actually is because it's spreading out and we're cutting off the light. And so the actual disk of Uranus is probably slightly smaller than it appears to be in this image.
Sorry, thank you very much for taking that, Tom. I noticed we had another question from Edwin Lance. Sorry, it's my other half. It's okay, don't worry. Who asks, what's so unique about Uranus and can you gather gases from Uranus for human use? And they mentioned that they're 13 and find this stuff interesting, which I'm glad that we do. We're here to produce stuff that is interesting.
So, I mean, it's a good question. What makes Uranus so unique is partly what it's made of, for sure. It's a very different composition to either Earth or, Jupiter or Saturn, and probably somewhat similar to Neptune. They're probably somewhat twins from each other, but what makes Uranus so unique is not so much what it's made of, but how it faces the rest of the solar system. Pretty much all the planets in the solar system have a north pole that points up, and that's because of how planets were made in the solar system. Basically, the sun, and all the planets were made out of a big rotating disk of gas, and so everything was rotating around in the same plane, and bits and clumps broke off and formed into planets. And so, rather like spinning tops, everything is sort of pointing up in the same direction. So the Earth points in roughly the same direction as the rotational axis of the Sun, of Jupiter, and all of the other planets. So what a brilliant picture from James O'Donoghue here. So that really exemplifies that. So Venus is a bit odd, but we'll ignore Venus for now because it's something weird happened to Venus. And what you can see is that most of the rest of the planets of the solar system generally point in roughly the same direction, except for Uranus, which is tilted very dramatically over onto one side. And we don't know why that is. It's one of the big fundamental questions of Uranus. There's lots of theories, many of which talk about whether it was hit by some large object early in its formation. And that, I think, is probably the source of most of the oddity that we get from Uranus. And often people talk about, as Lee did in his talk, that maybe Neptune is a more typical icy world and Uranus is a special magical world of its own. It's very hard to know how common or uncommon these things are, but there certainly seems to be a general trend towards all of the planets having fairly similar pointing. But every planet has its own unique characteristics that make it just as interesting in many ways. Could you use the gases from Uranus for human use? Well, most of the gases are pretty common on Earth too, just not in quite as much supply. So we've certainly got access to things like methane, ammonia, all of the things that make up Uranus. One thing that we have less of maybe is helium. We don't have an awful lot of helium on Earth in comparison to some other places, and we usually use that by extracting hydrocarbons and using that as a guide for pulling out the helium. So maybe helium would be something that we could use that is unique. I think it would be hard to come up with an economic argument for going to Uranus in order to mine it for anything. But in terms of unique substances, it's an interesting question, and I'm not sure whether there's stuff that we could use there that is super unusual to Earth. Generally, there's not an awful lot in the solar system that is super unusual. We're all made of very similar stuff. So we have less hydrogen and helium, but we still have hydrogen and helium on Earth. And everything else in the solar system is basically made of the same elements. So largely the processes are fairly similar. In fact, Earth is pretty good at being unique. Earth does have a lot more stuff on it that none of the other planets do in comparison, because it has water, and water does magical things when it meets other chemistry. So, you know, if you look at a geologist's satchel and pull out rocks from a geologist's satchel, there'll be a huge array of different minerals that are unique to Earth, that are very unusual if you were to go to somewhere like Venus or Mars. But the opposite is not really true. If you go to the surface of Mars, nearly all of the rocks you'll find on the surface are basically very similar, at least in their composition, to what you see on Earth.
So we have a couple more questions. Maybe we'll go to this one first because it's kind of related, because you were talking about the different planets' orbits and stuff. So why did Uranus and Neptune change places as the solar system evolved?
Well, that's interesting, because I hadn't realized that there was a theory that they had swapped, but I'm not super au fait with the current theories of formation. But what I do know is that there are a lot of different theories that try and explain not only Uranus and Neptune as planets, but also where Uranus and Neptune sit, along with a huge array of other characteristics that we have from our solar system. What we do know is that you can run models that make solar systems not too dissimilar from ours, from, you know, statistical modeling of stuff being formed. And generally speaking, there is a huge bias towards planets forming similar in mass to the solar system, but never in the same positions. So generally speaking, you'll have a big planet around about somewhere between where Mars and Jupiter are right now. Then a second moon, second planet, maybe a bit like Saturn, somewhere similar, and then smaller ones further out, but they're always much closer in, so more like where Saturn is now. So there's this huge dichotomy, and that dichotomy ultimately comes out from our trying to explain exoplanets, because before the exoplanets were seen, most theories about planetary formation basically made planetary systems like they are now here in our solar system. But what we found is that there's these vast arrays of hot Jupiters around other planets, and all of these sub-Neptune worlds very close in. And, you know, certainly for the hot Jupiters, that doesn't make any sense at all. There's no theory that easily explains the formation of massive Jupiter worlds that close in, generally speaking. So people evoked these ideas that you could move planets around in the early solar system history. So you have migration happening, and in migration, you're moving stuff towards the star. And then the big question is, well, why didn't that happen to Jupiter? Why isn't Jupiter fallen all the way into the star? And there are theories that Jupiter and Saturn were moving in. Basically, Saturn caught Jupiter up and caused it to reverse its migration back out. And that's the grand tack theory that sort of sets up the initial framing of the solar system. But the grand tack ends with Uranus and Neptune fairly close in, certainly sort of maybe well within Uranus's radius. And so there are other theories like the Nice model that then try and evolve the system even further, and they move Uranus and Neptune further out. And I do have a vague memory of them swapping places in some of those models as well. And it's all to do with the dynamical interactions between these worlds. And how they are interacting not only with each other, but also the vast array of small stuff, rocks and pebbles and the like, strewn throughout the solar system. So in terms of orbital resonance, you can sometimes have the interchange of two bodies, and they can swap their orbital location. There's some wonderful examples of that in our solar system. So if you look, basically always look at Saturn's rings, because Saturn's rings are fascinating and explore. All you need to explain all orbital dynamics is a deep understanding of Saturn's rings, because everything that you might expect to happen happens somewhere there. And there's at least one example of two moons that are in a resonant orbit with each other, where one is further out than the other, and then they start orbiting, and as they approach, they swap places, and one moves further in and one moves further out again. And so it's possible to have somewhat stable interactions where they bodies will swap spaces in rotation through resonance and through the gravitational interactions. Whether that's what happened for Uranus and Neptune, I don't know, but it is a fascinating topic. Of course, the real problem is we don't know. We can't go back 5 billion years. We can't ever really see what happened. So all of this is down to theories and models of what's going on. But it certainly is a fascinating topic to try and unfold and place our solar system in the context of other planetary systems.
Yeah, it is really interesting. Something else that's really interesting has come up in the YouTube chat. So Volga asked, I'm wondering if we've ever observed Neptune's aurora. If not, what do we expect from Neptune based on its properties and previous Uranus radio emissions of aurora? So William Dunn, our colleague, has already answered some of this question. So William said Neptune's UV aurora were observed by the Voyager spacecraft when it flew past it. And it also saw a lot of radio emission that we think are linked to the aurora. But we haven't been able to see the aurora since because Neptune is so far away and our technology just isn't up to it yet. Another big reason that we need to send a spacecraft there, so you can see everyone really would like a spacecraft to go to the ice giants. But that's Neptune's UV aurora, and obviously, yes, I can see Tom and Emma are nodding already. They're excited to talk about this topic, a very good topic. So obviously, we are big H3 plus fans. We observe in the infrared, we observe H3 plus, but we've not been able to detect H3 plus at Neptune yet. And this is, well, it's quite a puzzle. That we haven't been able to detect it, and it's a big goal in our research community to be able to detect the H3 plus at Neptune, and we'd love to be able to detect the H3 plus aurora at Neptune as well. I don't know whether Emma or Tom, you want to come in and explain maybe why we haven't found it yet?
Sure.
Plus at Neptune.
I'm happy
So
to
I
take either.
don't know if Henrik is around, because if Henrik's here, he's the person that is literally the world expert on this.
He is the expert. We are all just co-authors.
Hey, nice.
Go ahead,
Yeah,
Henrik.
it's a really interesting one, isn't it? We've seen H3 plus from Jupiter, Saturn, Uranus, but not Neptune. And we've really tried. Last time we tried, we spent 15 hours staring at Neptune using the same instrument we're using now on Uranus. So the question is why? Well, we don't know yet, of course. It could be that Neptune has cooled just in the way that Uranus has cooled over several decades. But Neptune also has a lot of internal heat, and that internal heat drives the turbulent lower atmosphere, sort of extending it up in altitude, and that could potentially destroy our precious H3 plus. So we're not left with much H3 plus in the upper atmosphere. There are plans with James Webb to observe Neptune, hopefully next year. And that's going to be our best chance yet to observe H3 plus in Neptune. And why do we want to do this? Well, it gives us a way to remotely characterize Neptune from sort of near Earth orbit or on the ground. How hot is the upper atmosphere? Is there an aurora, like Rosie said? The Voyager observations of the UV aurora was sort of not very convincing, I would say. There was not a lot of repeatability. We didn't get a map of the aurora like we did at Uranus, for example. So we basically know nothing about the aurora at Neptune. So we got ways to go there, and obviously emission will help significantly in furthering this particular cause.
Yeah, James Webb will tell us a lot especially, I think, if we don't see anything at all. I think, ultimately explaining not being able to see from Earth is getting us so far. And what we found is that, the work that you did, Henrik, was able to show that current models should expect us to have seen something.
Yeah.
So it's difficult to explain why you don't see something, but what we do know is that the current theories say that we should have. So there's only things that you can tweak to make things harder for us. And we just don't know what that is. It could be colder. It could be that more H3 plus was destroyed. It could be that the conditions are different, or that the aurora are very sporadic, or that, who knows? There's lots and lots of different theories. The idea of understanding aurora is that you can kind of contextualize what happens from one planet and hopefully relate that to another. And everything we know about Uranus, especially Uranus as of maybe 5 or 10 years ago, should make it somewhat similar to Neptune in terms of the magnetic fields and the atmosphere. But what we know from the space missions is that actually that's not true. And, they saw huge differences in terms of what they found in the magnetosphere too. There's Triton, which is a really dynamic, active world, and there's no real analogy to that at Uranus. So it's really hard to know why you don't see something.
Yeah.
And
it's interesting, isn't it?
Yeah.
We think about Uranus and Neptune as sort of twin planets almost. But actually, there are significant differences between the two systems, and that's partly played out in the lack of H plus at Neptune and quite a lot of H plus at Uranus.
Yeah. And sometimes it sounds a little greedy, but I'm a firm believer that we should have two spacecraft. I think that expecting us to characterize and understand one of these worlds from the other is not enough. And, obviously, if we get funding to go to one of these worlds, I will be delighted. But I've always worked on the assumption that we should have spacecraft to both of these worlds, because they are as different to each other, probably, as Earth and Venus. And trying to characterize Venus from Earth or vice versa is impossible. They are too different from each other because they're both terrestrial planets. They both formed in similar distances from the sun, but not the same. They both have very similar likely compositions. But one happened to be too close to the sun and all of its water disappeared. Plate tectonics stopped. Its atmosphere caused drag that slowed it down to no rotation. It didn't have a moon. All of these minor differences result in vastly different worlds. And we're seeing that from what little we do know of the planets,
Yeah, it's certainly an largely unexplored frontier in our solar system, compared to any other set of planets, Uranus and Neptune. So, yeah, let's go. Let's do it.
I'm sold.
Yeah.
Just taking that a bit further, we have mentioned exoplanets a few times today, but have we touched on H plus exoplanets yet? Because it's a sort of, it's coming into like the same conversation as, we see it at CH plus as Saturn and Jupiter and Uranus, but not Neptune and not yet exoplanets. So obviously we're hoping to detect H plus at exoplanets. I'm not sure we have we had a go at that yet?
We've done several observations to test it through the many years. So I remember doing an observation very long time ago, actually, probably like 2004 or something like that, where we tried it with one of the nearest planets. So far, we've never seen anything. It's an ongoing challenge. I don't know. I see James's name. I don't know if James is here. Again, we'll just pull the world expert in. Why not? James had observations from the Keck telescope to do this exact type of thing. Unfortunately, we had really bad weather last time and couldn't do it. So 2 times in a row now, I think, James. Is that right? Oh, you're on mute, James.
Oh, we can't hear you.
Oh, no. There you go. I said all of the answers now, so I'm not going to say them again. I'm kidding. So we've been trying to propose to look at a spatially separated exoplanet, one that is not in front of the star, and there's only a couple of candidates for that. So in other words, one that from Earth, you're looking at the star and the exoplanet and they're spatially separated. We want to look at that planet outside of the light from the star, which gets in the way of the observation. And so we applied for time on the Keck telescope in about 2019. Actually, we applied in 2018, but we didn't get time. And then we tried again, and we got time, and we were going to take our observations in April 2020, and a pandemic happened. So that's those observations out the window. Then we applied again, and we got time for April 2021, so this year. But then the weather was bad the entire time. So last month we applied again so that we could observe this exoplanet next year. So it's just been going on for a few years now. The main challenge has been just performing the observations themselves. But we think that if we see H3+, if we see this upper atmospheric ion at an exoplanet, then we basically have detected aurora, an exoplanet. But yeah, you're right. The problem is kind of like, how do you expect to see this, an exoplanet, if we hadn't seen it at Neptune? I'm not sure if this has been touched on, but I think there was an implication given by Luke Moore about why if you don't see H3+ at Neptune, if you don't see aurora at Neptune, what could be the cause of that? And Neptune is quite warm, so the emissions should be nice and bright, but the density must be low, I think. So one of the causes for that low density could be Triton leaking some material around the planet. Is that right? I think I saw that in a paper. It's an interesting, profound implication that a moon would be deluging the entire upper atmosphere and destroying the thing that we try to look at. Yeah.
Yeah, I mean, it's a theory that we have. We have all sorts of analogies for that within our solar system. As you know, Saturn, I mean, again, world expert time, Saturn's rings stream the material down onto the surface. And we do know that at the equator of Saturn, that swamps out the H3+ completely. So if we were only able to see the equatorial region of Saturn, we wouldn't see anything at all. We would have a blank view. Very fortunately for us, that only happens at the equator. So the auroral pole regions of Saturn are still beautiful and bright in H3+. We expect that there may be analogies to that from other worlds, but what we tend to see around other planets is that those moons eject material that ionizes, and then it actually enhances the brightness of H3+, because you get the wonderful sort of streaming aurora that you see at Jupiter, where you have these bright spots from the interaction with Io. And in fact, all of Jupiter's aurora are basically supercharged by the material coming off of Io, the volcanic moon. So it's really hard to know for sure until we get more observations to try and characterize what is really happening there. Triton used to be a world I didn't know and understand, but having worked with the Trident mission to try and propose for a flyby has become something that I absolutely love. It's a really fascinating moon, and trying to understand and unpick how it interacts with the surrounding space is really interesting, because it does seem to be quite strongly interacting from what little information we have. When we looked at the composition of the two surrounding space environments, Uranus is also almost empty. There's almost nothing there, maybe a bit of stuff captured from the sun, but not much else. Whereas there seem to be a lot more kind of nitrogen and other ions in the magnetosphere, which have to have come from Triton. So it's leaking to some degree, but we don't know what pathway Voyager took through that system. It could have been, as we know from Jupiter and Saturn, there's a lot of variability. So it could have been that it flowed through the densest part of that burp from Triton, and so that's the largest extent of the material being thrown off. Or it could have flown through a really quiescent region where there's almost nothing. And actually there's other regions where there's huge amounts of neutral material, and it might have a very strong interaction. Those might act to destroy the H3+ in the atmosphere by falling in either gravitationally or possibly along magnetic field lines, which is going to be awkward anyway, because it's the orbit of Triton is not in the same plane as rotation, and it's it's retrograde because it's a captured object, so it's all sorts of craziness.
I heard it's also the coldest place in the solar system, even including Pluto.
It is. It's an incredibly cold surface, except for the bits that are erupting large amounts of material, and we don't know still whether that eruption is a volcanic eruption or more of a sort of greenhouse-driven spurting. The original theory was that the sun was heating up the underside of underneath the ice layer, melting it, and it was becoming pressurized and ejecting material. But more recently, modeling has suggested maybe it's much more like a traditional sort of volcanic eruption on Earth, where you have upwelling and it's driving. There's so many fascinating aspects. And one of the most fascinating is the ionosphere. Obviously, I would say that, right? We always love ionospheres.
We're biased.
We're biased, but I mean, it drew my eye away from giant planets towards another type of ionosphere, and it's not the strongest and most powerful ionosphere in the solar system, but there are. That's partly because it's so far from the sun, so it's not being ionized by the sun very much. And what we do know is that it's much, much denser than it should be. So that suggests all sorts of interactions and crazy oddities associated with that. We have had a question posted by Edwin Lanson asking, would anything change in the solar system if Uranus did not exist? I don't know if anyone wants to take that.
Less jokes.
I guess we wouldn't be here. Is that what you were going to say, James?
No, I don't think I've seen a model which would disclude it, but I wouldn't say that well, we probably wouldn't be here, in some way or another. That's such a significant absence, I think. But maybe,
I mean, there's the classic kind of butterfly effect, right? Which is, what the Nobel Prize 2 days ago was basically given out for, the complexity that rises from small changes. Who could say what would happen? What we do know is that it's probably not as dramatic a change as if Jupiter wasn't there, for instance. If you take Jupiter out of the solar system, it's going to have a much stronger effect, but it's almost certainly enough that it would mean that none of us would exist, and quite possibly humans wouldn't exist, because who knows what comet was redirected at some point. Chicxulub hit and destroyed the dinosaurs. Maybe it would have just missed if the gravitational pull of Uranus was not there to slightly alter it, but another one would have hit at another time. That's the chaotic nature of the orbital dynamics in the solar system. It's these things settle down, and we know that there was a significant interaction between Uranus and Neptune and that surrounding outer material as they settled outwards and outwards into the surrounding space. So it's almost certain that, if you ran a model that was super complicated enough to predict all of these things, you would see dramatic, stark changes to life and to, anything that's associated with edge cases, like, humans being on the edge of extinction at times in our past. But would it stop a planet sort of similar to Earth existing? I don't know. Possibly not. Maybe it could have caused the gravitational interactions of the Mars-sized object that smashed into the Earth enough that it didn't do that, and so you would get no moon on the Earth. It's almost impossible to say. But in terms of the overall dynamics, probably not as strong an influence as many of the other big objects in the solar system.
I think you just ran the model for us, and it was nice to see the results there. Yeah, I think you're right. Like, it's kind of a skin deep reaction for what happened on Earth, but the bulk stuff should have been probably the same, I guess. I think out to Uranus and beyond, it's probably not too much of a big deal for major events afterwards, but yeah, I totally agree with that.
So John Morrell was asking again about what we're seeing here in the Uranus cam, and I think the thing that is throwing some people off is that this is a flipped image. So often what happens when we're looking at these things is that what we see is flipped, and so actually this is actually not flipped. It's rotated by 180 degrees from what you would see if you were to stand and look straight up at Uranus. And so the two bright stars down at the bottom, the two bright objects are not hot pixels, they are real. And you can see Umbrel most far out, and then Ariel slightly closer in. And then, although I can't see it in this particular frame, there is a fuzzy blob over on the right-hand side that we're pretty sure is Miranda. All of the rest of this material, it's harder to tell exactly what's going on. Some of that might be real, but a lot of this is just noise. So the best way to understand that is to, rather than have it constantly updating like we have, is to add it and stack it. So if we were actually taking images of Uranus and our scientific target was images of Uranus, instead of doing what we're doing here, we would be stacking things carefully and boosting our signal as much as we could. But of course, our focus is on those spectra on the left-hand side. Our aim is to get an understanding of what those are. And ultimately, this is just a tool. That the most important thing about this image to us is the green box. And the green box is just the computer looking at this image and saying, is the big bright thing in the middle of this box? And it looks in two directions and it says, okay, how close is this big bright thing to the center of the box? And if the big bright thing, which happens to be Uranus, moves away from that center point, what kind of offset do I need to put in to get it back? And it's basically guiding on the planet itself. So if the planet starts moving away from where we want it, it will automatically pull it back into place. So it's incredibly useful, because what it means is that we can ensure that the planet is always focused on a part of the array that we're interested in, and we can make sure that the data that we're taking is really concentrating on what we're interested in most. And the better that we can do that, the more accurate and more detailed and more carefully we can map out the various structures that we're seeing in the ionosphere.
We've had another question at YouTube. So, are the rings resolvable?
So they are resolvable, but unfortunately they are difficult to see. So you can't really see them here in the data that we have. Here's a frame, a movie from before, from a past observation where it's maybe a little clearer, and you could almost just about make them out above and below the slit. What we can do is add the data up, and again, if we add the data up, we should start seeing this weaker signal much more clearly, and that will help us pull that out. I can see them, but again, I can appreciate that many people probably can't. It takes something of a leap of faith.
So are they kind of like, they're quite thin and white, and then they're kind of like on the edge of that?
They're on the edge of the circle above and below. So they are sort of two halos, almost like a hat and a beard to the planet.
I can see it.
And you can just about make it out. As you add and stack the data, you get more and more easily seen observations. But of course, you know, we didn't resolve out the rings until we got there, which I always find quite surprising, because this telescope is from that period. So certainly before we arrived, this telescope was built before we arrived with a spacecraft at Uranus, and we can just about see them here as they are taken in a guide camera. So it's pretty amazing that it took a space mission to get there. But again, you know, instrumentation has improved so much since this telescope was built, and it does help make these observations much easier. Good.
So another question. So could William Herschel have seen the rings, as some authors thought?
So I've heard about these claims when we were planning this live stream. I was talking to Sian, and she mentioned this. It really surprised me. I don't want to speculate, right? It's entirely possible that the rings were different when we observed. Now and then. We know that there are some levels of variability in Saturn's rings, and who's to say that the rings back then weren't different from how they are now. It seems unlikely if they were the same as they are now, that he would have been able to pick them out. But again, some people's eyesight is incredibly powerful, and so again, I'm not going to preclude the possibility. I think it's interesting that there is some theories that suggest that, but I think that's ultimately down to a historian of astronomy to argue the case for or against, really. You can see how faint they are here, but then we're looking at infrared light here, so maybe it isn't the best comparator. What I would say is that, on the right days, with the right filters, we can pick out the rings using a 3-meter telescope. But that's quite a big telescope in comparison to the size of the telescopes that Herschel had. I think it seems less likely. But there are lots of different theories about what people could have seen in the past, and many of them suggest, quite exciting possibilities in terms of understanding of some of the processes that happened. And I'm not one to say that Herschel didn't have magical eyes. I'm sure he has better eyes than I do. That's for sure.
Yeah, it's always it's always quite hard. I was with some people and they were asking me, Rosie, what is that, like, the sky was really clear, and they were asking me, what is that, like, smudgy thing? And I was like, I don't know, I can't really see. And they've managed to spot, like, Andromeda just with their eyes.
Yeah.
I had to get, like, the binoculars out. Maybe I need to get my eyes tested again, but yeah. As also a little bit sort of like, once you got your eye in, like last year, I don't know how many people in this call managed to spot Neowise, the comet, and I was like pointing it out in the sky to quite a few of my friends, and again we were looking through binoculars and stuff, and once you got your eye in for it, you can see it so much easier. Like when we look at these spectra, and like we were kind of like, oh yeah, there's definitely one to the left, and like once you got your eye in, knowing what you're looking for, maybe it's the same with the rings. Maybe once you got your eye in, you can see them. Yeah, it's interesting.
Yeah, the human eye is an amazing piece of equipment in terms of being able to resolve things that are surprising.
Yeah, and like how when you're looking at the night sky, to look like slightly to the left or right of the object you're trying to see, that helps it. Yeah, it's really interesting. So here's another question from the YouTube. Which institutes are the lead for proposing, researching, and capable for finding funding for Uranus or Neptune missions?
So that's really interesting, because it sounds like that's one question, but it's actually 3 questions. And the people that are leading the proposing are not necessarily the people leading the researching. And they're definitely not the people leading the capability of finding the funding for a mission. Whenever you propose a mission like this, it's inevitable. I mean, the primary focus is how are we going to afford to do this? When I was involved in the Trident mission, that was seen as an incredibly cheap mission to an outer planet. And that was just $500 million. That was the super budget way to do these kinds of missions. In order to do an orbiter at either Uranus or Neptune, you're talking about for even a super cut down mission, at least $1 billion, and probably in the range of 3 to 5 billion. You are expecting an enormous resource output, and there's very few places capable of funding that. Obviously, NASA. ESA could fund it, but as Lee talked about, there are considerable constrictions on what we can do in the outer solar system, because only NASA has availability for plutonium, and you need plutonium in order to power. There's some really interesting research going on at Leicester looking into americium, which is another form of radionuclide that we're hoping will be able to be used in the future to power ESA missions, but that's still currently in the works and is a very long way off. And there's a huge political implication in terms of using nuclear power for these spacecraft. And unfortunately, it's almost the only way to do these space missions. Typically, closer to the sun, we can get away with using solar panels, but it's just too faint out there. The sun is a very distant star, and so we can't really use that as a power source. And the only really viable remaining power source is to use radionuclides to power your spacecraft. And even then, quite often, what you're doing is charging up over a longer period a battery, and then you use the battery power when you're actually doing your observations, and it drains away, because even these nuclear power sources are not fast enough to power the space missions for the whole time that you want to take data. So that's a huge resource, and you have to convince people that you want to spend that much money. And so it becomes this very large construct where you are at the same time showcasing the science that you can do and why it's important to go, and also showcasing the engineering that exists and showing that you can go. And so when you work on a space mission, there is a combination of a whole range of scientists that cover all sorts of different topics, whether it be the aurora or the lower atmosphere or moon surfaces or rings or the interstellar environment. All of these different people, the interiors of the planets, come together and argue the case for a mission based around all of the different sciences that they can do. And they are always hand in hand with a whole slew of engineers that do, rocket propellant, power systems, how you build instrumentation, how you build the telescopes that go onto the instrument, onto the spacecraft, all of those, showing that these things that we're going to do in terms of the science can be measured by these items that we built into the spacecraft. And so you build a spacecraft that can resolve out as much as possible all of the different science that you want. And there's always a constriction there, because you have to get to the planet. To do that, you need fuel, and to do that, you need to launch fuel. So the bigger and more complex the orbits that you're going to take, the more fuel you have to put on, which means the less instruments you can put on. And so you always have this balance. You wish you could put everything onto a spacecraft, but you are tied down to just those instruments that best answer all of those science questions. And so what spacecraft you have totally depends on what the engineers can get you effectively, in terms of how stripped down can we make various aspects of the spacecraft to allow ourselves to have enough mass and space to include as many of the instruments that we want to resolve out the science that's fascinating and interesting. So it's always this interplay between those two to showcase that you can create an affordable mission. And then, of course, you have this brilliant mission to Uranus, but someone else has a brilliant mission to explore the early universe. Someone else has a brilliant mission to look at Mercury, or to look at the Mars surface, or to bring back rocks from the dark side of the moon, or 1,000 other potential really interesting scientific targets. And so you go through a bidding process where you try and argue your case. So that's what happened to the mission I was on, which was the proposed mission to Neptune, a flyby mission from Neptune. We managed to get down to the final 4, and we were arguing our case against 2 missions that were going to look at Venus in 2 different ways, and a mission that was going to orbit Jupiter and look at Io, all of which had fantastic, amazing science on them. The mission to Io was going to be able to see lava flows as they formed on the surface of Io. I mean, that would be amazing to see. And this is someone speaking who is in arguments against it. So all of these space missions have amazing potentials for science, and ultimately we're arguing for funding. The ideal would be everyone would get that funding, but the realistic nature of science is that we're always trying to argue our case against any other science. You're muted, Rosie.
There's just so many different roles and different things they have to consider for space missions. It really is a mammoth task, but hopefully, obviously it's in the theme of the day. We want that mission to the ice giants. So coming up now, we're going to have another speaker. So Emma, would you like to introduce the speaker?
So hi, Will. Hopefully you can hear us. Hopefully we'll be able to hear you. I think you're muted just at this moment.
Yeah, can you hear me okay?
Yeah, we can hear you perfectly well. Thank you, Will. So for everybody in the audience, this is Dr. Will Dunn, who is joining us. Well, I know exactly from UCL, from the Mullard Space Science Laboratory, or from your own home. But either way, it's lovely to have you. So Will is a research fellow at University College London, or UCL, more specifically with the Mullard Space Science Laboratory, whose research focuses on observing planets in the X-ray spectrum. I noted that Will is also working with partnering scientists with schools for ORBYTS, if I have that correct, in order to provide original science and space research projects for schools, which, obviously here with a lot of outreach ourselves, incredibly great to hear. Earlier this year, Will and his colleagues showed a low signal detection of X-rays from Uranus after a long number of years observing with the Chandra X-ray Observatory. And so today we hope he'll be able to enlighten us with this research. Take it away, Will. Whenever you're welcome to share your slides.
Can you see my screen?
Starting to share. Yes, we can see the whole of your screen at the moment.
And presenter mode?
Yes, perfect. We can see that.
All right, awesome. Okay, great. So yeah, thank you so much for the invite to speak today. I just think this is really cool. I think, and also I'm kind of in awe of you guys, like doing science live while having these discussions that are so illuminating at the same time. It's really cool. And I think it's a really cool model. And yeah, and the more of these, the merrier, I think. So yeah, as Emma said, I was invited today to speak about X-raying Uranus. I'm amazed more people haven't cracked up during this at all of the related jokes. So yeah, but as Emma hinted at, it was a really low signal detection. And so I was really going to struggle to fill 30 minutes talking about it. So instead, I hope this is okay, but I've changed my remit slightly to be talking about the magnetosphere and the aurora at Uranus. So first of all, to understand these, we need to talk about matter. And I think it's really important that we focus on why we should care about these things. So in school, typically you would do solids, liquids, and gases, and they would be the three states of matter that you would learn about. So for water, you get ice as the solid, you get a glass of water, for instance, as the liquid, and you get clouds and stuff as the gas. But actually, the most common state of matter in the universe is one that you don't learn about in school. It's plasma. And plasma makes up 99% of the observable matter in the whole universe. So based on this, it's kind of important that we know how it works, right? What dominates its behavior, what controls the behavior of this stuff that is the majority of the universe, and therefore what controls the dynamics of the universe as a whole. So what is plasma, this mystery state of matter that I've just mentioned? So gas is typically molecules where you'll have your nucleus, and then you'll have some electrons orbiting that nucleus, and they'll be floating around together as a molecule. Plasma is what happens if you tear that electron off of the nucleus. And so you separate the electron from the nucleus and you get electrons and ions. And so you get these two differently charged things, electrons with negative charge and then ions with positive charge. And so plasma is this, it's where you tear these two things apart and they float around distinct and not orbiting each other. And I guess what's really key here is that plasma is going to obey whatever a magnetic field tells it to do. If you nudge or change the magnetic field, then the plasma and these charges on the plasma are going to change their behavior and the dynamics that control them. And why we care about this for planets is because lots of planets in our solar system have massive magnetic fields. And this is kind of cool, right? It presents us with the opportunity to study plasmas across the universe because we can go to these planets and we can explore their magnetospheres, that's the magnetic bubble around the planet, and we can see how that magnetosphere is controlling the plasma and therefore what processes control how plasma behave and therefore what processes might be controlling the vast majority of matter in the universe. These magnetospheres can be really, really big. So for instance, Jupiter's is the biggest coherent structure in the whole solar system. The magnetosphere, if you had plasma vision, you'd see this magnetosphere that stretched 6 times the size of the moon in each direction across the night sky. It's truly vast. And within this, there's lots of
dynamics and processes going on that we can study. And the way that we typically study these things remotely, as we're going to have to do for Uranus and Neptune for the foreseeable future until hopefully we get a mission at some point. To study these things, we use the aurora, or the northern and the southern lights. And the aurora really acts as this video, whatever processes are going on in the magnetosphere, whatever processes are governing this plasma. You can see here that the magnetic field lines, these like blue stretch things around Jupiter, thread into the poles of the planet, and that's where you get the northern lights. And here, this is a video, I think this is from one of your colleagues at Leicester, actually, from Johnny Nichols. So here, overlaid on this image of Jupiter is actually a real video of Jupiter's ultraviolet aurora. And you can see loads of crazy things going on here. Actually, I think, yeah, I think I have a closer up video here. So this one, where the last one was from Johnny Nichols, this one's from a chap called Denny Grodon in Belgium. And so what you can see here is a video taken by the Hubble Space Telescope. So Hubble is staring at Jupiter's North Pole here and taking this video of the ultraviolet aurora. And then here on the right, we basically reprojected this image that we see from the side so that we can look down onto it and see how it would look if we were flying over the top of the pole. And there's so much going on here. There's so many, I mean, I can watch these videos for so long because I find them spectacular and stunning and kind of beautiful. And there's so many processes going on here. So I think actually maybe Tom, like 10, 15 minutes ago, mentioned that, that for instance, Io pumps out loads of plasma. And so we actually get this dot from Io, which you can kind of see here, pottering around the magnetic field lines from the planet, thread out from the planet and touch the moon Io. And so as Io moves through the magnetic field line, it nudges them, and that leaves an imprint on the North Pole of Jupiter and on the atmosphere of Jupiter, where you get this little bright dot here. Equally, you get dots from Europa, you get these kind of crazy, almost like lightning storm type things going on in the polar region. We still don't really have very much of an idea of what causes all of the crazy things that we see going on in Jupiter's pole. Particularly, you see this very bright flare. I just missed it here, but you'll see it go off again here. Jupiter has these monstrous flares that they equate to terawatts of power. So that's a crazy amount of power. You could actually, if you had, I think one of the questions before from, I think it was Edwin, asked, no, I think someone else asked, well, how could we as humans use Uranus? If we had, it would take someone incredibly creative and with some level of engineering genius that I can't even comprehend, but if you could somehow capture this power that Jupiter's aurora is injecting here with these bright flashes that you see just going off over here, the terawatts of power, you could power all of human civilization with that. It's a crazy amount of energy that Jupiter's magnetic field and the plasma around it is pumping into the atmosphere and delivering into the atmosphere. And actually, so James O'Donoghue, who's also on the call, he did this really cool study, I think it was 3 months ago now, where he showed that actually the energy that Jupiter's aurora is pumping into its atmosphere is actually heating the entire atmosphere of the planet. So it's not like these almost esoteric plasma processes aren't relevant to planets, right? They're capable of changing the temperature of the whole atmosphere of the world and really changing the dynamics and the chemistry that's going on in that atmosphere. So understanding this coupling between this plasma, this weird thing that for some reason we don't teach school students, to magnetic fields, and then how that connects to the planet, that whole system is coupled, and the dynamics of each part of it are deeply interconnected. And so understanding how they're connected is important for us understanding how planets work, how the dynamics of the whole universe works. If I can move slides. And in fact, it's not just planets that have this plasma environment, that have these magnetospheres filled with plasma. Stars also are constantly pumping out plasma. So this is a video of the sun. And here I'm particularly highlighting some really dramatic events where the sun is pumping plasma out into the environment around it. These are called coronal mass ejections, and they're huge explosions on the sun, giant solar storms. You can see this giant one go off here, and you can almost see before it goes off that it traces the magnetic field of the sun. And you see this loop where the plasma is gliding along the magnetic field of the sun before it gets ejected and thrown out. And so the sun is constantly pumping out this plasma. Sometimes it does it with these really dramatic events, these coronal mass ejections. But generally, most of the time, it still kicks out this thing that Lee Fletcher was talking about a lot earlier, which is this thing called the solar wind, which is this steady ejection of particles. Here goes another of these coronal mass ejections, but the whole time it's also pumping out plasma out into space. So electrons and ions are constantly flowing out of the sun and into space. I can again watch these for hours. I just find them stunning. Like these huge explosions that our local star produces. I think it's really cool. So maybe you're starting to wonder now, well, the sun's throwing out these huge ejections of plasma and also kind of this general trickle. I say a trickle, that's the wrong word. It's like the particles leaving the sun are traveling at hundreds of kilometers per second. They travel across the whole of the UK in a couple seconds. They're bulleting out of the sun. And they're flying out through space and they're going to collide with the planets as they reach the planets. Here's another of these huge coronal mass ejections being thrown out through space. And when they get to the planets, if your planet is unfortunate and it doesn't have a magnetic field around it, then they're going to start tearing away at the atmosphere and they're going to strip the atmosphere off the planet gradually. In fact, potentially they might preferentially strip certain atoms from the atmosphere, potentially, for instance, removing hydrogen so you can't have water at the planet and things like that. But if you have a magnetic field, actually all of this stuff flowing out through space and the magnetic field that flows out with it through space is going to interact with the planet. So here's what happens to the Earth when you get a flow of this solar wind, these charged particles, this plasma flowing out of the sun, and it rocks up at the Earth. And so what happens is this magnetic field that's woven into the plasma and flows out with it will interact with the Earth's magnetic field. And so you're going to see this here, and it kind of peels it, it opens it up. You get this process called reconnection. And it opens it up and it's going to drag that magnetic field over the planet and away from the planet as the solar wind flows over the planet. And towards the tail, away from the planet, it's going to, as you drag it and open it, you're going to apply pressure and squash it. And as you squash it, this thing will have kind of a tiny mini explosion and the field lines will flow back towards the planet and you get the beautiful auroral displays that you can see at the North Pole or the South Pole. So, as Tom's already said, the Earth is kind of, it's almost, maybe it's simple because we've studied it so much, but it has quite a well-catalogued and well-characterized interaction. And we understand what happens with this outside magnetic field from the sun and from the solar wind, and what happens when it connects with the Earth's magnetic field, and how that produces our northern lights. But Uranus has this, I mean, I think we talked about this quite a lot today already. It's totally bizarre that it just rolls through the solar system on its side. But what's even stranger is that the magnetic field, unlike Saturn, for instance, where the magnetic field and the rotation axis are really, really closely aligned. And for Earth and Jupiter, it's kind of, they're within 10 degrees. For Uranus, they're tilted to a huge amount, 60, 70 degrees off. And what's also kind of, so that as Uranus kind of rolls through the solar system, it's at lots of different angles the whole time, just changing direction the whole time. And so all of these magnetic field lines that are wrapped around Uranus are also rotating through the whole solar system. And so if you have this magnetic field from the sun approaching it, the whole time you're kind of changing the orientation of this magnetic field that's facing it. And really we're not, oh, there's one other factor as well that's kind of crazy, and I don't really fully understand how this works. But it's true for Neptune and it's true for Uranus. Not only is the magnetic field pointing in a different direction to the rotation axis, but also it's not through the center of the planet. Like the center of the magnetic field is offset from the center of the planet. So you have a bigger magnetic field almost on one side to the other side. And you can kind of see that here with this bar magnet offset from the center. And that's true for Uranus and Neptune. So maybe this is like a universal property of ice giants, and we're going to see this at all of those ice giants that exist across the universe, or maybe it's unique to our two local ice giants, Uranus and Neptune. I showed what the magnetic field does to the Earth's magnetosphere and how the solar wind coming along interacts with the Earth's magnetosphere. We really are so unsure. I mean, I think what's really cool about Uranus and Neptune is quite how little we know. They're just worlds of complete mystery. And this is another aspect where it's really mysterious what is going to happen and how this whole system is going to interact. Jin Kao and Carol Patty, two of our colleagues, produce these amazing magnetic field models. And so here you can see kind of different field lines and from this magnetic field and where they're pointing, and their simulation of what they think is going to happen as you rotate the planet and as you rotate this whole magnetosphere, and what happens with the solar winds, these particles from the sun and their inbuilt magnetic field when this thing rotates through them. There's a crazy amount of detail here that I probably don't have time to go into. But yeah, Lee already showed this graphic, actually. In fact, it's from his paper from last year. But what we think happens is that as this whole system, as Uranus rolls through the solar system, I think James actually said a few days ago on his Twitter account that it's kind of like if you had a bar magnet in like a washing machine or a tumble dryer, right? This whole thing's rotating through the solar system and the thing's pointing in different directions the whole time. And so when your solar wind comes towards it, it's going to get twisted and wrapped up and really kind of becomes this helical structure where you just get this twisting string going out through the solar system, where the solar wind attaches to it and then gets twisted as the planet's rotating and moving this field. So we think what probably is happening is that you get these giant knotted up ropes of magnetic fields twisting out through the solar system from Uranus. And so you have kind of the boring terrestrial Earth-like case here, and then this crazy knotted ice giant-like case here. To really understand these magnetospheres and actually what's happening, probably our best tool until we have a spacecraft at the planets is to study the aurora, like all of the fantastic H3+ Leicester people are doing today. So here are two images of the aurora taken by Laurent Lamy from 2012 and 2014 by the Hubble Space Telescope. And so you can see you get these weird dotted type structures, these like little patches basically of aurora. In fact, James has produced a really cool video that I'll show in a few minutes' time. But so we actually don't, I mean, there's some really cool ideas and hypotheses, and Laurent's come up with a great explanation, which is that where the magnetic field attaches to the solar wind, that might be what causes these. It's called the cusp. It's where the magnetic field opens and stitches itself into the solar wind. And so maybe what we're seeing here is that we're seeing the magnetic field stitch itself to the solar wind, and then particles flow down from the solar wind and crash into the atmosphere of the planet. That's one possible explanation. We still don't really know. So that kind of neatly brings me on to X-raying Uranus and why we might want to do this. So Rosie's already talked about my woes as an X-ray astronomer and trying to study X-ray emissions through the Earth's atmosphere, and that you can't do it, right? X-rays don't get through our atmosphere. It's not like the infrared emissions and this H3+ emission that the other guys are looking at. We don't get this stuff getting through our atmosphere. And that's kind of good, right? We're like, we wouldn't exist if X-rays were getting through the atmosphere. We'd all be dead, and probably life on Earth, on the surface of Earth at least, couldn't have evolved if it was possible for X-rays to reach the surface. They're really bad for us. But it really ruins my astrophysics as well, because I can't study it without using spacecraft. So we have to have spacecraft and X-ray telescopes that sit above the atmosphere to study this. Unfortunately, we have a whole fleet of amazing X-ray astronomy spacecraft, but these are the two that I'm going to mention today. So we have NASA's flagship X-ray instrument, that's Chandra. So Chandra is kind of like the Hubble Space Telescope, or like JWST will be. So JWST will do infrared, Hubble does UV and visible, and Chandra does X-rays. It's the flagship X-ray instrument. And it basically takes us amazing videos. And most of the images I'll show to them the Chandra images. We also have the European Space Agency's XMM Newton instrument, where Chandra is this colossal telescope. Actually, Chandra is the heaviest thing that the space shuttle ever launched. It's got these massive, massive mirrors, tons and tons and tons of just mirror. And the reason for that is because if you try to use a normal mirror for X-rays, they're just going to smash into it. Chandra has these like very gradually graded mirrors that just guide the X-rays down the telescope and into the camera at the bottom. So Chandra has one gargantuan telescope, the heaviest thing that the space shuttle ever launched. And XMM has 4 telescopes, actually. It has these 3, which are the same size, and then it has a little optical one, which also does ultraviolet imaging as well. So typically, X-ray astronomy used to do really exotic and crazily energetic things. So these X-ray images are from exploding stars. They're from supernovae. So the most massive stars you can imagine, potentially hundreds, maybe millions of times the size of our sun, exploding. And when they explode, you get these huge supernovae which flow out through space, and you get structure. These are the actual images, and you get structures that look kind of like this. Equally, so X-rays are really good at studying super energetic things, stars exploding, galaxies, and like really bright stars in galaxies, get clusters of galaxies. So not even just single galaxies, whole sets of galaxies that are connected by gravity, that are colliding into each other. Black holes at the center of galaxies. I mean, I struggle to imagine anything more energetic than a black hole. So these things called active galactic nuclei that sit in the middle of galaxies and almost maybe spin the galaxy. And the huge black holes in the middle of those, we use X-rays to study those, and we use X-rays to study when black holes eat things or collide together, or neutron stars collide, or all of these insanely energetic, massive things bump into each other. So why would we? So actually, what's kind of cool is that actually, despite these crazy energies that are associated with these other things, let me move this. Actually, we can study X-rays from planets as well. And it tells us quite a lot about the planet. So here I've overlaid X-ray images from Chandra of Jupiter's X-ray aurora from the North Pole and the South Pole onto Juno images as Juno flew over the North Pole and the South Pole at the same time as the observations were taken. So the X-ray aurora here is in purple, and the visible images are from the Juno spacecraft. So X-rays tell us about the aurorae and like what these magnetospheres are doing. They're also really good at telling us what things are made of. So down here on Earth, we use X-ray fluorescence the most to study what something's made of. So this could be to study if jewelry or paintings are fake and what they might be made of instead, or what fake paints people have used to make these forgeries. They're used to study what's in food, for instance, like to make sure that there's not chlorine in toothpaste, or to make sure that your tomatoes aren't covered in arsenic or something. So we study basically the atomic or the elemental composition of anything on Earth. If you want to study it, your best bet is probably to use X-rays and to use this process called fluorescence, which studies the composition of things. X-rays are maybe the best thing for doing this at an atomic level, whereas the infrared is really good at doing this for molecules and seeing methane or O2 or H2O or things like that. At the other end of the spectrum, at the other end of the EM spectrum, X-rays tell you, okay, there's this much oxygen, there's this much carbon, there's this much nitrogen, there's this much magnesium or silicon, or at an atomic level, they tell you how much of something there is. And this has been used widely through the solar system. So way back in the Apollo era, when we were first visiting the moon, X-ray instruments were taken to the moon to study what it was made of. Similarly, the Messenger spacecraft took them to Mercury to study what the surface of Mercury was made of. And our colleagues at Leicester have made this amazing instrument MIXES, which is currently flying towards Mercury and again going to study what the surface of Mercury is made of by using X-rays. So X-rays are really good at telling you what things are made of. They're good at telling you about the aurorae. There's also this super cool mission that's coming up called SMILE. SMILE, again, the X-ray instrument's been built by our colleagues at Leicester. And so the X-ray instrument on SMILE is actually going to image Earth's magnetosphere for the whole time. Previously, we have spacecraft that measure little individual bits of it, or we look at the aurora. But actually, the X-rays here are produced right on the boundary, where the solar wind crashes into the Earth's, the edge of the Earth's magnetosphere, and it glows in X-rays. And so we're going to study this SMILE type event with this instrument called SMILE, and that's going to use the X-rays as well. So that brings me neatly to our study of Uranus. So back in November 2017, a colleague of mine, Laurent Lamy, got in touch and said, "Okay, we're taking Hubble observations of Uranus in November. Do you fancy organizing some X-ray observations?" And so I jumped on the possibility. I got emailing to the director of the X-ray observatories, and I said, like, could we please have some time? In fact, it doesn't work like that. It's like the amount you beg is not going to give you the time. You have to lay out a really well-reasoned argument and competitive argument, because exactly like Tom said earlier, you're competing with everyone else to try to get this time and to try to convey that the science you can do with this instrument is going to be transformational, and it's going to really rewrite what we know about these places. And so when I first got this data, I looked at it and I wrote this really beautiful paper that I was really proud of, entitled "No Significant Detection of X-rays from Uranus." And then I was encouraged to look more deeply at the observations by some of our colleagues. And actually it turned out that it wasn't a non-detection, it was a very slight detection. So here's what the image that we saw of the night sky from Chandra was. And so Chandra's field of view, this whole region that it can look at, is really, really big. So Uranus fits in this tiny little red square here, and we're looking at a region that covers tens of thousands of times the area of Uranus across this chip. Oh, sorry. And actually something really key here is that we don't get a lot of X-rays, right? It takes a lot of energy to make an X-ray. And so each of these dots is a single X-ray that was detected by the detector over a 5-hour window. So you could actually, I mean, if you had sufficient time, you could sit here and you count all of the little individual dots that we got from the detector over the 5 hours that we were staring at Uranus. And what you can see is actually a lot of the field of view is empty, right? Most of the night sky is not producing a detectable X-ray signature during the window that we were observing. There are big blank spaces all across it. And then there are some bright X-ray sources. So what did we actually see in this little red square? I wanted to show you guys the actual data today, because I think too often we show some pretty images and not the data. And I feel like what I love about this live stream is that you're actually seeing the data as it comes down, real data directly straight from the scope of the telescope into the detector and then straight live streamed. So this is what an X-ray observation would look like. And so if we stare in that little red box, actually what we find is that we got 5 little X-ray photons perfectly coinciding with the location of Uranus, and then a lot of blank space around it. So this is what I first saw, and I thought I don't know if we can declare this as a detection. So I did a lot of simulations and ran lots and lots and lots of tests. In fact, I ran about 10 million different simulations where we tried to reproduce fake signals that the telescope would produce and check to see how often we would get 5 photons in this time window located with Uranus. And what we found is that actually it's a 1 in a million. So one of those 1 million, or actually it was 3 of the 10 million simulations, produced a signature coincident with Uranus that was this strong. So that's, I mean, potentially still, maybe we hit that 1 in a million time and we got really lucky or unlucky, and that actually this isn't a genuine signal. And maybe it's the 1 in a million times. But actually then when I delved deeper and I looked at the colors of the X-rays, so just as visible light comes in lots of different colors from red to blue, X-rays come in lots of different colors or energies as well. And the weird thing is that if this is a fake signature or like a randomly generated signature, then the colors of the X-rays from Uranus look exactly the same as the colors of the X-rays we get from Jupiter and Saturn. They don't look like the colors of X-rays we get from black holes. They don't look like the colors of X-rays we get from huge stars when they explode, things like that. They look like what we would expect from a Jupiter or a Saturn. And so I think beyond the fact that this is a one in a million chance that you would get these 5 photons precisely on the planet, also the colors of the photons look like what we would expect from a planetary signature. And so this is where they sat. They sat, 2 of them sit here, kind of, I don't know, it's 2 photons, right? But this is exactly where the aurora was during the observation. So maybe they come from the aurora, maybe not. It's, and then the other 3 possibly coincide with the rings. And then this guy up here, this is the size of a pixel on our detector. So that's like a little square on the detector, and basically how precisely we understand the location of these things. This guy up here potentially comes from the rings as well. So the weird thing about the signal is we shouldn't be getting a signal this strong. We should only be seeing 2 X-ray photons. We should be seeing basically the number of photons leaving the sun in the X-ray waveband, bouncing off Uranus and coming back to us. And that should be less than 5. And so the strange thing about this is that it seems like Uranus not just is reflecting X-rays coming from the sun, but actually it's somehow generating these things that we normally associate with the most energetic processes in the universe, processes associated with black holes and things like that. So not only is Uranus reflecting X-rays, but it seems like it also produces more X-rays than we'd expect to see. Here was another observation that we had in 2017. And again, this very temporary brightening coincided with the location that we expected the aurora to be at. And we also see something seeming to coincide with the rings. I want to be really conservative here. So this I should say as well, this whole image was made, the infrared image, which is in the blues behind, was taken by the VLT at the same time. Exactly like was discussed earlier, it's really difficult to see the rings unless you kind of change the contrast of the image slightly. So that's been changed to bring this out. And actually this image was made by a school student. So I think Emma said at the start that I do lots of work partnering with schools and supporting school students to do active research and to play around with space missions. And this was done by a school student. So he took the X-ray data and he took the infrared data and he overlaid them. And so maybe tenuously, again, we're seeing a bright burst of X-rays in the same location as the aurora would have been, and a bright burst near the rings. Again, we should be super conservative and careful with this. And what we really need is more observations. So James has made this amazing video today showing where the aurora are, what they might look like. And so what we might expect is if we were to watch Uranus for multiple rotations, we might expect to see the X-rays follow. If they're coming from the aurora, we might expect to see the X-rays follow the aurora. I want to stress that, so would we expect X-rays from the rings? Well, actually, Saturn has these iconic rings that I guess the whole planet is famous for. And we see those rings glow in the X-rays. In fact, they glow in oxygen colors of X-rays. And that's because the rings are full of water ice, some of it from Saturn's tiny moon Enceladus, which has these amazing water volcanoes constantly pumping out water and producing the rings. And so Saturn's rings glow the color of oxygen in X-rays because of water ice in the rings. We haven't collected enough X-rays in these images to know what color they're glowing. And so we can't actually figure out yet what the rings might be made of that might be causing them to glow, if indeed they are glowing. What I want to stress is the time that we were given for these X-ray observations was really short, really exploratory. We didn't have a lot of time to do detailed science. It was basically, okay, you can have some time, let's see if you detect anything. And it seems like we detected something, unless we hit that 1 in a million chance that it's not a detection and that it was randomly generated by the instrument. And it also seems that across the 3 observations, we see the X-rays maybe coinciding with the locations where we expect the aurora to be, and also potentially clustering along the rings. I think I want to close this by basically saying we're proposing for more observations. We'd like more time to really test this, and we need much longer observations. Like the few-hour observations we had weren't enough to collect enough photons to really understand what this signal means. Are we seeing X-ray aurora from a whole new planet? Are we seeing the rings of Uranus glowing in the X-rays because things are smashing into the rings and causing them to glow the color of whatever they're made of? And so I think this is kind of it's a disappointing sort of watch this space. It seems like we've discovered that there are X-rays being produced by Uranus. They're brighter than if it was just reflecting X-rays from the sun. And so there seems to be something else going on. Maybe it's aurora, maybe it's the rings, maybe it's something else that I haven't imagined yet, or that someone else much smarter than me can figure out. But we want more observations in order to study this more. I think, yeah, I should probably close up there because I'm already a little over, sorry.
Said it's no worries. Thank you so much, Will. We appreciate your time and wonderful slides you prepared for us. I still really I remember reading your paper earlier on in the year and getting kind of a great idea as I'm writing up my own paper at the moment, and being like, it's interesting because we're all very tentative, especially when it's just the beginnings of stuff, because you don't want to particularly be the person saying, yes, it's this, and then have a paper, like 6 months later going, actually. So thank you all. I will have a quick check to see if we have any questions. I don't see any on YouTube at the moment. I don't know if we had any on chat. I guess I'll ask one myself. So I guess this is a combination with you, partnering scientists with schools, but also kind of with your work. So how much do you bring with Uranus research? Do you go to schools and teach to? Again, you're welcome to correct me on this in terms of the secondary schools, high schools, or primary schools. How much do you bring in, and do you in depth, like as you mentioned, you had a student work on the infrared and ultraviolet. So what kind of how much are you involved with that really?
Yeah, so thanks so much for letting me do a little plug for Orbits. So Orbits is this program that we started. It was started by a colleague of mine in 2015, and she just finished her PhD, Clara Sousa Silva. She's now at Harvard, and she just finished her PhD and became a teacher at a local secondary school, and got the school students involved in the research that she'd been doing on her PhD. And that went kind of well. The students worked super hard and discovered some really cool new things, and we were able to publish that result. And so then some other colleagues of mine went back the following year to that school, and then it kind of gradually spread from there. So basically teachers' word of mouth, just talking to other teachers, said, oh, this is kind of a cool program. And I think it's cool for two reasons. I think we have two massive problems with science. There's a misunderstanding of who can be a scientist, and we have this, I think a lot of that is focused around confidence issues and this problem that we have, this expectation that you need some innate level of intellect that's just impossible to reach. And I certainly don't have that. And I think probably a lot of people on the call would also acknowledge that they don't have this Einstein level of intellect that people think you need to be an astrophysicist. And so the first thing is that it really shifts the perceptions of who can be a scientist, because the school students get to meet and work with the scientist week on week. This isn't like a one-off visit. It's researchers working with the school students and hopefully shifting to the school students leading the direction of the research, and letting the school students play around with spacecraft data from, in my case, Chandra and XMM, but Hubble, from Cluster, from loads of spacecraft around the Earth, from spacecraft on Mars, from Cassini, but pretty much any spacecraft you can imagine. You can figure out ways that you can enable school students access to that. And we just collect years and years of data from these spacecraft. And there's so much hidden in that. And there's so few scientists in the world that there's always opportunities there for school students to explore things and discover things that we didn't even know existed, right? I think that's probably what we will find we enjoy the most about science, right? It's that moment where you see something and you realize you're the first person in human history to ever see that thing. And I think that's the coolest part of being a scientist, discovering things for the first time.
I want to say hi to you, Will.
Oh, hi.
The best year of my life was being you for a year with Orbits and teaching. I mean, it was so much fun to work at UCL with that group. And then seeing all the students work at the end with that huge event that you would have, and then presenting, and they were just scientists. And thank you so much for that opportunity to kind of co-develop along with you a bit of Orbits. That was fantastic. Highly recommend it.
Thank you so much for running it while I was in the US.
It was the best thing because it gives students the opportunity to do the science themselves. This is the best thing of the Orbits program, because there are others out there, but this is the one thing I did appreciate about Orbits, was that you managed to get the astrophysicists, the students at UCL, to go into the classroom and facilitate that, because obviously it benefited them as college, PhD students. It benefited the students, obviously, because they're getting like brand new knowledge, but it also benefited the teachers, because then they had someone they could talk to and ask questions about and learn about all this current research. And they could see also, it allowed them to see their students in a completely new light. It's just amazing. So really well done, Will.
We actually, I'm probably dropping him in a bit here, but we actually have Declan Fleming, who's one of our partner teachers, is on the call. So I don't know if it's possible for him to say.
Absolutely.
To say something. But,
what's their name?
Yeah, maybe he can share his experiences. But yeah, so I think, everything you said, Lucinda, like the fact that for a lot of schools across the UK, in fact, in the UK, we have this huge teacher shortage, right? On average, your average secondary school in the UK has one or less physics teachers. And so those physics teachers are typically just drowning in work because they have to manage physics for the whole school. And so I think the opportunity that we give by providing an extra science specialist, even if it's just one evening a week when they visit, is potentially transformational for those teachers, because it takes some of the pressure off them to run projects like this. And it gives them an extra subject specialist that they can hopefully gain lots of information from. The school kids hopefully get like a relatable role model. We break that impression that scientists are these, have this innate level of genius that we can't.
So who was that a teacher you have here?
Yeah, so Declan is, I think he's in the chat actually.
Okay, I'm going to bring Declan over now.
Yeah, Declan's just
no pressure, Declan.
I'll let you take that on, and I'll bring Declan in. Declan's joining us.
If he fancies talking about it, he's probably had like an incredibly exhausting week at school, and now dragging him in front.
Welcome, Declan. I'm going to spotlight you, add you here with talk with Will. Go for it.
Hey, Will, how's it going, man?
Good.
I was just popping in the chat there that I was totally screenshotting Will's slides. Monday morning, period 1 is force on the current carrying wire and revisiting magnetic fields again. Constantly having to apologize to my students for never shutting up about fields and aurora, basically. Yeah, I said in the chat, there's a project. I say this without hyperbole. It literally changed my life, and that was so many of my students. I could talk for hours about chance meetings on Twitter and the ridiculous things that we ended up doing, and the doors that Will's opened for me, and the way that so many of my students talk about science, like in a different way. I don't want to name drop people. He will know. And it's an amazing program. It's huge. Really important to carry it on.
Yeah, I think it does some stuff that just school students don't. It's impossible for them to get that opportunity without programs like it, right? I guess we should say if anyone watching this on YouTube now or later wants to get in touch, you can just Google William Dunn at UCL and my email will pop up. Ping me an email. And
it's Astro Will with 2 underscores.
Yeah,
the number of times
underscore.
It's working. Like there's another Astro Will with 1 underscore.
There's tons of them, or tons of us. There's loads of Astro Wills. But feel free to get in touch and we'll try and make it happen. I don't want to overpromise. Like we need to find, our shortage is always amazing researchers. We're so fortunate to have so many cool researchers who work on so many different things, from machine learning to water in the atmosphere on Mars, to the northern lights on other planets, to the space environment around the Earth, to the solar wind, to imaging galaxies, to black holes, to like all these crazy things, to images of the sun, who I think hopefully provide inspirational role models for school students. But we need more. There's more schools that I think who would like to do these sorts of programs than we currently have researchers. So if you're a researcher as well and you'd like to get involved, please get in touch. We have
that was the biggest hurdle, wasn't it? Like you're making sure we had enough facilitators to go into the classrooms. And so, yes. And what I'm going to do, Will, is I'm going to give me something I could probably put into the YouTube description list to get in contact with you, or on our web pages at RAS regarding this session. And I'd be happy to get orbits or get people to get in contact with you. Thank you.
Thanks so much. Cool.
So I was going to say thank you very much, Declan, for joining us. I have a question now, away from orbits, apologies. I have a question from YouTube from James Agnew, who says, what are the best theories to explain the difference in rotational axis versus the moon orbits? I don't know if that one's, a bit of a question.
I'm going to jump in because I have the advantage that I saw it come up first, right? And I had a look because it sounds like a really interesting theory, but everything I can see, everything I remember is not that there isn't really a difference between the orbital, the rotational axis of the planet and the moon's orbits. And the real question is, the really interesting question is, why are they so similar? Because everything that we know about how the planets we've talked about already is that those rotational axes should be kind of pointing up in the solar system. Everyone knows where up is. Earth is pretty much north is up. So is the sun. So is Jupiter's. So is Saturn. Then Uranus is all the way over on its side. So something happened to tip it over. It must have been up at some point. And if you tip something over, the orbital dynamics of that world must go absolutely crazy. So why are all the moons around Uranus quite happily orbiting on a perfectly regular orbital basis? And it must be that whatever happened so early in the formation, or at least was so dramatic once they happened, that over the billions of years since, something reorganized those back into perfectly ordinary and circularized orbits. But it must have been quite quick, because all of the planets have moons that do aberrant things, and Saturn and Jupiter have vast numbers of retrograde orbiting moons that are quite happily pinging in and out. Neptune has this monster moon that is retrograde, and yet Uranus has very boring moons in some ways, in terms of it being these lovely, almost circularized orbits. What we do know, though, is that they're all small. There's no big moons. There's nothing dramatic like the Galilean moons or Titan. Now, maybe that's perfectly ordinary for an ice giant, because technically Neptune doesn't have any big moons either. It just has a captured dwarf planet that pretends to be a moon. We don't know, but it is fascinating that the moons seem to form up around the planet in that way. So John Morrell says that the dwarf planet Pluto is also rotating on its side in the early animation. That's true, but if you look at its rotational period is something like 6 to 7 days, I think, which means it must have lost a huge amount of its energy. And it also has a very odd orbit, because sometimes it dips inside of Neptune's orbit, and so it must have also encountered some really interesting dynamics. Just like Venus technically has a rotation that is upside down. It has the most inclined, but it depends whether you believe that, how you believe a planet is defined in terms of what its rotational period is. Venus's rotational period is not really a rotation at all. It's basically been forced to not rotate, and it happens to be orbiting in a way that leads it to have a sort of slightly retrograde rotation, if anything. Venus is just super weird with its day length. Pluto's odd, and that works well until you can happily discount Pluto because it's not a planet. So we'll just draw a line through it and move on. I think that's fair. Sorry to jump in front of you, Will. I thought you needed saving.
Thank you so much. I did desperately need saving from that question. Otherwise, it would just be an silent for minutes.
There's one thing that I learned, you guys are amazing at what you know, for obvious reasons. But I know that you don't always have all the answers, and that's okay. And that's why collaboration is so important, and that's the important thing about kind of my job working for the Royal Astronomical Society is, I'll go into a talk and someone will ask me a question and I have to say, I don't know that answer, and that's okay. And then it's good to kind of get that out to the public, that you guys don't have all the answers. You're brilliant. You're amazing.
It's something that a lot of our PhD students struggle with, actually, because obviously we get high-flying students, the people that have aced every exam they've ever been in, and a fundamental difference between passing exams all the way from primary school through university is that you have to get the answers right. And the point of research is that we don't know the answers. And in fact, it's better to get the answers wrong often. So just as Will was explaining, he thought he didn't see anything, and only on reflection does it start becoming apparent. Only by getting things wrong can you find the right answers. And that's a huge mind shift in terms of understanding. And I often think that people that are comfortable with getting things wrong do better than people who've always gotten things right.
It's kind of a large shift from our... Sorry, Liz.
No, please, Will, go ahead. Go ahead. I was just going to say that I'm going to capture that and play it again and again.
I mean, it's a total shift, right, from the way that the education system works, where we place, with the way we teach science is based on things that we already know, and yet when you're actually doing science, you're playing around in the unknowns. You're right on the cusp of what we don't know. And so yeah, and getting things wrong is how I spend. Someone asked earlier, like, how do you spend most of your day? Probably getting things wrong is probably how I spend most of my day. Like exploring things and then being wrong a lot, and until I find out that, until I can't find myself to be wrong anymore.
Yeah, and a fundamental thing about what we do, what makes us great researchers, is that we are creative. I think there's a lot more similarities between us and artists than a lot of people appreciate. And it's very hard to capture that, because my creativity comes out in a very different way than an artist's creativity. If anyone's ever seen my drawings will attest to. But, you know, ultimately at its core, there's a similar spark, and there's a similar kind of playfulness in science. The willingness to play around. So I'm humble enough to know that the amazing results that I've got, that the RAS have given me a medal for, come out because I'm obstinately playing with stuff that I shouldn't be. I shouldn't be doing that stuff. I should be teaching. I should be looking at the research that I promised the research agencies I'd be looking at, and instead I'm plugging away with fun things that I find are funny, and then it's a little bugbear in the back of my brain going, keep doing it, there's something there, even though I don't know why or what. And then you know, there's the magic happens, and then you get this result that no one expected. Because if you always got the results people expected, you would be a middling scientist. You need things that no one expects, which is why Will's completely right to throw caution to the wind and look at a planet that no one expects to have an X-ray source on, because X-rays come from black holes, don't be silly. And then, you know, it's how we get forward, because we find things that no one expects. That's the fundamentals of research. And it's so fascinating that there's this gap. We can't communicate that to people because they see us as this sort of like ivory tower, and it couldn't be further from the truth, really.
Will, did you expect to only find 5 photons? You emailed me.
Well, we expected 2, right? We expected it to just be reflecting whatever the sun did, and then we got 3 bonus ones. So yeah, I really hope that I have a super talented PhD student called Ophelia who's talking tomorrow, actually, and she's just yesterday put this request to do for us to look with the European Space Agency's XMM Newton telescope, and that will be, Tom, I think you call them a deep burn, right? That's a really long observation, and we should really be able to pin down the answer to this. It won't be 5 photons. We're hoping for like thousands of photons, maybe. If it looks like that 5 photon observation, then we should get hundreds of photons at least. And that'd be kind of cool, because if we do that, then we might be able to see, for instance, the atomic composition. Like, we might start to pin down what the rings are made of, if that is indeed a source of the X-rays, or what causes the aurorae. So if, for instance, the leading hypothesis for the aurorae at the moment is that it's a connection between the magnetic field and the solar wind, right? And so if it's this cusp thing where the magnetic field of the planet connects to the solar wind, then you should get solar wind particles flowing down that. And when those solar wind particles hit the atmosphere of the planet, we know that produces X-rays. And it produces X-rays with a very clear signature. So maybe we'll see that. And then that will say, okay, now we know what causes aurora on Uranus. Probably we won't see any of those things. We'll see things that we have no idea what is going on, and it will take us years of scratching our heads and not really understanding why planets are doing this weird thing, or what even they are doing. But that's kind of the fun of it as well, like not knowing what the universe is going to show you at any given time.
And that's science, isn't it? It's what's the next question? There's always, you end it with, well, then another question. So absolutely.
And a lot of the time you end up answering questions that you didn't even know you had at the beginning of it, which I think is kind of, a cool weird thing when halfway through you realize you need to ask a question that no one had ever thought to ask before. And that's the way that you get to the answer.
One thing I really love about the work that Will does is that the wavelengths, the energies are so different from what we do, that if we can both see something at the same time, it kind of fills in completely different parts of the picture. So we've certainly done this for Jupiter, where you compare what we see in the infrared with the UV, and there's some overlap. But if you compare it with what you see in the X-rays, the X-rays are blasting into regions of the atmosphere we can't even see anything in the infrared. So it's wonderful to layer these, because you're starting to build up a three-dimensional picture of the atmosphere in situ, and it's really useful and profound for that kind of stuff. I mean, the idea that we can use something like X-ray to better define the rotational period, better see the aurora than any other wavelength is almost madness, right? X-rays are this super hard to see thing, but they're also super obvious. If you see an X-ray, you've not got some horrible bit of noise from nowhere. So we're looking in the infrared. We're desperately trying to see the aurora, and in the meantime, we're looking through the Earth's atmosphere, which is hot. And so the Earth's atmosphere is glowing. The planet's glowing. Similarly, in the UV, there's a whole load of solar reflection, and it's really hard to pick out anything. Whereas, the X-rays are just one or two photons, but those two photons are vastly higher in their signal to noise because the noise is zero. So it's wonderful that you can sort of maybe pull out this kind of information. I mean, the ideal, I think, is radio. If we could get radio to work, that would be even better, because that goes all the way at the other end of the radio, of the energy level. But we can't do it from Earth, because the radio is exactly the same radio that Earth produces. So the ionosphere of Earth is hugely noisy in exactly the same window that we would hope. So we need some kind of massive space. I'm completely distracted by Lucinda's cat now. If we had like on the night side of the moon, if on the far side of the moon, some giant radio telescope, then we could profoundly understand Uranus. But before that, because it's at the other energy level, even though there's huge amounts of radio aurora, it's the way we know that there's really an aurora at Uranus and Neptune is the detections by where we were flying past. The noise levels in the universe, in the solar system, in our planet are so profoundly high that we can't possibly see anything. Whereas with X-rays, we're getting two photons, but they're beautiful, beautiful photons, right? And I love that difference.
It does feel ridiculous though when Emma said, "Oh, could you give a 30-minute talk?" I was like, 5 photons. That's six minutes per photon. I don't know if I can drag a photon out that long. But I think it's cool. I think that there's actually a mirroring here between the H3+ studies and the X-ray studies, in that these are both areas of the electromagnetic spectrum that really have been underutilized for studying planets, right? And really, to fully understand these places, we can't just look in a single waveband, because it only gives you one piece of the whole story. Like you said, Tommy, to get the 3 dimensions or to get the whole picture, you want to be attaching all of the different pieces of the EM spectrum together.
I was going to say that Emma brilliantly showed a graph earlier of that noise. And that's what I said, which is you get a whole bunch of stuff and then you've got to strain it out to see those peaks. I don't know if she's going to bring that up now, but I thought that was a really great demonstration. And she's got lots of stuff up her sleeve, I know, to show us now and again. I really, sorry about my cat. There she goes, I think. Great. Yes, that was it. Yeah, Emma, did you want to talk about your slide? Oops, is she there?
Oh, you're muted.
Right, I
Emma.
muted myself on the back of my headset, sorry. The useful thing of having 2 mute buttons, but also the unusefulness of having 2 mute buttons. So what we have here is essentially a line being taken through one of our, we call them orders, but basically one of the many pictures of slits kind of all stacked together. And this gives us kind of an idea of what we are seeing, but just with kind of the numbers. So these bits where I've kind of circled with green is basically a point where Uranus has emitted light. So it's basically gone, hi, there's something happening here, and that's with our molecule H2+. But just as I've ringed in red, we have other emissions. I'll see if I can. This is going to be a bit of a juggling. Let me stop sharing for a second and share my other screen. Sorry about this, everyone. We're going to, there we go. So bringing up with the SpectraCam, hopefully I can in that as the main spotlight. There we go. We can see just these areas like such as with the spectrocam just above the sea. There is a bright white line. That's in the same kind of row as when we're seeing our very bright 2 emission line. And that, if you just take a line straight through in basically like Y versus X direction, then you will end up with basically kind of a big peak, which, depending if it's a galactic cosmic ray or if it's due to a hot pixel or due to any kind of noise that interferes, can basically just create those annoying areas, essentially. I think that's why I call it annoying, because it requires a lot of, as I was saying with Henrik earlier, a lot of scrubbing of the data to basically make it much more cleaner and easier to use.
Are you just giving us an update right now, Emma, on where we currently are with
I can give it a
Uranus?
very, very quick update to everyone.
We do have, just to give you a heads up here, we do have Dr. Walsh in the as a participant or panelist, and he's got his, and well, first, before we get there, Will, thank you so much for being with us. You're welcome to stay on as a panelist and hang out with us for sure. We do have a classroom who's going to join us very shortly. So if you want to give us a quick update, Emma, that would be appreciated. Thank you.
Yeah, of course. So again, thank you very much, Will. Really appreciate your time with us. So the update after talking with Henrik, who is currently leading with the telescope side of things at the moment, is unfortunately, we can kind of see here in Uranus, Uranus is beginning to fade away a little bit. And that's because in Hawaii, we're at about 5:30 in the morning. So we're starting to get towards daylight or daybreak. So because of that, we're actually not being able to see the moons, nor are we seeing Uranus that much. So we're keeping our fingers crossed for the last bits of data coming through. But as you can see very nicely with the spectra, we have at least 2 lines that have come through, and it's incredibly difficult to see. I don't know if I'm going to be able to show on the live stream, but if I can kind of bring up just where we're seeing kind of the green arrows, we're seeing this very faint second line, which we were mentioning before, and that's starting to come into focus. So I'm very excited that we've got those coming through. It really helps with finding the physical quantities like temperature and column densities at Uranus. So those will help massively in deducing where the auroras are.
Excellent. Thank you so much. So please stay where you are, the H3 Plus team and Dr. Dunn. We have with us a teacher, Dr. Walsh, who I have the pleasure of also teaching GCSE astronomy with. He's from Westminster School, and he's got, I believe, Dr. Walsh, let me make sure you can turn on your mic here.
I can hear you loud and clearly. Hopefully you can hear me too.
Yeah. All the Wednesday Zoom meetings we have with GCSE students. So it's wonderful to have your students with you today.
Yep, it's good to be with you. If I can turn the camera around, you might be able to see a whole bunch. There they are. They're waving frantically at you. Yes, there they are. Good. So it's not just me. It's not just me, I promise you. We're all here. So if I could, yes. So sorry that we've only just joined the day. You've obviously been going for a while today, and so because we've only just joined, we've missed everything. So sorry about that. So you might be repeating yourselves, going over old ground again. But I don't know how you want to play this, Lucinda. I don't know if you want to just if people want to just give a little sort of 30 seconds of something, and then I will ask this illustrious and highly motivated and knowledgeable group in front of me to pepper you with impossible questions.
Well, I would. So our astronomer that we're working with is Emma Thomas. So I would ask her if she's got something that she could give, or Tom, who's also the H3 Plus team. He doesn't want to be called the leader, but if anyone has an update that they can give this Westminster class, that would be fantastic.
I'm happy to take the lead if you want, Tom. So hi, I'm Emma. I work at the University of Leicester. Today we are using the IRTF telescope that is in Hawaii. So we are looking up at the night sky in Hawaii rather than here in the UK. We had a couple of questions asking about that one. I'm just thinking, I can see in the background, may need to spotlight my second monitor. Apologies on that one. Let's get that. There we go. Hopefully, there we go, so you can see that. So we have been observing Uranus for the last 6 to 7 hours, getting towards 8 hours now. Because of the time difference, we're actually about 5:30 in the morning in Hawaii. So Uranus is getting quite hard to see. I apologize, but that's in Uranus cam on the left-hand side is basically the brighter ball is Uranus. We were able to see Umbrio and Ariel, but unfortunately, because we're getting so close towards the daylight and we've had quite a lot of clouds happening in the area. Let's see if I can fiddle just a little bit on the resolution. There we go. We're able to we're seeing Uranus, right at the second, so that's kind of interesting on that side. We're using this data to collect what is known as spectra. That's basically light, but in this case, we're looking at light from Uranus at a specific wavelength. So that's known as the infrared wavelength, which covers between 3 to 4 microns. So unfortunately, this isn't the visible light. You can't see it with your bare eyes. You have to actually have a specialized telescope and instrument to do this. In the spectrocam, I have brought up basically what we are seeing in the slit. So that's the black rectangle you're seeing across Uranus, which you're seeing 2 Uranuses at the moment. That's because Uranus is switching places along the slit. So there aren't 2, I promise. We haven't suddenly duplicated it. There is just 1. But because we have Uranus at these 2 locations, we end up with 2 lines rather than a single line on the slit. So we're seeing a positive line and a negative line, and that's because as Uranus changes from these 2 positions, so Uranus is currently in its B position, but as it shifts to the left, it's what's known as the A position. So in order to strengthen our data and to mitigate any of the noise from the Earth's atmosphere, we'll do an A minus B, which gives us these 2 lines, one in the positive, and that's your A frame, and one in the negative, which is your B frame. The molecule that we're looking at, which is H3+, is what gives us these lines and what basically lights up and says, hi, I'm here, I'm doing things, happens at specific wavelengths. So that's why we're not actually seeing like lots and lots of lines. We're only seeing at the moment 2, possibly 3 lines. But by looking at these lines and analyzing them, i.e. we look for the intensity, we can actually get ideas of what the temperature is like in the upper atmosphere, as well as what the ion density within the upper atmosphere of Uranus is as well, which is really exciting as it's this is like the leading stuff in the area for Uranus getting a better idea of what's going on so far away from our planet. And then last recap is the last 2 videos we have. Just at the very bottom, we have inside of IRTF. This is a GIF from last night showing you basically how the telescope is being operated, not only by the telescope operator, but also just any kind of daytime engineering or even daytime observations that occur. You're just seeing at the moment. And lastly, on the very right hand side, we have the sky above IRTF. This is another GIF of about 10 hours from last night of the night sky above IRTF on Mauna Kea in Hawaii, which I find absolutely stunning and just wanted to put in to show everyone.
Just sharing a picture of Mauna Kea for the students to see where you are remote observing from. And Emma is, I don't know if Henrik is still with us, but has it changed as who is the observer? Is that you now, Emma? Was it Henrik?
Henrik is still main leading at the moment. I've tried to assist, but Henrik's more on the ball than I am at the moment.
And I wanted to know if you could just introduce yourself to Dr. Walsh's class as well, and what you're a PhD student, and it sounds like you're also taking over the reins sort of as doing observations on your own. Is that correct?
In an essence, but I wouldn't like to say I'm taking over the reins. I feel that's me. That I'm taking results, but I've looked to Henrik more than anything in terms of the knowledgeable one with Uranus observations, because Henrik's been doing this for many years than I have. But I am putting my toe in the water of trying to send out proposals to telescopes. So this is my second proposal that I sent. I sent one to the Keck telescope, and unfortunately they rejected our idea. So we went to IRTF shortly afterwards and asked for the same project. and we got through. So that was very exciting. But to, I guess, round off, yes. So hi, my name's Emma Thomas. I am a third-year PhD student at the University of Leicester, which is off in the Midlands. I didn't know that one too well until I started actually traveling around most of the country. I try to think what else about myself. I look specifically, or I'm looking for the infrared aurora at Uranus. So that's why we're looking at Uranus today, is to try and spot these brighter patches of light on the planet to basically go, hey, look, it's the northern lights and the southern lights on another planet. And yeah, if I am successful, then it will be the most detailed look that we've seen at the aurora in probably, well, the aurora at Uranus since pretty much first finding infrared observations back in 1993.
Excellent, thank you so much. And I don't know if you can get any of those brilliant animations that Dr. Donahue did of the orientation of Uranus and also the magnetosphere. Maybe while you're getting that up, Dr. Walsh could prime his students for any questions about Uranus. Or, I mean, we've got, I don't know how many expert astrophysicists on the panel here. We've got Dr. Stollard, of course, we've got Dr. Dunn, if he wants to chime in, and Henrik, Dr. Mellon, and Dr. Johnson, right? Is Rosie still with us? She is.
I was going to say, I believe, Kevin Walsh, your sound is off. Or mic is off, apologies.
It was deliberately off because I'm priming my class.
Sorry, apologies.
Didn't want to hear you, everything I was saying. But we do have a question. So the question, I'll put it this way. There you go. So here we are. There are some, far away, go ahead.
How do you properly say Uranus? What's the proper name for it? Is it Uranus or?
Yeah. Of course it is. Yes.
Okay.
We're on a bit more than that. That's the best you can do. Go on.
So I know the aurora borealis or the southern lights, they're caused by magnetic fields of planets.
Yes.
And so Uranus has one magnetic field. But I know like Mars doesn't. So we're like, why does it size?
Okay, so I think the question is to do. I mean, Uranus clearly has a magnetic field. Or at least the assumption is that Uranus has a magnetic field, hence these aurorae. But what is it that gives Uranus this magnetic field that's, say, is the reason that Mars doesn't?
That's a very good question. I'm not gonna lie. I'm probably gonna need some help on this one. I know because I did a little bit of a project with Mark Lester here at the University of Leicester, where we looked at the interactions with solar wind and the magnetic fields on Mars. So Mars itself doesn't have a consistent magnetic field. It has I may need a bit of help on this one, Tom. If I recollect, it's
I can tag in anytime you want, Emma. I'm quite happy to help out if you need me to. Okay, so there's lots going on here, and we don't have all the answers to it. Will talked a little bit about this earlier. Let's say, well, why doesn't Mars have a magnetic field? Well, Mars doesn't have a magnetic field because effectively it's a dead planet. There's a lot of evidence of geological activity on Mars from the past, but most of that has stopped, and that's just because it's small. It doesn't have as much heat in it as the Earth, and so it's dried up, it's solidified. And so what you need to make any magnetic field is basically you need to make currents move, and so you need a medium for those currents to move through. And so in the Earth, we know that there's this wonderful solid iron core with a liquid iron surrounding it, and that causes all sorts of spinning, slushing motions in that liquid iron core. As soon as you induce any kind of magnetic field, you start getting currents, and those currents drive magnetic fields, and it starts this feedback loop that ultimately allows you to sustain a magnetic field. It's called a self created dynamo. Effectively, the magnetic field creates currents, and the currents create magnetic fields, and it goes on and on forever. So we know a lot about that from Earth because we can look at the Earth much more easily. We know that Jupiter and Saturn both have magnetic fields that are somewhat similar to the Earth. Obviously, the compositions are completely different, and we think that those have magnetic fields because they have hydrogen that's crushed so much that it's kind of like a metal. So we think that maybe that's where the magnetic field is. The Uranus and Neptune magnetic fields are a bit harder to understand because there's not really evidence of that kind of material, the kind of material you need to generate a magnetic field in the same way. And also the magnetic field is so weird. It can't be a sort of nice, simple, boring process. So a lot of the theories at the moment have sort of looked at the idea that maybe this sort of surrounding layer away from the core has some sort of slushy ice mantle, and that is conductive enough that it can generate a magnetic field. But the real answer is we just don't know. We don't know why there's a magnetic field. We do know that there is one because we flew past with one spacecraft and it was able to measure it. What it measured was the profoundly most weird magnetic field we've ever seen until it reached Neptune and found an even weirder one. So we know that ice giants have very different magnetic fields, and we don't really know why. So in order to answer that question, you need more than just a quick fly past. You need a detailed kind of mission, similar to the Juno mission at Jupiter. And of course, I've just said that we understand Jupiter really well. And what Juno has shown is we don't understand Jupiter well at all. So the more you take this data, the more you reveal that actually Jupiter was supposed to be really easy. But in fact, there's all sorts of weird and wonderful things going on at Jupiter. There's some kind of magnetic field stuck somewhere near the pole that isn't in the center. And undoubtedly, we'll say similar stuff. But Uranus has such a weird magnetic field that it has two magnetic equators. I can't really explain to you how that works, except for the fact that if you had a compass, it would be pretty useless if you were at Uranus, basically. So, as with many things with Uranus, we don't know, and we just wish we did. And that's basically one of the major reasons that all of us are working on trying to understand the aurora. It's one of the windows we have into understanding those worlds.
Okay, thank you very much. Yes, Molly.
You mentioned a sort of idea of a self-creating sort of dynamo. Does that sort of go so just having the medium, or does that require some sort of energy, possibly from like the orbit or the rotation of a planetary body?
I mean, it has to start from something. You can't get something from nothing, but there's lots of other magnetic fields. So the sun has a huge magnetic field, and it mostly hits us from this solar wind that expands out. And you can induce currents very easily. And we see all sorts of interesting evidence of that in terms of the upper atmosphere of the Earth and the induction that we see there. And there's also people that are working on detecting oil under the surface of the Earth by the induced currents that you can see up in the ionosphere. So it doesn't take a lot to start that process, and it just feeds off of itself, I think. So it is an interesting quandary. Is it a chicken and egg thing? You know, how do you get things going? But I don't think we need to worry about that because there's so many magnetic fields in the universe that you could just trigger that trip switch, and once it's going, it just gets stronger and stronger and has this very positive feedback. So you end up with a very strong magnetic field.
Well, when the students get more questions, I know there's a hand up. Dr. Walsh, I wondered have you ever had orbits at Westminster? If not, may I please introduce you to Dr. Will Dunn?
Okay, right. Excellent. Good. Hello. How do you do? Thank you. Yeah. We had another question there from Sasha.
So, do we know why there's any? Do you know what magnetic compounds are present on Uranus, or why it would have a magnetic field at all? Because you wouldn't expect it to.
So I think the question really, yeah, I think that was addressed in terms of the very high pressure. I mean, they just don't know really. Is the short answer to that. But I think another thing we were talking about earlier, actually, before we came on, was the fact that the planet is tilted. So those images you were showing us earlier, Emma, were we looking directly at the pole there?
Sorry, apologies. I may have to flick through a couple. So are you referring to these ones?
Yes, exactly. Yes. So
okay.
At the moment, I mean,
it's rather hard to see. Apologies. I think we're finishing up at the moment, just because it's gotten so close to daytime. But this is the last image we have.
Do you want to pull up the movie that James made? That's a good representation.
That's a much better representation. Yes, sorry. There we go. So
okay.
Spotlight onto that one. I don't know how big that is on the screen. Apologies. Hopefully that's clear enough to see. But yes, so at the moment we are looking at, well, it gets a bit up in the air. So technically this is the northern pole in IAU standard. And the other side is the southern pole, but depending on which scientist you talk to, that can get flipped around, so it can get quite confusing very quickly. But in our observations, what we're seeing is basically the southern pole is directed towards us and the northern pole is currently facing away from us. But back when I was, well, the data that I'm currently looking at back in 2006, we were actually able to see both the northern pole and the southern pole at the same time. And then previous to that, we saw more of the northern pole than the southern pole. So it's a fascinating thing with Uranus where you can, I think it'd be like 10 years difference, and you'll go from being able to see both poles to only one pole to only solidly one pole, and then back again to seeing two poles. And kind of reiterates why we need to have so many people working on Uranus and Neptune, because Uranus takes about 84 years to rotate around the sun. So at the moment, we actually don't have a complete idea of how Uranus varies in one whole cycle around the sun. And it's something that we are still really looking into at the very beginning of understanding what the long-term variability is of the planet.
And those red blobs are temperature variations, or?
So the red blobs are approximations of where we expect the infrared aurora to be in our observations. So at the moment, we expect to see the southern aurora kind of rotating around the northern or southern pole, whilst the northern aurora is more close to the very edge of the planet at the moment.
And presumably this means that the rotational axis and magnetic axes are not aligned.
Yes, so they're not aligned at all, basically. They are about 59 degrees difference between the two of them. What also makes Uranus really fascinating is that the center of where the magnetic field is actually off from the planet's midpoint, from about 0.3 Uranian radiuses. So it really creates this very funky looking aurora, where we actually have a much larger northern aurora and a much smaller southern aurora than we would see at any other planet.
And how is it, I mean, without going into too much detail, how is it that you made these predictions? I mean, you know, why are you expecting to see aurora in these places?
That's a really good question. So this kind of leads back to the work back with Voyager 2. I'm seeing if I can bring up the figure I had before. There we go. So let me just zoom in. There we go. And then I will share on my screen. I don't know if that's going to override my other camera. Hopefully. So hopefully you can see this image. This is from Herbert 2009. It is reiterating the observations that we saw from Voyager 2. All of the black smudges that you see are emissions in the ultraviolet spectrum. And the pictures that we have rotating on Uranus at the moment come from these, which come from this image specifically, which is marking out where we would expect, or where we expect the magnetic poles to lie, their rotation, and where the aurorae lie due to where we've seen the emissions themselves. Hence why we've discussed before, it's much smaller. You see about 240 ULS longitude. At minus 30 ULS latitude, we actually see a very small condensed southern aurora, and in comparison, we see a very widespread northern aurora, which is, I think, my favorite thing I love to say with the northern aurora is that it actually, I'm trying to think, I didn't know the word at one point. It itself actually spreads over the equator at Uranus. So it's almost a fascinating concept to think that if you were, at the equator on Earth, that you would be able to see the northern lights, no problem. It's an absolutely fascinating concept for me to just try and get my head around,
Absolutely. Got a couple more questions. So yes, go first.
So just a quick question considering the layers of Neptune. Does it have an iron core?
Uranus or Neptune? Uranus.
It's like Uranus.
Yes. Does it have an iron core?
Yes.
Well,
what are the different names?
That's a very good question. I'm not sure I can answer that one actually, because I don't know too much on the core of Uranus. My understanding is that there is metallic hydrogen and helium, if I'm correct in thinking that, Tom. No. Okay, no, I'm not. Sorry, apologies.
Shall I step in again?
I think you're going to have to
or
step
should we get
in.
Will to step in?
We can get.
No, Will's backing away. All right, I'll try my best. I mean, ultimately, again, it's really hard to say because the only way we can understand what the interior of a planet like this is by looking remotely. You know, we know from Earth really well because we have seismology. We can measure earthquakes as they ring around the Earth and bounce through all of the layers, and that gives us a really good picture of all of the different layers, and that's why we know that there's a solid metal core and a liquid metal core, because different waves move at different velocities or don't even flow at velocity through these layers. So we're cheating on Earth because we have this technique that we just can't use for most planets. But other techniques we can use is by basically knowing where the spacecraft is and measuring very small variations in its orbit. We can measure the gravitational pull of different parts of the atmosphere as it rotates around. So that's one technique that we're using at Jupiter to measure these things in great detail. We don't have that level of detail at Uranus or Neptune because we have one flyby for each planet. So we have a very cursory understanding of the interior. Most of that comes from modeling. So it's not even measurements at all. It's just, let's get a load of stuff that we think that the planet is made of and stick it together and see whether it matches up with what we're seeing. We know what the composition of the atmosphere is, so that gives us a guide. Based on theories of how planets form, there's probably some metal in there. There's probably some rock. And we think that was probably what started the formation. So there was probably an Earth-like world, super Earth, maybe 5 or 10 times the mass of the Earth, and that started dragging in all of these ices and growing. But that's all theoretical, and the only way to answer that is to go back. But it's a really interesting question that we probably still don't really know for Jupiter and Saturn, where we've had a lot more information. Getting details of the interiors is incredibly hard because it's so far removed from where we are.
Max.
Are the aurorae only infrared, or are they also visible light or ultraviolet?
Yeah. So what frequency spectrum is there for the aurorae?
Well, this is definitely a Will question. Come on.
All right. Okay. Okay. So we've only visited these planets once, right? In 1986 and 1989. So 1986 for Uranus and 1989 for Neptune. And that was with the Voyager spacecraft. So the Voyager spacecraft launched in 1977, and it was pretty amazing, right? This event happens once every 175 years, and the planets sit in alignment. And it happened that I guess we just got lucky that like human technological evolution happened at the moment where they were lined up. And so the Voyager spacecraft flew all the way past, all the way through. And so Jupiter, Saturn, and then each of them went to Uranus or Neptune. So they saw at Uranus and at Neptune, they saw ultraviolet aurora, and they saw radio emissions that we think are from the aurora as well. And what they saw is that the radio emissions, so sometimes the sun gives off these massive explosions. Like simplistically, they're called solar storms, but sometimes we call them like coronal mass ejections. They're huge explosions of matter that work their way out through the solar system. When those things hit a planet, they hit the magnetic field of the planet and they squash it. And so what was seen at Uranus is that when those things squash the magnetic field, then you get bright bursts of radio emission. And at Earth, we know that when those things happen, we get really bright aurora. So what we think is happening at Uranus, maybe Neptune as well, we don't really know. But for Uranus, at least, we think that the solar wind here plays some part in triggering the northern lights. And so we've seen them in the UV and the radio. They were seen in the 1980s. And then again, I think for the first time, but someone correct me if I'm wrong here, in 2011 with the Hubble Space Telescope was the first time they were seen again in the ultraviolet for Uranus. Since then, they've been seen several more times in the ultraviolet. So we know that the planets produce UV and radio emission. There's a possibility they pump out X-rays as well, which is kind of weird because X-rays are these things that are associated with really energetic processes. So maybe X-rays. And then I think the whole point, tell me if I'm wrong here, Emma, but I think like one of the big drivers for these observations that you guys just saw happening right now is to figure out, can we see them also in the infrared, and specifically in certain bits of the infrared? So I guess in summary, so we see them in radio emissions, UV emissions, maybe X-ray, and maybe hopefully the whole point of this weekend's observations is to figure out, do we also see H3+, which is like a molecule that's seen in the infrared? Tell me if I'm wrong here. This is the H3+ team, and I'm not one of them. Although I'd love to be. They're a great group of people. So yeah, so I think we see them across lots of bands of the EM spectrum. Does that help?
Yes, thank you. There's another question. Yes, Sasha.
So when do you think we'll next be able to visit Uranus on a mission, so we can find out more about your work?
Yeah, are there missions planned?
I mean, I'm happy to take somewhat on this, although Tom, you have had a big hand with Trident, which is looking at sending a mission to Neptune, but as well focusing mainly with Trident, the moon of Neptune, which it was going really, really well. And then they have picked 2 missions to Venus instead. So unfortunately, that isn't to come. At the moment, to my knowledge, there are no missions in construction to Neptune and to Uranus, which is a massive shame. We had Leon earlier discussing about kind of the key windows of time. I think he mentioned that if we want to try and get a mission to Uranus and Neptune, we're looking at, for Uranus, sending something off in 2030, I think, to about 2034. So that's in a good 10-15 years. And then even then it's going to take a good 10-15 years for it even to arrive at Uranus. So we're talking not getting any results for about 30-40 years, which is a long time to think about it. Scary to think about it that long.
Yeah, it's an important point. I desperately want a mission to Uranus or Neptune. I don't care which, to be honest. I think they will both be amazing. I think that more and more of the planetary community are coming behind that call, and I'm hoping we'll be finding out in the next year whether America agrees with us as a community. If they highlight Uranus and Neptune as the most important mission, we will have one. It will arrive probably around 2045. So I will be retiring, and you guys could be about my age and in a prime position to understand and analyze the data, maybe even take a lead on the instrumentation. This kind of mission is very much us trying to set the pathway for you guys in the future to do the observations and understand the data.
You are a challenge. Right, I'm very conscious of the time. It's been a very long day for our panelists here, so we'll just have one more question. Go on.
How many moons does Uranus have? And of those, which are like, I guess, the most interesting?
So it's a question about them. Do we know how many moons Uranus has? Are we still counting them?
We are definitely still counting, right? I'm desperately Googling. Uranus is really interesting because it doesn't have a big moon, and that's the important thing, really. It's the only big planet, only one of the 4 giant planets that doesn't have a big moon. It has quite a lot of moderately sized moons, I think 4 or 5. And then all of the gas giants have a whole slew of moons that are mostly just junk that they picked up over time. I'm happy to defer to other people for favorite moon for Uranus. I certainly have one.
Well, I have one because my full name's actually Rosalind, and there's a moon around Uranus called Rosalind, so maybe that's what I was named after.
No bias.
Can't be sure.
That's a fair reason.
Okay, well, we'll have to leave it there. But thanks ever so much to all of you for extending your day and for fielding our questions. And I hope you won't mind if I get some more in the next 20 minutes or so, if I send them your way. That would be great.
Yeah, we're happy to answer anything you have to throw at us.
Super. Okay, thanks. Can we have a round of applause?
Just
Thank you
wanted
very
to say, thank you to all our panelists, our wonderful scientists here. Thank you to you, Dr. Walsh, for joining us today and your class at Westminster School. We definitely, you made today this program. Thank you for being a part of it. We definitely appreciate it. We're going to be here Saturday and Sunday. So registration is still available on Eventbrite. If you register, you could join us on Zoom and listen to more about Emma's amazing work on Uranus. And thank you to all our scientists here. Before we go, I did introduce Will, Dr. Dunn, to Dr. Walsh, only because if you haven't had anyone from the Orbits program at your school, I highly recommend it. And then I wanted to ask Emma introduce herself before we go. Maybe the other scientists can just a quick, what do you do? What's your area of research to these students, just to kind of let them understand and know what work you do.
So I'm Dr. Tom Stallard, and I am focused mostly on Jupiter aurora and also the sort of boring bits of Jupiter, down at the equator that are becoming more and more interesting as we look. Well,
I am Dr. William Dunn. I X-ray planets, all sorts of planets, comets, moons, lots of things. So that's kind of weird because people normally use X-ray instruments to study black holes and colliding black holes and crazy energetic things, the whole structure of the universe, how clusters of galaxies stitch together, and how they're connected, and therefore how the universe evolves. But I just point them at planets and try to understand, therefore, what planets are made of, how the magnetospheres and the aurorae work, and stuff like that.
Rosie.
Hello, I'm Dr. Rosie Johnson, and like Tom, I like to study the more exciting bits of Jupiter. I like to study Jupiter's northern lights and Jupiter's southern lights. I've also in the past studied the Earth's northern lights, and I worked as a Northern Lights tour guide for a bit, which was a little bit of a dream job. But now I'm back on Jupiter, which is also a dream job because basically I pretty much do what Emma does, but for Jupiter. So the same observing thing with the spectra, looking at Jupiter's northern and southern lights.
And Emma, do you want to add anything to that? I mean, I could get it all on video. That would be great. Go ahead.
So yes, I guess reiterating, hi, I'm Emma. I am a third year PhD student working with Tom and using a lot of Rosie's work. I look at, I'm trying to map the aurora, the infrared aurora at Uranus, that's the northern and southern lights. Tom, I don't know if you had something to add to that, or? No, sorry, apologies, thought you did. But yes, sorry, I am looking to fully map the infrared aurora at Uranus, both the northern and southern, which hasn't been done in great detail since first finding infrared evidence of Uranus since back in 1993.
Excellent, thank you. Sorry to keep you, Dr. Walsh.
Not at all. Thank you very much, and it's great to see such interplanetary collaboration taking place. It's heartwarming, and good luck with all your work, all of you. And as I say, I hope you don't mind if we send you the odd question, and it will be an odd question in the days and weeks ahead. Okay, thanks very much for your time and expertise and for sharing your enthusiasm with us today. Thanks again. Okay, bye-bye.
Bye. So this is, I don't know if you want to do any sort of summary today, Emma, of, or did you, how would you like to end today? We already passed our time.
I feel very bad that we skipped over one of the really important questions that Dr. Walsh rushed past for I don't really understand why. I think it's really important we return to that question because it's terrible to leave a student hanging. We should really talk about how you say Uranus, because I think it's a really important aspect of the work that we do when studying the planet, right? Yeah. And there's different ways people pronounce Uranus, and they're all rude. There's no good way of saying Uranus, because you could say Uranus, in which case you're saying something rude, or you could say Uranus, in which case you're talking about something rude, or you could say you're an ass, in which case you're being rude to someone. The only really feasible way of saying it that isn't rude is Uranus, which I've never heard anyone say. So I don't know if anyone has preferences on how you say it.
This is a purely scientific discussion, correct?
Absolutely. Absolutely. Well, you know, we are studying the hot gaseous envelope around Uranus, so I think it's important to be clear here about how we define terms.
I hope I still have my job tomorrow. Does anyone else want to weigh in? I can't wait till James comes tomorrow. I know Sean was actually supposed to share a joke with us from way back when, but I didn't hear that. Maybe she's going to join us tomorrow. So maybe does anyone else want to weigh in?
I guess, yeah, I'm just going to reiterate with Tom. Back a couple of years ago when I was doing planetarium talks, I had a very firm talk with the person in charge who was like, you've got to say Uranus, because but you can't say Uranus, because if you say Uranus you'll never get past everyone giggling and you won't be able to do the talk, so you've got to say Uranus instead. But I agree, we can't be stuck up about it in a sense, because at the end of the day everyone knows it is Uranus, and that's just how it is, and if people giggle, that's fine. It means that they are engaged, and that's, at the end of the day, that's just what we want from people, is for people to be engaged and interested in what's going on.
We've had some Royal Society meetings about Uranus and there's been giggling. Let's be clear, no one can not talk about Uranus and not giggle at some point.
I wanted them to...
I can't handle, I have to say Uranus. I can't take myself seriously in normal times, let alone when I have to say Uranus. I just say it wrong. I feel like the first time I observed it with Henrik, I feel like he probably got sick of me because I just kept making so many jokes and basically just laughing at myself. I'm not even sure the jokes were funny.
I'd be happy if they called it George. It would be easier teaching about George. Will, any thoughts from you? I hear you're pretty silent on this subject.
Because I'll just be laughing the whole way through. Yeah, I mean, X-raying Uranus.
You said that earlier, and I don't know if I have my camera off, but that's another sound bite I'm going to collect from this recording. There's lots of good ones.
Well, the best way to observe Uranus is through a giant mirror with a hole in the middle, so the light gets through. I find.
Okay, are we going to wrap up today? Cannot wait. We still have 2 more days of this, folks. It's going to be fun. Emma, is there any last words from you as our featured scientist? And this is your research. Is there anything you want to share with us about anything you observed today in particular?
Well, I can give the closing notes, which is this morning we saw what we thought were bright emissions at the northern pole, which is very exciting. I'll see if I can flick very quickly to James's lovely video. We should shortly be coming along. We see kind of a red area poking up near the edge of the animation here on the edge of the planet, which we're hoping, because we're seeing that emission, that may have been the northern aurora, but it may have been the southern aurora. And again, just because of the amount of pixels that we get, it's sometimes difficult to spot which one's which. We did see in the middle of the day, towards about 1-2 o'clock BST here, but again, some emission brightening more towards the middle, so we think that's possibly evidence that we saw part of the southern aurora. So hopefully today's result is we saw part of the northern aurora and southern aurora. I can't promise I'll have lovely pictures of if we saw stuff, because that would require the code to play ball tonight, and I don't know how much it wants to play ball. But fingers crossed I'll at least have a nice pretty GIF of today's observations with Kyle, that's the imager, and I'll be able to put that up for everyone tomorrow so they can see kind of what happened today in terms of the moons, and probably give a good idea in terms of by the end how terrible the vision gets on Uranus because daylight's happening, along with how clouds interact with our seeing Uranus. But if it's okay, I was just going to add at the very end that I was incredibly thankful for everyone that's come along today. I myself tried to message out to a lot of friends and other players that I play a lot of games, so I've been messaging a lot of people in my Discord groups going, hi, would you like to see space? So I'm very appreciative that a couple of them have come along and said hi, but equally I am very appreciative for anyone that decided, who saw this YouTube link or saw the Zoom link and went, hey, I'd like to come along. So yeah, I'm incredibly thankful, and I hope that you'll be excited and interested to come along tomorrow and Sunday.
Well, that's fantastic. It's been wonderful to be with you all, but this isn't over. I've just asked Henrik if he'd turn off his video and join us. If there isn't anything else for people to add, we should all wave and say goodbye, and then I'm going to end this Zoom call. Is that okay? Is there anything else? Anyone? Henrik, did you want to add into anything before we say goodbye?
Just to say this has been a fantastic set of observations, and it's fun to share that with people, I think. Yeah. Going to be some good science out of this.
And you're off on a holiday tomorrow, so
yes,
have a wonderful time, everyone. Thank you so much, everyone, for being here, and I'll see you guys bright and early tomorrow morning. So bye. Thank you so much.
Thank you so much, Lucinda.
Bye,
See you tomorrow.
See you tomorrow.
See everyone tomorrow.